course, I had already missed 2 weeks of intensive lectures and practicals. On the first day of my attendance, the last 2 hours were allotted to practicals in statistics. The teacher in charge was a bright-looking, bespectacled young man who appeared to me like a demonstrator in my college lab. I was sitting in the last row in the class of more than 30 students, each one of whom had a facet mechanical calculator and a sheaf of dull red graph sheets. I was sitting quietly without understanding a word of the lecture that was going on. After a few minutes, the teacher came to my desk and asked, "Where is your practical record?" I replied, "Is it sold in the office?" He was puzzled, but he went to the blackboard and continued the lecture. At the end of day's class, when the bell rang, I shot out of nearest drawer, but the teacher confronted me and said, "Go and see the head." The next moment, he disappeared from my sight. I inquired about the location of a head's office. The partitioning glass screen of the head's office had a name, C.R. Rao, painted in blue, and entrance was guarded by an old peon in khaki. I told him that I have to meet the head. He went in, came out a minute later, and let me in. To my consternation, I saw my teacher greeting me with a smile. He said, "Remember to maintain a record of all your practical work done in the class and bring it. Now you may go and have your tiffin in the hostel." Such was my introduction to Dr. Rao. To this day, he maintains the same puckish humor. In those days of institute, there was only one professor, and it was Director P.C. Malnovis. All the rest were called workers or students. The famous younger professor of statistics was just addressed Dr. Rao. In our class, most of the students had no statistical background. In those days, we had no computers or electric calculators. I, for one, was not even aware of elementary notions like mean, variance, standard deviation, median, mode, etc., which today's class children are taught in their mathematics lessons. Dr. Rao made us toss a coin 100 times and record the outcomes in the form of a sequence of H and T, H for head and T for tail. Pooling the data from the whole class, bunching them properly, and analyzing the frequencies of H and T. In the bunches, he deftly navigated us to drawing the bell-shaped curve approximating the normal density. Another example I still remember is cutting strips of paper of standard length, say 6 centimeters, without using any scale. Repeating this, say 10 times, measuring the lengths of different strips, recording the deviation from the standard, making the frequency table of the pooled data of the deviations, plotting a histogram, and arriving at an approximation for the bell-shaped curve of the normal density. Combined with the theory classes in probability, we finally learned to appreciate the De Moivre's limit theorem for binomial trials and the Gauss-Laplace theorem in the theory of errors. Slowly and steadily, all the well-known elementary probability distributions like the binomial, negative binomial, geometric, hypergeometric, Poisson, beta, gamma, chi-square, student t, Fisher's F, etc., rode by appearing in practical statistical problems encompassing a variety of scientific phenomena. Dr. Rao's classes remind me even today the spirit of William Feller's dictum, how the Poisson distribution happens. Star in the sky, animal litter in the fields, bacteria in the blood, particles emitted by a radioactive material, accidents in a street, and so on. Another striking example from his class was the problem of estimating the number of fish in a pond using the hypergeometric model. The limit to this variety of applications of statistics is the sky. In the winter of the same year, 1956, which was the Silver Jubilee year of ISI, a big international conference was organized in the RTS. Many distinguished scientists from all over the world participated in the deliberations of this conference. Sir Ronald Fisher from England, Professor Jerzy Neyman from the US, academicians N.N. Bogliobo and academicians Amberstumian from the former Soviet Union, Professor T. Kitagawa from Japan, among others were present. Our classes were stopped and all the students were advised to attend the lectures. Tea and refreshments were provided gratis. I could not understand much from the lectures, but some keywords got strongly registered in the back of my mind. There was a memorable debate in one session in which the statistical giant Fisher and Neyman participated. Whereas Fisher concentrated on the estimation of parameters in parametric models, Neyman emphasized the importance of testing hypotheses in practical statistical problems. Both these theories were included in the syllabus of our program. We had some knowledge of the method of maximum likelihood estimation as well as the famous chi-square test. The Fisher-Neyman debate was prolonged. The chairman of the session was Dr. Rao himself. When the time limit was very much exceeded and Dr. Rao could not stop it by the standard methods, he got up and declared, "It is time for tea." The debate stopped and the audience began to disperse. Later, in a lecture organized in the city, Neyman gave a lucid and elementary lecture on the philosophy of testing hypotheses and explained the basic notions of errors of first and second kind and power of a test. This, together with a course on the same topic given a year later by Professor R.R. Bahadur, fortified our knowledge of testing hypotheses as well as Abraham Ward's sequential analysis. For our readers, it may be interesting to know that Wards acknowledges the role of Professor P.C. Mahalanobis in the introduction of sequential analysis in statistical thought while working on sample surveys. There was a lecture by academician Bogliobo in statistical mechanics, and this new keyword left a deep impression on me. 2 years later, I read a paper by Bogliobo in ergodic theory, which proved useful in writing my PhD thesis. Academician Amström lectured on the distribution of multiple stars in the astronomy. These two lectures opened my eyes to the appearance of statistical ideas in physics. After the conference was over, We were back to our classes and frequent examinations. In many tests, we were permitted to use our books and notes, and there was no time limit. This was indeed a new experience. During an exam, Dr. Rao visited the classroom to enjoy watching the students struggle. The facet machine was an important tool in the exam. In my second year, Dr. Rao gave two courses. The first one was an introduction to design of experiments and analysis of variance. Notions like randomized block designs, balanced incomplete block designs, partially balanced incomplete block designs, Latin square designs, factorial designs rolled by. The role of randomization in the elimination of bias was a revelation. In the same course, finite Galois field and their role in the construction of designs were discussed. Later, I came to know about the role of finite fields in the construction of Dr. Rao's orthogonal arrays, Chaudhary Henkin, that is BCH course in communication and information theory. In 1960, Bose, Parker, and Srikande used finite fields in the construction of mutually orthogonal Latin squares earned the title Euler spoiler and hit the headlines of New York Times. Today, orthogonal arrays of Dr. Rao are used in the construction of entangled states in quantum information theory. They also appear in the construction of quantum error correcting codes. The same year, Dr. Rao gave a course on multivariate analysis, which involved the central role of the multivariate normal distribution. It is here we learned about Mahalanobis D square and its distribution as derived by R.C. Bose and S.N. Roy. What I have said reveals the distinguishing feature of the education in RTS. The students came to know about the fundamental contribution to statistics by our own teachers. In our theory classes, we learned two important contributions from Dr. Rao. The first, the Kramer-Rao bound, the second, Rao-Blackwell theorem. The first result was proved by Dr. Rao when he was just 25 years old. Today, it is used in a wide variety of statistical applications in almost all science. New research in this bound have appeared in non-commutative quantum statistics. The Kramer-Rao bound puts a limit on the variance of any unbiased estimator of a parameter appearing in a statistical model. It is no wonder that the position momentum Heisenberg uncertainty relation can be derived from the Kramer-Rao bound as a corollary. The second result mentioned here tells how an unbiased estimate of a parameter can be improved if a sufficient statistic is available. If a complete sufficient statistics is available, the estimate can be achieved. Today, these results are taught in any undergraduate statistics program world over. The third year of our course was reserved for a project. Each student was given the freedom to choose the topic and appear with a brief outline. I chose the title, The Moments Problem, and made a brief presentation of its outline based on a book by Shohat and Tamaskin. V.S. Varadarajan was appointed as my tutor for the project. It was a wonderful gift for me. In the course of the project, I learned many subjects like set theory, measure theory, and general topology by taking evening walks around the ISI ponds, listening to him and studying books by Kamke, Holmes, Kelly, and so on. Using the generous book grants from ISI, I could purchase many useful books for my work. After completing the studies, I wrote a short essay on my project and made a presentation to an audience including Dr. Rao, Varadarajan, and many of my teachers. Later, I told Dr. Rao that I would like to do a PhD. He said, go and learn information theory. Dr. Joshi, who is currently a visiting scientist, will help you. At Dr. Joshi's suggestion, I began to read Mathematical Foundation of Information Theory by the Russian probabilist A.I. Kinchin. This in turn led me to study lectures in ergodic theory by P.R. Holmes. After a brief stay in ISI, Dr. Joshi left. I explained to Dr. Rao what I was studying. I tried to explain the ideas of basic information theory to Dr. Rao and report my progress. Dr. Rao was a very busy man, and soon I was left alone. After a year's work, I prepared a paper, described its results to Dr. Rao. I submitted my paper to the Annals of Mathematical Statistics, and it was rejected by the editor with the comment that I am on a wrong track in the subject of information theory. Without making any changes, I sent the same paper to Illinois Journal of Mathematics, for which J.L. Duke was the editor. Within a few months, I got an acceptance letter along with a nice report from the referee. When I showed it to Dr. Rao, he went through it quickly, smiled, and said, "Your scholarship has now been increased." My joy knew no bounds. It enabled me to read the whole of Kinchin as well as Holmes and write a short thesis on information theory and submit it to ISI for the award of a PhD degree. By this time, ISI was declared an institute of national importance by the nation's parliament. In its first convocation, I got my PhD degree. In the same convocation, Sir Ronald Fisher was conferred an honorary DSc of the ISI. I also got a faculty position in the RTS. It was Dr. Rao's personal decision to offer me this position without any advertisement or interview. So this was a journey of KRP with the CRR at RTS.
It's a great honor for
Thank you. Yeah. Thank you, Prasad, for presenting KRP's lecture. It did a very nicely presented and nicely written lecture. Even I didn't know some of the things that were mentioned. So it was very good to hear the experiences in RTS. I want to ask whether any of the audience has any comment or question or remark.
unmuting.
Yeah, you may raise your hand. Yeah.
Yeah, I just want to say that Professor K.R. Parsardi was also my teacher, and he taught us vector spaces and linear algebra. And I am grateful to him all these years. He is my guru along with Professor Rao, and I enjoyed listening to his talk on the life at ISI during our early years. Thank you.
Thank you. Yeah, he was my teacher also. Many of us had him as a professor. Thank you. Yeah, Bikasina, you are raising your hand. Is it Professor Bikasena? You want to say something?
Yeah. I was going to thank Professor Parthasarathi for taking the pain of narrating in so many nice words about his deep interaction and motivation that he got from Professor Rao. It's a very wonderful document for those of us who quite work with Professor Rao. It's a very wonderful document. Thanks to Professor Parthasarathi.
Thank you.
Parthasarathi is also my de facto teacher. We have been together for many years in Calcutta and Delhi. He is also like my de facto teacher. Thanks, Professor.
Thank you very much. Thank you very much.
Any other comment or question? Yeah. Okay, so Professor KRP, do you want to add some last minute comment or remark?
Yes, after my PhD was over, Professor Rao asked for the next, do you have any suggestions for the award of an honorary degree, honorary DSc degree of the Indian Statistical Institute? And Professor Vardhan also was with me at that time, and we suggested that academician A.N. Kolmogorov from the of Moscow would make a wonderful addition for this great honor of honorary degree. Then Professor Mahalanobis and Dr. Rao succeeded in organizing a visit by Kolmogorov, and he was in India for a month, and he gave, of course, he did not know any English. In fact, it was very interesting. In the ISI campus, people asked him, can you speak English? And Kolmogorov replied, I know Indian better. Am I audible?
Yes.
Yeah. Professor BLSP wants to join. Please unmute.
Oh, just I haven't finished. I haven't finished my comments.
Okay, please.
Then, after Kolmogorov's return to Moscow, he suggested that I may visit Moscow University, and at his suggestion, and all the arrangements were made by both Professor Mahalanobis and C.R. Rao for my visit to Moscow as a visiting fellow of the USSR Academy of Sciences. I had a very valuable year at the Moscow University as well as Steklov Mathematical Institute. And during my stay in Moscow, Vardhan's thesis was lying in Moscow for examination, and they were not getting the referees reports from Kolmogorov for quite some time, and Vardhan was deeply worried, and I requested Kolmogorov and asked him whether it would be possible to hasten this referee's report. And Kolmogorov wrote a very nice report for the PhD thesis of Professor Vardhan. Thank you very much.
Yeah, BLSP. Yeah, please go ahead. Prakash.
I want to supplement to what Professor Karpasardi said. Professor C.R. Rao, he designed the course for MSTAT and BSTAT programs, for which the MSTAT, I was the first student in the MSTAT program. And as a part of our training, Professor Karpi also mentioned that one of the experiments we have to do is to toss a coin 1,000 times and prepare a histogram, and then check whether it is an appropriate scaling, is it bell-shaped or not. But another one is there, which some of you might know. We were sent to a place called Giridhi in Bihar, where we have to do the sample surveys, and we have to design the schedule and do the sample surveys, and then learn how to do this, starting from the design of the survey as well as execute the survey and write reports. And this is all, I think, Professor Rao's ideas that students in statistics should not only be good in their theoretical work and so on, but they should also know how to do the practical aspects of it. And this is a revelation, and all of us, the students. And in fact, even though the courses were a bit heavy as it is right now, it's not the case. So we were asked at one time, there was a time when there was an exam, the holidays were announced suddenly during the exam time. So even though we were asked to take one exam, since it could not be done due to holiday, we had to write 3 exams the next day. So this Professor Sierra was a taskmaster, but then that's a part of learning process. So this is what I would like to supplement what Professor K.R. Parthasarathi has mentioned. Thank you.
Okay, so thank you very much. I think we will move on to the next talk by Professor Vikas Sinha on exact inference in a multinomial.
Bapat, my talk is already recorded, so I hope they will play it.
Yeah, they will play it now.
Okay. Me to be invited to speak.
Exact inference in a multinomial distribution.
Present over there.
Vikas Sinha.
But anyway, this is the best that we can do. So I'm going to make a presentation on a topic which has been of interest to me for quite some time. This refers to exact inference in a multinomial distribution. This is in the name of Professor C.R. Rao, whose birth centenary was celebrated worldwide, is being celebrated worldwide for the last 3-4 months. This is my joint work with Professor Monisha Pal of Calcutta University Department of Statistics and Madam Papia Sultana of Department of Statistics, Rajshahi University, Bangladesh. The abstract says we have a 4-cell multinomial distribution specified by the 3 parameters P, Q, R. So the 4-cell probabilities are P square, Q square, R square, and the last one is 2 times PQ plus PR plus QR. So that the total is P plus Q plus R whole square, and the parameter space takes care of P plus Q plus R equal to 1, strictly between 0 to 1. Now the question is, there are 3 parameters PQR bounded by the linear relation. So if we are talking about unbiased estimation of these parameters, and if we can take care of 2 of them, the third will be automatically understood because of this linear relation. So essentially, we take the problem of unbiased estimation of P or Q or R one at a time. And question number 2, simultaneous unbiased estimation of P and Q and hence of R. So these 2 issues are separate, and there is a difficulty level attached to the second problem. The first one is well known. I would assume that the listeners, they are already familiar with the question of unbiased estimation of P when we have P squared in the model as one of the cell probabilities. But getting simultaneously estimates of both P and Q, that's a bit tricky. And we know that no finite sample size strategy will suffice for these unbiased estimation problems in the exact sense. So we are talking about unbiasedness in the exact sense. So I'll be dealing only with simultaneous estimation of P and Q. That is what is essentially mentioned in this page as well. So we are looking to the problem. So we go for a sequential sampling strategy. So we collapse the cells 3 and 4. These are the cells R square and 2 into PQ plus PR plus QR. These two things we club together, and that total we call theta 0, and P square we write theta 1, and Q square we write theta 2. So essentially we convert the 4-cell category into a 3-cell category, theta 1, theta 2, and theta 0. And our parameters of interest are P equal to square root of theta 1 and Q equal to square root of theta 2, while theta 1 plus theta 2 plus theta 0 is equal to 1. So we now proceed to define a 3-way sequential sampling strategy in order to unbiasedly estimate P and Q simultaneously. It says we continue sampling the units from the multinomial defined by the categories 0, 1, and 2. Let us recall 0 defines the category with probability theta 0, 1 is with theta 1, and 2 is with theta 2. So these are the 3 categories, and we continue sampling until all the categories are represented. That means until each category is represented at least once. So that is our sampling strategy, sequential sampling strategy. This amounts to stopping when the frequencies in the 3 categories are of the forms we have displayed it here. So there are 3 types of frequencies: frequency type 1, frequency type 2, frequency type 3, because we want every category to be represented. So these 3 types tell which one is the last category to show up. So frequency type 1 shows that category 1 is the last to show up, and before that, prior to that, we already have 2 and 0, K1 and R1 times both greater than or equal to 1. So they both have already shown up, and category 1 is the last to show up. That is the type of frequency 1. Frequency type 2, when category 2 is the last to show up, and frequency type 3, when category 0 is the last to show up. So this is my sequential sampling strategy. How do you continue sampling until every category is represented at least once, and these 3 are mutually exclusive and exhaustive, collectively exhaustive sampling strategies. Frequency type 1 amounts to observing 1 unit of category 1 at the end, after having observed units of the other 2 categories, at least one of each category. Likewise for the other 2 types. These are, as I said, these are mutually exclusive and collectively exhaustive sampling strategies. We can verify that in terms of getting into frequency type 1, the termination via frequency type 1, that is P1, P2, and P3, those have been displayed here. And further, one can verify easily that some as it should be. So these are collectively exhaustive and mutually exclusive frequency types 1, 2, and 3. So given a sample, which is a frequency count in one of these 3 types of frequencies, we have to find a method for estimation of P and Q unbiasedly. There are several remarks here. If we look at samples of type 1, which says that 1 is coming at the end, so before 1 we are getting 2 and 0. Let K be the frequency of 2 and R be the frequency of 0 before the type 1 before category 1 shows up. And or it could be 0 R2 K1. So I want to observing category 1 at the end. So what is interesting is that 1 is coming at the end, and before that we have both 2 and 0 showing up either way. Similarly, we have 2 at the end, or similarly we have 0 at the end. So this suggests observing which category you are observing at the end, that is described by this kind of description of the frequency counts in the three categories. Remark 2 says 2k 0r1 has to be interpreted as comprising of all possible combinations of k plus r units in the two categories 2 and 0, with frequency counts as specified by k and r. Likewise for the other two types. We have more remarks coming up. To unbiasedly estimate p, which is square root of theta 1, this is the representation that is used classically. Theta 1 times theta 1 to the power negative half, which is theta 1 times 1 minus theta 2 plus theta 0 whole to the power negative half. Now you go for infinite series expansion, the usual expansion of this thing, and it leads to summation j greater than equal to 0, a suffix j theta 2 plus theta 0 whole to the power j times theta 1, where a suffix j is this quantity. This is a standard representation for j equal to 0, 1, 2, etc. So the above expression suggests that there are probability expressions of 4 different types. Everywhere we have theta 1 as a common factor. So category 1 shows up in the very first draw. That probability is theta 1 because essentially we are sampling from theta 1, theta 2, theta 0 trinomial population. So category 1 shows up in the very first draw. That probability is theta 1, and this corresponds to j equal to 0. For j equal to 0, aj will be equal to 1 and the coefficient will be theta 1. That is exactly what is happening if we find category 1 showing up in the very first draw. Then successive units representing the categories 2, 1 or 0, 1. For j equal to 1, we are getting either 2 followed by 1 or 0 followed by 1. Similarly, for j equal to 2, we get 2, 2, 1 or 2, 0, 1 or 0, 2, 1 or 0, 0, 1. That is how the whole thing is going on. That is how we can see the role played by j. It is like waiting time. You wait until you get the category 1. That is represented by theta 1. And when you are waiting, you are getting all possible combinations of the categories 2 and 0. Classification of samples as per the description of the sequential sampling strategy. We have non-terminating sample. For j equal to 0, if the very first unit is category 1, then that corresponds to j equal to 0. That is a non-terminating sample because the sampling will terminate when all the categories have been represented, each one at least once with a frequency of at least once. So theta 1 coming up right in the very beginning, which corresponds to j equal to 0, that is a non-terminating sample. Similarly, for j equal to 1, we have 2 followed by 1 or 0 followed by 1. It is still non-terminating because to terminate, we have to have all the three categories represented. Look at j equal to 2. So there are 2 units before hitting the category 1. So those two could be 2, 0 followed by 1 or 0, 2 followed by 1 or 2, 2 followed by 1 or 0, 0 followed by 1. In case of 2, 0, 1 or 0, 2, 1, all the three have been represented. Therefore, it is a terminating sample. On the other hand, 2, 2, 1 or 0, 0, 1, they correspond to j equal to 2 because I am getting 1 at the third attempt, but still they are non-terminating because for 2, 2, 1, 0 has not shown up yet, and for 0, 0, 1, 2 has not shown up yet. So we have a classification of the samples corresponding to different values of j, 0, 1, 2, ... And the classification corresponds to whether the sample is a terminating sample or non-terminating sample. In our description of the estimate of P, we have to base it only on terminating samples. When the sample terminates, when sampling terminates, we have the entire sample, the entire body of data, so we propose an estimate of P. That is what we do normally. So in our description of P hat, we have to base it only on terminating samples. Note that in the expression for P, for each j greater than equal to 1, the extreme terms corresponding to 2j1 or 0j1 are non-terminating samples. For j equal to 3, before hitting the category 1, we have 3 observations prior to that. Those 3 could be combination of 2 and 0. It could be exclusively 2, 2, 2, 2 followed by 1, or 0, 0, 0 followed by 1. This is what I'm referring to here as non-terminating samples. Other than these 2 extremes, all other combinations of 2 and 0 for a total of 3, 2, 2, 0, 2, 0, 2, 0, 2, 2, 0, 0, 2, all kinds of combinations of 2 and 0, those are terminating samples. That is what is meant here. In the expression for P, for every j, the extreme terms corresponding to 2j1 and 0j1 are non-terminating samples, while all the rest are terminating samples belonging to frequency type 1, because 1 is showing up at the end. The non-terminating samples will denote henceforth by initial units with a semicolon ... because we still don't know what else is coming up, where the rest comprise of all possible descriptions until it terminates in one of the frequency types. So formation of p hat based on terminating samples. Here I am giving a description of p hat based on terminating samples. The whole idea is coming from the expansion that we have for p, which is square root of theta 1. This is the leading slide where we are showing what is p, how p has been expressed as a function of all these thetas. This is the basic idea. So for a sample of the type, we already mentioned that for j equal to 0, the unique number 1 is a non-terminating sample and a0 equal to 1. Now we are talking about sample of size 201 or 0 to 1. These are terminating samples. Sample size 3. We already have all the 3 showing here. So IS, that corresponds to A2. A2, if we expand, A2 is half. So the indicator of the sample is half. What does that mean? That means in case I get 201 or 021, I will terminate and I will use the indicator half, and I will develop a auxiliary randomization through use of a Bernoulli trial with success probability half, and I will execute it. If I get success, my indicator value will be 1. If I get failure, my indicator value will be 0. So my p hat will be 1 or 0 according as I get the result of success or failure by performing an auxiliary non-randomization, a Bernoulli trial, with success probability indicated by this indicator function IS. Similarly, if I'm talking about j equal to 3, then there are 3 prior to getting 1, and all these 6 descriptions here, 2 to 0 followed by 1, 2 0 2 followed by 1, etc. All the 6, they refer to terminating samples with j equal to 3. A 3 is 3 over 8. So the indicator for any of these samples is going to be 3 over 8. So I use the auxiliary randomization Bernoulli trial with success probability 3 over 8, and I act accordingly. If it is success, I say p hat equal to 1, otherwise I say p hat equal to 0. Like that, even in general terms, when there are k plus r observations before I hit to the category 1, and if both k and r are strictly positive, then I get aj for every sample S. Here 2k and o are refer to all possible 2 to the power j terms, excluding the 2 extremes, because the 2 extremes, 2 are 2j1 or 0j1, they correspond to non-terminating samples. So, but for those 2, for all others, we know we can use aj. Here is is the usual indicator function, as I mentioned, with the designated multiplier for every such sample S. And this refers to what is known in the literature as auxiliary non-randomization. So my sample starting with 1, indicator is 1. My sample of size 2, starting with 2 followed by 1, or starting with 0 followed by 1, it is j equal to 1 and aj equal to half. Therefore, my indicator is half for every sample of this type. Next, my indicator is 3 over 8 for every sample of the type 221, 001, 201, 021. So 2j1, that is what I was mentioning, a series of 2 followed by 1. That is an incomplete sample, non-terminating sample. That's why I use semicolon dot dot dot. Similarly, I have all zeros followed by 1. That is also an incomplete or non-terminating sample. But my indicator function is aj, depending on how many j's have shown up before. So I is the usual indicator function. It must be noted that the non-terminating samples of the type 2k1 or 0k1, they do terminate with probability 1, conditional on the first part. I have got a bunch of 2's followed by 1. If I continue, because I got 1 for the first time, I stop here to provide my estimator. But if I continue, then with probability 1, I'm going to stop somewhere. That is what it says. Every non-terminating sample will terminate with probability 1, conditional on the first part. The idea is to identify the nature of the complete sample by referring to the first part which has been observed and then assigning an indicator to it. That is exactly what we are doing. We are looking at the sample, whether it is terminating or non-terminating. We first hit the category 1 because we are primarily interested in estimation of P, which is square root of theta 1. We are developing the whole thing keeping theta 1 in mind, which corresponds to category 1. Therefore, my sampling I will stop the moment I get 1 for the first time. It may be a terminating sample or a non-terminating sample. And even if it is non-terminating, I know if I would have continued, then I would get it would terminate with probability 1. So the idea is I identify the nature of the complete sample just by referring to the first part, because first part helps me in providing an estimate of P based on whatever I have observed so far, that number K. That gives me a K and all that. Let's take up some example. For unbiased estimation of Q, we reverse the roles of the categories 1 and 2 in the multinomial setup. There is no need to change the category 0. So samples of the type 2 dot dot dot, 1 2 dot dot dot, 0 2 dot dot dot, etc. Even though these are non-terminating samples, now for estimation of Q, my emphasis is on category 2. Therefore, I stop the moment I get 2. And accordingly, I allow my estimator to be constructed depending on the value of j, the number of 1s and 0s preceding first appearance of category 2. So we can skip the details now. So now I take up some illustrative examples. So this one talks about the case when we are observing the units one by one through the trials. The first trial results in an observation from category 2. Next one again from category 2. Next, it comes from category 0, followed by 0, followed by 2, followed by a succession of 3 zeros. And finally, at the 9th trial, we get category 1 and we stop. Because our idea was to get hold of category 1 for the first time, so we stop here. And we find our head count, j equal to 8, and therefore my computation tells a sub 8 equal to 0.1964, and therefore for this particular sample, the Bernoulli trial will have the success probability 0.1964. We execute the trial and we find that it is a failure, and hence p hat equal to 0. Again, from the same sample, q hat equal to 1, because category 2 is observed in the very first unit in trial number 1. We can avoid such indicator-based estimates by repeating the exercise independently some n times and taking the average score. So this last part we explain with reference to estimation of P. So I'm talking about 20 repetitions of the trial. The serial number 1, the nature of sample, it is terminating, j equal to 12. That means after a series of observations up to 12 runs, covering both the two categories 2 and 0, at the 13th trial, we find the category 1. Therefore, it is a terminating sample. A sub j, A sub 12 is given by this math, and we perform a Bernoulli trial with success probability A sub j, and we end up naturally, it seems that we have ended up with a failure, so P hat is 0. The next observation coming from another independent sample is also terminating in nature, j equal to 15. So at the 16th trial, we got hold of the category number 1. This is my AJ. This again results in P hat equal to 0. There is a non-terminating sample, j equal to 0. That means right at the first attempt, we got the category number 1. Therefore, A sub 0 is equal to 1, and this time P hat equal to 1. So it goes on like that. We have got a bunch of terminating samples here. Only one is non-terminating in this first lot. And in the second lot, we have got 2 more non-terminating samples. But whatever be the case, we know the interpretation for J, computation of AJ, and carrying out the corresponding Bernoulli trial with success probability AJ and getting hold of the score 0 or 1. So eventually we find that there is 1, 2, 3, 4, 5, 6. There are 6 ones. Therefore, my average over all the 20, that leads to 6 over 20, which is 30%. Surprisingly, in this, it is quite surprising that in this particular simulation, we started with P equal to 0.3, Q equal to 0.5, and R equal to 0.2. So it is remarkably identical to the true value that was taken for carrying out this simulation. But anyway, that's accidental. Let me now talk about simultaneous unbiased estimation of P and Q. As I said before, in this particular illustrative example, that once I have P hat equal to 0, that comes out of the Bernoulli trial consideration. But in this example, Q hat equal to 1, because the very first trial resulted in the category number 2. That's why Q hat equal to 1. But for simultaneous estimation of P and Q, unbiased estimation, let us start with this remark, that unbiased estimates for P and Q are based on the indicator functions, which are basically AJ values, depending on the desired outputs. But this time we need 2 indicator functions, one referring to P and the other referring to Q, even though they are both based on AJ values. So for P hat, we identify appearance of category 1 for the first time in the sample. And while for Q hat, we identify appearance of category 2 for the first time in the sample. Note that these AJs, they form a, it's interesting to note, A0 equal to 1, A1 equal to half, A2 equal to 3 over 8, and so on. They are decreasing sequence, and not only that, any 2 of them together, AJ plus AK, is strictly less than 1. That's something very interesting to note. And that is what is being utilized quite profitably in this context. So for P hat, we identify appearance of the category 1. So that means there is a score J, which means the number of 2s and 0s preceding the appearance of category 1. And we use K for the number of appearances of 1 and 0 preceding the first time appearance of category 2. So we have got the notation J identified for category 1 and the notation K identified for category 2. Having done that, we find that we can compute AJ and AK from the given sample, and that AJ plus AK is strictly less than 1. Therefore, given a sample, whether it is terminating or non-terminating, we identify J for category 1 and K for category 2. Because this total is less than 1, we can perform a trinomial trial. Earlier we were doing Bernoulli in case of single parameter. Now because I have got 2 parameters P and Q, they have to be estimated simultaneously. We think of a trinomial trial with probability Aj, Ak, and 1 minus Aj minus Ak. Aj refers to category 1, Ak refers to category 2, and the last component refers to category 0. Therefore, if we perform a trinomial trial with these probabilities for any given sample, looking at category 1, I identify J and hence Aj, and looking at category 2, I identify K and hence compute Ak. So I have this trinomial trial with all the components known, Aj, Ak, and 1 minus Aj minus Ak. And therefore, I will end up with one of the three outputs, 1, 0, 0, 0, 1, 0, or 0, 0, 1, with an obvious interpretation. Now, if we consider and continue this exercise for a sample of size n, 20 or 30 or 40, averaging over such outputs would result in proper estimates avoiding the boundary value. If I look at single observation, it is 1 or 0 for every category. Therefore, these are the boundary values. These are not impressive. But if we take a sample of 20 or 30 observations together and take their average, then the resulting values will be proper estimates, as it happened in case of the earlier exercise that we took up here. Just for estimation of P, there are 20 observations. So the same exercise you could carry out for this particular data set by looking at P and Q simultaneously, and that would result in, for every sample, we would identify J and K and compute Aj, Ak, and 1 minus Aj minus Ak, and then perform the trinomial trial, end up with one of these three results, 1, 0, 0, 0, 1, 0, 0, 0, 1, with obvious interpretation, and then averaging over all those observations, all those sample outputs for a sample of size n, we would come up with P hat, Q hat, and hence R hat automatically by default in a proper way, and that would avoid the boundary values and we would get the estimates. So that last part, we are working on a small example now. I think that's it for the time being. Thanks for your patience and attention.
Thank you, Professor Sinha. Bapat is Professor Bapat. Yeah. Okay. Now it is unmute. Okay. Earlier it was muted.
No, now I want to. So are there any questions?
Maybe before any question comes, let me supplement. Yes. So towards the end, I talked about the joint estimation of P and Q and the simulation results. Now we have the results for 20 trials, for 100 trials, and for 1,000 trials. So with reference to 100 trials, again by taking P equal to 0.3, Q equal to 0.5, and R equal to 0.2, we find that P hat is around 0.3 and Q hat is around 0.55. So that is what we find in respect of the simulation carried out for 100 trials, and the standard errors are of the order of 0.08, 0.09, like that. So results are quite encouraging. That's the supplement that I wanted to mention.
Part of this work has it appeared somewhere, or you are going to? Has some part appeared? Okay. Okay, so I think we'll move on to the next talk by Professor C.L.S. Kakasara. First, that we may proceed to discuss. Yeah.
A great pleasure to participate in this conference arranged by Professor Manjunath Prasad to celebrate Professor Rao, C.R. Rao's birth centenary. And And especially Professor Rao has contributed not just for statistics, but even for matrix theory. And I have done a bit of work. My special interest is in inference for stochastic processes. But however, I have done a bit of matrix theory connected with Professor Rao's results. So I thought I'll present them to you today. But since the time allotted to me is only about 25 minutes, it's not possible to go into the proofs of these results. So I will just highlight. So I'm going to talk about some matrix versions of covariance, homog mean, and other inequalities, which are connected with my work as well as Professor C.R. Rao's. So I would like to dedicate my talk to Professor Rao during his birth centenary year. And I'll take a little bit about a couple of minutes, maybe about his life story, a little bit. Professor C.R. Rao was born on September 10, 1920 in Hadagalli, in the current state of Karnataka, India. He grew up with 6 brothers and 4 sisters in a comfortable family environment created by his mother, A. Lakshmi Kantamma, and father, C.D. Naidu. Today, he is a living legend whose work has influenced not just statistics, but has had far-reaching implications for fields as varied as economics, genetics, anthropology, geology, national planning, demography, biometry, and medicine. We are celebrating Professor Rao's birth centenary, and I would like to present this lecture in appreciation and celebration of his great contributions to the subject of statistics and to science in general. I have written an article entitled C.R. Rao, A Life in Statistics, for the series Living Legends in Indian Science in the journal Current Science in the year 2014, but I will not be presenting them here. I was a student of Professor C.R. Rao in my master's program at the Indian Statistical Institute, Calcutta, during the years 60 to 62, and later his colleague at the Indian Statistical Institute, New Delhi, during the years 1976 to 79, before he left for USA. It's a great pleasure for me to dedicate this work to my teacher, Professor C.R. Rao, during his birth centenary year. Our focus today is on some of his research works in matrix algebra and their applications to statistics. C.R. Rao has extensively used matrix algebra in his study of unified theory of linear models. He has shown that some of the important results in matrix algebra can be derived from statistical results. Rao derived seven inequalities in statistical estimation theory, one of which deals with the harmonic mean of positive random variables. I was able to generalize this result to matrix theories in the year 2000, and Rao gave also an alternate proof of this result using again ideas from statistics. And coming back to my own contributions, Kimmeldorf and Sampson published a paper in Journal of American Statistical Association. They derived a class of covariance inequalities. Now, I have been able to derive the matrix versions of these inequalities in the year 1990, and they were published in a volume which was released in honor of Professor C.G. Khatri, who was an expert himself in matrix algebra. We will now review some of these results dealing with the harmonic mean for positive random variables and some covariance inequalities. And it so happens that Professor Jubilisco and Hansen have derived recently, generalizing my results as well as Professor C.R. Rao's results in a very big fashion. I will just talk about a little bit about them. So the covariance inequalities, let's start with that. So suppose script A is an open convex subset of R2, and xy is a bivariate random vector with support A. So further, we'll assume hereafter they all have components x and y have second moments. And suppose you consider any function gxy for which second moment or variance exists. Let us take that. And suppose gxy satisfies this inequality which I have presented, x2 minus x1 times y2 minus y1 is less than or equal to gx2 y2 minus gx1 y1 square. Then Kimmeldorf-Sampson proved that any function g which satisfies those conditions will lead to the inequality covariance xy is less than or equal to variance of gxy. So this is what I mean by covariance inequality. So by choosing different functions g of this satisfying this condition, we can get a class of inequalities. A matrix version of this result was proved by me in 1990. So the result is the following. Suppose psi and a are two random matrices. Now here they are not random vectors or random variables, but random matrices. Suppose you have two random matrices of order R by S. And further, suppose that all the entries of these matrices have finite second moments. So let's say expectation by the matrix of expectations. So when you say expectation of a matrix, you mean matrix of the expectations of the entries. And let's say prime denotes the transpose of the matrix psi. So the result, so the covariance is done in natural way. Of course, matrices don't necessarily commute. So you cannot use the usual standard definition of covariance of random variables. So you use this, which I have denoted at the bottom. Covariance psi eta is by this. You have to make it symmetrized. So that's why you have to have psi minus expectation psi eta times expectation of eta transpose, and the next term take the average. And variance, of course, is the standard notation. So you can use these things and then develop matrix covariance of matrices. And then it turns out that if this so-called matrices commute, if the random matrix commute, then it reduces to the standard definition. That's what I have presented in this transparency here. So it reduces to the standard definition if they commute. If they don't commute, then you have to symmetrize, and that's why the earlier definition was there. So using this theorem, the theorem 1, which I have noted here, of course, the standard notation we write for a matrices, A less than or equal to B, of course, square matrices. If A is less than or equal to B, if B minus A is non-negative definite, and A is strictly less than B, if B minus A is positive definite. This is the standard notation for matrices. And the theorem 1, which I have stated, so if you have two random matrices for which the support is in a set A, and if you take any function G, which is defined on those space of matrices, products of matrices, then you can see that covariance psi eta is less than or equal to variance G psi eta, if and only if that condition on the matrices, which I have written at the bottom of the slide, if that holds. Of course, it looks very complicated, but for some special functions G, this condition can be verified, and then you get interesting results. Now let's look at some examples. Suppose I take the function G a b equal to a plus b by 2. So it's a very simple example, a function, and you can very easily check that condition which I stated in theorem 1 holds, and that result to a very interesting inequality for matrices. Covariance psi eta is always less than or equal to variance of psi plus eta by 2. Notice that this inequality is in terms of, that means the variance minus covariance is non-negative definite. It's a inequality on matrices. So similarly, suppose I and eta are positive definite random matrices of order R by R. Then of course, and suppose you have A and B are symmetric matrices, and then you define GAB, and suppose they commute. Suppose A and B are matrices, if they commute, and GAB you define in the fashion A power half, B for half, then you get another application of this result. Then there is another inequality which comes up, which is a consequence of Cauchy-Schwarz inequality for matrices. Not many people know about Cauchy-Schwarz inequality for matrices, but for those who are interested, it is given in the book by Ibrahimov Kasiminski in 1981. And this is the result, which is at the bottom of the page. Here you can see that expectation of psi and pros greater than or equal to psi eta transpose, expression of eta transpose inverse, expectation of eta psi transpose, of course, assuming that mean is 0 and of eta and E, and then this is strictly positive definite. And a third example which comes up again for this, if you have any positive definite matrices, D plus D inverse is greater than or equal to 2i. This is easy to check for the matrices, and in fact it's a consequence of this elementary result. D half minus D to the power minus half square is non-negative. Non-negative means, as I said, non-negative definite. In particular, for near to positive definite matrices, using this result, you can show this condition, and as a consequence, you can derive following result. Suppose you choose the function G to be A times B, then you can show that applying the inequality, you can show that theorem 1 holds for this function. So in particular, if you take A equal to psi and B equal to psi inverse, you get covariance psi inverse is very less than or equal to variance of G of psi inverse. But psi inverse is identity matrix. So that's, the G psi inverse is psi times psi inverse, that is variance of identity matrix, which is 0. So because identity is a constant matrix, so variance is 0. This in turn implies expectation of psi times expectation of psi inverse is greater than or equal to I for any positive definite random matrix. So it's a very interesting result. So of course, everybody knows psi inverse is the identity, but expectation of psi, remember psi is a random matrix. So expectation of psi and expectation of psi inverse is greater than or equal to I. So this was proved earlier by Browski and so on. And there are other results. Suppose we define a positive definite matrix A and B. This is a symmetric average. This is something analog of arithmetic mean. Then A hash B by this formula and A exclamation B by this formula. So then it's known. Ando is a specialist in matrix theory. He proved this inequality. A exclamation mark is less than or equal to A hash B, less than or equal to A triangle B. Generalizing this, generalized arithmetic mean, geometric mean, and harmonic mean inequality for positive real numbers. This is a corresponding inequality for matrices. So Ando proved from his matrix theory results a nice result like this: A triangle B is greater than or equal to half of A to the power Q plus B to the power Q to the power 1 by Q. And of course, he has ways of defining the qth root and qth power and all that. Under the commutative assumption, it can be checked, they're all equal. This A hash B is equal to AB to the power half, and it's equal to A to the power of B to the power half. So it was shown earlier by theorem 1 that it works for arithmetic mean and also for this function under the commutative condition. But it does not hold for A exclamation B. And this result is also known even for real valued random variables, it doesn't hold. And but the theorem holds for functions of this type, which I will not go into because lack of time now. So this is an open problem for all matrix theory specialists to find out whether the theorem 1 holds for functions of this type and also for the function A transpose B. So people, whether it holds or not. Now there is called harmonic mean inequalities. Rao 1996 proved the following result. If x and y are positive valued random variables with finite expectations, then expectation of 1 by, so this power minus 1 is here. So 1 by x plus 1 by y is less than or equal to 1 by expectation of x plus 1 by expectation of y. And this is a result for harmonic mean. So it's I know harmonic mean is familiar with those. So Rao's proof involves the use of Holder's inequality and the dominated convergence theorem. So he first discusses for a discrete case and extends the results to the dominated convergence theorem for the functions of random variables. Now this result was extended by me to matrices in 2000 in a journal called Students Magazine, which was published from Netherlands. And the result is following: if A and B are almost surely positive definite random matrices with these expectations finite, as I told you, expectation of a matrix means matrix of expectations. Expectation of inverse means you take the inverse first and take the expectation of those entries. That's what it means. And suppose these matrices are there and this difference is non-singular, then expectation of 1 by A plus 1 by B is less than 1 by expectation of S plus 1 by expectation of B, and there is an inverse again. So this is a matrix for harmonic mean inequalities. And this result actually can be proved by 3 or 4 methods, and my paper contains the proofs of these results. So one method uses what's called Jensen's inequality for matrices. So all of us are familiar with Jensen's inequality for random variables. And here, this is a Jensen's inequality for matrices. But for matrices, first of all, a notion of convexity for matrices has to be studied, because people know about convexity for functions, and we also know about concavity and convexity for functions. But here is a convexity for functions defined on the space of matrices. And this convexity was defined by Davis in a paper in 1963. The references are all in my paper if somebody is interested. So for any fixed positive definite matrix M, the matrix valued function Gx is equal to 1 by M plus 1 by X. We can show that this function is concave in X or the class of positive definite matrices. So if you can define convexity, concavity is a consequence of a similar thing. People know about that. And hence you get this inequality. Expectation of 1 by M plus 1 by X is less than 1 by M plus 1 by X. And now you take expectations again, takes with respect to the probability measure of the random matrix M. On both sides, the result follows. Here, these are essentially something like conditional expectations given M, which I have not written here. So this is given M, you have this result, and then take overall expectation, then you get the result. And there are several other proofs which are I have listed in my paper also. So one is, for instance, interesting example is for any two positive definite matrices, G inverse minus H inverse is greater than or equal to H inverse times H minus G times H inverse. And this is a consequence of the fact this non-negativity holds. There is another result. If G is a positive definite matrix such that it is finite and non-singular, then you can get this interesting result. This I have already discussed a few minutes back. It's like expectation of psi inverse is greater than or equal to expectation of psi inverse. This follows as a consequence of theorem 1, which I have done that, and I have it displayed today. And the third inequality using this HND or positive definite random matrices, finite expectations, then you have this inequality. Again, this is a fact that's is a consequence of the fact that the function A, B inverse A is a convex function over the class of positive definite matrices. And the detailed proofs are given in my paper. As I said, my time is short. I cannot go into the details of these proofs. Now, this is the recent contribution, that's 2017. These are called the general mean inequalities. This is the work by Gibilisco and Hansen. And they refer to my paper as well as Professor C.R. Rao's paper. So I thought it's interesting to present their results in this conference along with our results. And that's what I plan to do. Now, this definition of general mean is very interesting. It subsumes all these other means which are in literature until now. So, for instance, suppose you take two positive real numbers. You have the arithmetic mean, which is x plus y by 2. The geometric mean, which is xy to the power 1/2. The harmonic mean is 2 by 1 by x plus 1 by y. And the logarithmic mean, which is x minus y by log x minus log y. So these are four types of means which we construct. And Gibilisco generalized all these, Gibilisco and Hansen, they have generalized all these results to what are called bivariate means, which I will explain in a minute. And all of these others have been special cases of that. And as I said, the results are known of arithmetic mean. We all know the inequalities of arithmetic mean, geometric mean, and harmonic mean. Now there is a course called logarithmic mean. So I have given the example here. Suppose if you have positive random variables, so linearity of expectation operator implies expectation of MAXY is MA of expectation of XY. Essentially what it means is expectation of X plus Y by 2 is expectation of X plus expectation of Y by 2. So the operator here is the average operator. Now there is a Cauchy-Schwarz inequality, gives you this so-called geometric mean. Expectation of MGXY is MG of expectation of X, expectation of Y. Okay, so this is again a standard result. Cauchy-Schwarz inequality gives you this. Then Rao in 1996 with an additional proof in 2000 and myself in 2000, we proved that expectation of harmonic mean of X and Y is harmonic mean of expectation of X, expectation of Y, which I have discussed earlier. So Gibilisco and Hansen investigated the generality of this result, including the question whether such a result holds for logarithmic gain. Now I'll just give a brief information on that. So a bivariate mean, which generalizes all the others, are given by a function satisfying these various conditions. It's if you x and x, if you take it gets x, the function is symmetric. And if you took x and y and take the mean, it lies between x and y. If x and y, x is less than x, y is less than y, then mean of xy is less than mean of x prime y. and the function is continuous and is positive and homogeneous, there is m of t x t y is t of mxy. And you can check that all these are hold for arithmetic mean, geometric mean, harmonic mean, and logarithmic mean. So this definition of bivariate mean is due to Petz and Temesi in 2005. And suppose you call this class of bivariate means as script m. So now you define a class of functions which satisfy the following conditions: is continuous function, monotone increasing, at 1 is equal to 1, and t of ft inverse is ft for t positive. So let's consider the class of such functions, but we'll show you some examples later. And now introduce the mean. Mean of x and y is bivariate mean is called f of y times, so if you have x and y, it is y times f of y inverse x. And you introduce a function fmt is m of 1t for positive numbers x, y, t. Now there are examples. For instance, if you choose f function as 1 plus x by 2, you get the bivariate mean is arithmetic mean. If you take root x, it becomes geometric mean. If you take 2x by x plus 1, it becomes harmonic mean. If you take x minus 1 by log x, it becomes logarithmic mean. And there's one more which we can construct. All the functions described above given to the class f are their concave functions, and Gimelisko and Hansen proved the following result, generalizing my work and Professor C.R. Rao's work. And that's this result. Suppose f is a function in the class f, the inequality expectation of mfxy holds mf of expectation of x, expectation of y for arbitrary positive random variables if and only if f is concave. And this generalizes our results. In particular, the result holds for logarithmic mean for positive random variables. And in fact, Gimelisko and Hansen extended this result for what are called operator means in the sense of Kubo and Ando. So these are Ando's paper has appeared in the linear algebra applications on concavity. And then, of course, you can see that the second paper, Ando's paper, 1983, and the arithmetic, geometric mean, harmonic mean for positive definite matrices. So the result on arithmetic, geometric, harmonic mean is known for real numbers for the last 60, 70 years. But he has applied for positive definite matrices. Now, of course, Bobrovsky and Zakai, and they have done some results. Then this is the result paper I was telling, Davis paper, who extended the notion of generalizing the notion of convexity for functions of matrices. And this is the recent result of Gimelisko and Hansen, an inequality for expectations of means of positive random variables, which appeared in Annals of Functional Analysis in Italy. And then, of course, my paper, my result is generalized Kimmeldorf and Sampson. And then this is Kubo and Ando's result, which is I have explained. And this is the result which I have done on matrix version of covariance inequality. This is Gujarat Statistical Review, which is in honor of Professor Khatri, who has worked with extensively with Professor Rao on linear models and matrix theory and all that. So they're both experts in their work. Khatri is an expert in matrix theory, and Professor Rao has done extensively in matrix theory, and his work in generalized inverses is very well known. And I have done this. I've contributed inequality for random matrices with application to statistical inference. It was published in a magazine called Student way back in 2000. And Professor Rao has written these 7 inequalities in statistical estimation theory. So these are all inequalities which are known, but his idea is to derive them through the concepts of statistics. And then, in fact, he's a more extensive paper and statistical proofs of some matrix inequalities. Well, thank you very much, and this concludes my lecture. Thank you. May I say something?
Yeah, please.
Hello?
Can you hear me? Yeah, please.
Yes, please.
Can I say something?
Yes, yes.
Yeah, sure.
Yeah, you see, I think now I know the problem with recorded talks, because there was no synchronization between my lecture and then transparencies. They moved much faster than my talk. But anyway, it gives a basic ideas of what I wanted to present. Thank you.
ಕೇಳು ಮಾಡಿ
Thanks for the feedback.
ಕೈ ಬರ ಮಾಡಿ
ಕೈಗೆ ಬರಲಿ
ಏನು ಕಾಣ್ತಿರ್ಲಿಲ್ಲ.
ಕೈ ಬರல நீங்களே கேட்கலாம் அப்படி அது வருது இதோ வருது
Any questions?
இதோ வருது
Odu,
நீங்க
yes.
Please ask.
Is there any connection between your versions of matrix inequalities and many similar matrix inequalities proved by Rajendra Bhatia?
Well, the only thing I know is this paper by Jibilsko and Hansen. They have unified all matrix, all sorts of means of inequalities. So that includes arithmetic mean, geometric mean, harmonic mean, and all that, including Ando's results. So whether it includes Bhatia's results or not, I have no idea.
They have matrix versions of mean value theorem, second mean value theorem, and Lagrange remainder, and so on. They are all functions of matrices, but scalar valued functions of matrices, and for them they are trying some kind of Taylor expansions, and in that context Bhatia has several interesting inequalities.
Probably it might be possible to extend those results to these ideas of Gibilsko and Hansen, generalizing all those inequalities to this. And then he has also inequalities and operator means and so on. So probably some of these might extend to that. So it's open field now for general work based on their work.
Thank you. Thank you.
Thank you. Thank you.
Try to extend to n tuples. Then I think you get some of the difficult. I know that the geometric mean of tuple is a difficult problem. Arithmetic mean and harmonic mean. I don't know if you have tried some results for n tuple other than single. I think you have to unmute.
I am not able to hear you.
சொல்ல
I am unmuted.
அவன் சொன்னா I'm not able to hear you.
I have unmuted. Can you hear me now?
No, he's not able to hear.
Not very clear.
Okay, I don't know what is the problem because
அவனுக்கு காது கேட்கல பாப்பர் சொல்றது அவனுக்கு கேட்கல அவன் சொல்றது அவனுக்கு கேட்கல.
is it clear now?
Yeah.
And
Yes.
Professor Prakash Rao, you have to unmute.
Professor Prakash Rao, you will have to unmute your system. Please unmute. It is muted.
Now?
Yes.
No, Professor. Now it is unmute. Fine.
Okay.
So I had just one remark that whatever you have presented, if you, I think for n tuples of matrices, if you try to extend, then there are many, but the geometric mean is a difficult problem. That as far as I know, but I think some of the results will go over for n tuples. That's what I wanted to remark.
I would be interested in seeing that. Yes. Thank you.
Okay, so I think the time is running out. We will. I want to thank all the speakers and all. Of course, there was some problem in the synchronization, but other than that, it went well, I think. But hopefully, it will be taken care of next time. Okay, so I want to thank all the speakers and conclude this session now. Thank you very much.
Yeah, we invite them for evening presentation function.
Okay.
Well,
yeah.
Yeah, Professor Rao, Sinha, and Parthasarthi, please join us in the evening during the presentation function.
We will.
You can join us greeting Professor Rao.
Okay. Thank you.
Okay,
Thank you. section. Where are you? You may take care.
Thank you, Professor R.B. Bapat, for chairing the session. Now we have another invited talk session. The speakers of this session are Professor Jeffrey Hunter and Professor Stephen Hazlett. The first speaker, Professor Jeffrey Hunter, is an Emeritus Professor, Auckland University of Technology, Auckland, New Zealand. He will be speaking on the impact of Professor Rao's research used in solving problems in applied probability. He is one of the mathematicians closely associated with Professor C.R. Rao. He applied the results of Professor C.R. Rao to the field of applied probability. He was even invited by Professor Rao as a keynote speaker in a two-day workshop. It is our pleasure to have you with us, sir. A second speaker is Professor Stephen Hazlett. He is a former professor and director of the Statistical Consulting Unit, Massey University, New Zealand. His presentation will be on the topic on treating random effects in linear models as fixed and testing whether they are zero. His association with Rao is through the conferences that he attended. We are pleased to invite you, sir. I now request Professor B.K. Sinha, ISI Kolkata, to chair the session. Over to you, sir.
Thank you. So as has been announced, we have two eminent speakers for this invited session. Let me call upon Professor Hunter to make his presentation. He will have about 25 minutes and then 5 minutes for discussion. Okay. Professor Hunter.
Well, thank you very much for the invitation to speak. I'm delighted to be present at this meeting this way, and I think the best thing is to start the presentation now, please. It's my pleasure to be able to present this talk on the impact of Professor Rao's research used in solving problems in applied probability. The outline of the talk is basically four small sections. Firstly, we're going to look about the research that Professor Rao did on matrix inverses, generalized matrix inverses. Then I'm going to explain how I became exposed to his research. And then a section when I present a variety of results that I've used based on his results. And in the final section, I'll talk a little bit about the formal links that I have with Professor Rao. There were three key publications that set the scene for Professor Rao's work on generalized matrix inverses. A paper in 1955 in Sankhya, a paper in 1962 in the Journal of the Royal Statistical Society, and his book on linear statistical inference in 1965. There are two other related publications which I've also consulted. His 1966 work in the Festschrift for Professor Jerzy Neyman, and in 1967, a general theory paper in Sankhya on the calculus of generalized inverses of matrices. His paper in 1955 had the concept of a pseudo-inverse, and this appeared in an appendix to his paper when he was looking at the computational aspects of the general theory of least squares. He was looking at solving the normal equations and showed that he could play around with those equations and get an expression that behaved as the inverse of the matrix A that he wanted to effectively invert. In 1962, he was a bit more general and gave a set of conditions so that if ax equals y is a consistent set of linear equations, then x equal to a minus y would be a solution where a was defined as the generalized inverse, or what we'll call a G inverse. And then he showed that if a minus is a G inverse, a minus a equals a, and conversely. And it then found a general solution to those set of linear equations, introducing an arbitrary vector z or z to the last expression there. He also looked at some computational aspects using the sweep out process in solving for generalized inverses. His 1965 paper was a bit more general in that he introduced the four-conditioned Moore-Penrose inverse, A+, and he distinguished that from a one-conditioned G inverse A- by showing that A+ had to satisfy the four conditions that I've labeled there, the well-known four conditions of the Moore-Penrose G inverse. And he showed that such an inverse exists and is unique. After he published his book, he actually had in the paper for Professor Neyman necessary and sufficient conditions for a set of equations AX equal Y to be consistent, namely that A minus Y would be Y, where A minus was any G inverse. And then went on to show that necessary and sufficient conditions for a much more general equation, AXB equals C, to have a solution was the consistency condition, A minus C, B minus B equal to C, and then gave a general solution, this time involving an arbitrary matrix, Z. And in his paper in 1967, he provided a representation of all generalized inverses from any one. Given a single generalized inverse A minus, then he showed that A minus plus U plus A minus A, U, A minus, where A was a particular G inverse and U was an arbitrary matrix, gave all the G inverses for a matrix A. Then he looked at some necessary and sufficient conditions for a minimum norm solution, and these were effectively the 1-4 conditions for the Moore-Penrose G inverse. And the least square solution of the consistent equation AX equals Y effectively required the G inverse to be an A13, or the first and third conditions of the Moore-Penrose generalized inverses. So I was exposed to his research when I was studying for my PhD in 1965 at the University of North Carolina in Chapel Hill. And I was taking a graduate course on the analysis of variance with applications to experimental design. This course was taught by Professor Indra Chakravarti using notes prepared by Raj Chandra Bose. And the term conditional inverse was introduced in this course. And here's just some extracts from Professor Bose's notes, showing that when A was square and non-singular, this conditional inverse was -1 solution of linear equations. So here's some comments about this. How did Professor Bose and Professor Chakravarti come to know about this work? Well, Professor Bose was from the University of Calcutta, and in 1940, Rao was in the first group of students that he taught. He then became the head of the department at Calcutta and later joined Chapel Hill, UNC, in 1949. Professor Chakravarti did his PhD under the supervision of Professor Rao at ISI in Calcutta in 1958, and he joined Chapel Hill, the University of North Carolina, Chapel Hill in 1964. The three of them, Professor Bose, Professor Chakravarti, and Professor Rao, all edited a monograph published by the University of North Carolina Press in 1969. Now, I was not going to do any research in the general area of statistics, but I was going to do research in applied probability. And here was an opportunity in my coursework to be exposed to various different areas of statistics before deciding on my actual research topic. I had the opportunity to take courses from a number of leading figures in their fields at the time: Professor Norman Johnson, known as Johnson and Cox fame, Professor Vasily Höfting, Professor Walter Smith, whose work in renewal theory, and I actually worked with Professor Smith, he's my supervisor, and Professor Ross Ledbetter, who is quite well known as well. After I finished my PhD, I was engaged in some research in Markov renewal theory and Markov chains. My PhD thesis had been on semi-Markov processes, not directly involving Markov renewal processes, those semi-Markov processes are embedded within such processes. But the first key paper was in 1969 on moments of Markov renewal processes. And that started me going on my work in generalized inverses. In 1982, a paper in linear algebra, a survey article on generalized inverses and their application to applied probability problems. 1988, characterizations of generalized inverses, and then extending that in 1990 to parametric forms. And I'll talk briefly about these 4 papers. The 69 paper was the first one to identify that Kemeny and Snell's fundamental matrix of Markov chains, which appears in Kemeny and Snell's book in 1950, the Z matrix. I showed that that is a one-condition G inverse of I minus P. Now, this is more general than Markov chains. We're actually looking now at Markov renewal processes. Then the matrix of mean first passage times in such a process, I could find an expression using that generalized inverse Z, and also an expression for the matrix of renewal counts, MT, also involving Z. I'm not going to talk about the other terms there, other than the fact to show that I solved systems of linear equations to get a result using a particular generalized inverse. 1982, in this general survey paper, I showed that if I've got a finite irreducible Markov chain with a transition matrix P, stationary probability vector pi transposed, then if U and T are arbitrary vectors such that U transposed E, that's a vector of ones, that says the sum of all the elements of the vector U are non-zero, and pi transpose T is non-zero, then I minus P plus T U transposed is non-singular, and that inverse of that matrix is a G inverse of I minus P. And then I showed any G inverse of I minus P has that general form involving an arbitrary vector F and another arbitrary vector G, that general form. I used that extensively in some general procedures for finding stationary distributions, moments of first passage times, asymptotic forms for the moments of occupation, random variables. In particular, I had this general expression by computing a matrix A as I minus P times a generalized inverse G to give an expression for the stationary probability vector, and an expression for the mean first passage time matrix using any generalized inverse, and analogous to the renewal counts, in this case, the expected number of times state J is visited from state I in N trials in a Markov chain has got that expression. I also extended this to Markov renewal processes and Markov chains in continuous time. I then went on to characterize generalized inverses associated with Markovian kernels in terms of the 4 conditions that Rao introduced regarding the Moore-Penrose generalized inverse, and also an additional 5th condition for square matrices requiring AX equal to XA. And then I gave a whole range of characterizations for the 1, 2, the 1, 3, the 1, 4, the 1, 5, any arbitrary collection of those generalized inverses, all including the condition 1, the main condition for a one-condition generalized inverse. I showed that the group inverse had a nice simple expression in terms of any G inverse, and the Moore-Penrose inverse one could compute. This is the Moore-Penrose of the Markovian kernel I minus P. In the follow-up paper in same paper, 1988, I showed that you can express one generalized inverse, this I minus P plus T2 U transposed inverse, in terms of any other generalized inverse where some pre and post multiplying terms are specified and an arbitrary constant involving the limit matrix, which is E times pi transpose. And then showed a nice little subsidiary result that this particular matrix, A delta, doesn't depend on delta. The final paper in those 4 papers was the parametric form, and that was, if you give me any generalized inverse G of I minus P, we can always find parameters A, alpha, beta, and gamma such that G can be expressed as this inverse of I minus P plus alpha, beta transposed plus a gamma times E pi transposed. Now recall, alpha is a column vector, beta transpose is a row vector, so that of course is a matrix in there. And then I showed that the alpha and the beta and the gamma can be expressed in terms of the matrix A, the matrix B I've given there, and also the generalized inverse G. And I've got some other relationships, but the nice thing that came out of this was the A12 generalized inverse, satisfying conditions 1 and 2 for the more Penrose conditions. The gamma has to be -1. And for A13, alpha has to have a particular form, A1 form, beta has to have a particular form, and A15, which is a unique matrix for Markov chains because I minus P is a square matrix, the alpha is E and the beta is pi. I've summarized and elaborated more on this early material by including it in some books of mine in 1983. It's a typo there, it's not 1883, it's 1983. Mathematical Techniques of Applied Probability, Volume 1 and Volume 2. Volume 1 has now been republished as an ebook by Elsevier. And then I've got 15 other papers here that I've listed where I've used generalized matrix inverses and extended the results to a number of different applied probability areas. I'm not going to go into all of those papers. There's some more papers here and some further additional ones. So you can see that I've used generalized inverses quite extensively in my research, but I'm going to highlight some key results in some of these papers. In 1992, a way of taking any generalized inverse G and finding expressions for the stationary probabilities pi j and computing the mean first passage times mij in terms of the elements of G and the elements of a matrix A, which is I minus P times G. And there's a simple computational process which is easily done using, for example, MATLAB. Then I got into some work on perturbations of Markov chains, where I take the transition matrix P and make a small change to it to create a matrix P tilde, and then you get the difference between the two stationary probability vectors in terms of a matrix H, which is involving any generalized inverse of I minus P. And furthermore, some expressions involving some terms involving the mean first passage times in a matrix N for any general perturbation E. I then went on to look furthermore into this, because trying to work out what the significance, if I go back a slide, go back to this matrix N, the significance of the elements in this matrix N. And it turned out that if I look at the sum j equals 1 to m of mij times pi j, that's sometimes now called the mixing time or the time to stationarity. And in a finite irreducible Markov chain, that's independent of the initial state. All those expressions for each value of I is constant, and it's now known as Kemeny constant. And then I showed that I take any generalized inverse of I minus P, I can get an expression for eta, or Kemeny constant, in terms of the trace of that generalized inverse. I also showed that for any irreducible Markov, M-state Markov chain, that the Kemeny constant was always greater or equal to m plus 1 on 2. And then an application to perturbations of Markov chains, I was able to get bounds on the difference between the two stationary probability vectors in terms of Kemeny constant. In 2007, a paper in Asia Pacific Journal Operations Research, I have a variety of expressions using different generalized inverses for finding mean first passage times in the stationary distributions. Here is just a simple result, a simple addition of the matrix where adding on a matrix EB transpose. EB transposed is a vector with zeros everywhere but one in the bth position. And I just show that one can get simple expressions for the stationary probabilities and the mean first passage times. Then extended some work in 2008 to look at the variance of first passage times and some applications to mixing times and Markov chains. Showed that the second moment of the first passage time distribution can be expressed in terms of any generalized inverse G, and the M, the mean first passage time matrix, and got a vector for the variance of the mixing times. And this matrix, this mixing matrix that you end up with was what we had before for that matrix N. Looked at some works in Markov chain properties in terms of the column sums of a transition matrix, and defined a new inverse G inverse H involving just a vector of ones and a vector of the row vector of the column sums of the transition matrix, and showed that you can express the the stationary distributions as a linear combination of the Hij, and some relationships within the mean first passage times. And once again, Kemeny's constant appears in terms of this matrix H. And the final results I'm going to talk about here are generalized inverses of the Markovian kernel I minus P in terms of properties of the Markov chain. Suppose you're given any generalized inverse of I minus P, then you can find the parameters, the alpha, the beta, and the gamma that we had before. And I can show that the elements of that generalized inverse can all be expressed in terms of the parameters, the mean first passage times, and the stationary probabilities. So that's I then look a lot of applications of these results. And further, if K is Kemeny's constant, I get an expression in terms of the delta J from this expression for delta up here, some of the beta parameter time the mean first passage times in Kj. Now, I've had some opportunities to meet personally with Professor Rao. I was involved in inviting him to New Zealand in 2005. He was the keynote speaker at the International Workshop of Matrices and Statistics held at Massey University in the Albany campus, and I was chair of the local organizing committee. We had organized for him a workshop at the University of Waikato, organized by Professor Naijon. He was the Nokia lecture at IWMS, and that was organized through Simo Puntinen. I had him arranged to be a distinguished visitor to Massey University and also a visiting lecturer for the New Zealand Statistical Association. We worked him hard. He had an extensive program. He visited every university in New Zealand, gave public lectures, and spoke at our workshop, as well as this data scrutiny and data mining workshop at Waikato, Ruakura. And here's an advertising blurb for the International Workshop of Matrices and Statistics, where he was figured as a keynote speaker. And here's a photograph of him with Mrs. Rao and members of the organizing committee, Professor George Stein, Professor Joachim Werner, and another invited speaker at the conference, Professor Shale Searle from Cornell, who's now deceased. Professor Searle was a New Zealander. And here is a group meeting, a photo of the group. I can see Simo Puntanen in the middle, in the third row back. Professor Rao, of course, in the front row. Professor Stein in the back row. And there'll be some others probably well known to some of you. I had an opportunity for him to sign my copy of his book on the linear statistical inferences applications, a nice little footnote to his visit. And then he invited me to go and be a keynote speaker at a 2-day workshop at Penn State University, University Park, where he was based. And there were 4 speakers at that meeting, Professor Jean Golub, Professor Tom Kalias, myself, and M.B. Rao from the University of Cincinnati. And it was a workshop schedule. He had me giving 2 talks. He only, Tom Kalias gave a couple, and so did Jean Golub. And C.R. Rao gave his talk on anti-eigenvalues and anti-singular values that he talked on in the conference in New Zealand the year before. And so here was a photo of the 5 of us, Professor Jean Golub, myself, Professor Rao, Professor Tom Kalias, and M.B. Rao. And then Professor Rao invited me and my wife to visit him in his home at Penn State, University Park, and a photo taken in his residence. So some final comments. As an undergraduate in mathematics at the University of Auckland, I was exposed to some of his pioneering classical results, in particular the Cremair-Rao lower bound. And I had the opportunity to meet Professor Cremair, and he wrote a book with Professor Ledbetter. So there's connections that I had there with through that Cremair-Rao bound. While the significance of Professor Rao's contributions to a number of statistical fields is well known, I'm proud to have been able to apply his outstanding contributions on generalized inverses and their use in solving systems of linear equations to a large number of problems in applied probability. Thank you.
Okay.
Thank you, Professor Hunter. It's very exciting to know about your intensive academic interaction with Professor Rao, both in Penn State as well as in your own university. It's a very good, extensive presentation. Thanks for keeping us aware of your deep interaction with Professor Rao. Thank you.
My pleasure.
We can entertain 1 or 2 quick questions or comments. Yeah, looks like people are tired now. Okay. Anyway, we thank you again. I'll pass on to I'll pass on to the next speaker now, Professor Hasde. He is from New Zealand. So, Professor Hasde, the floor is yours, please.
So my talk today is going to be on treating random effects in linear models as fixed and testing whether they're zero. But before I begin the talk, I just wanted to make some preliminary comments about my introduction to C.R. Rao. So I met C.R. Rao in Auckland at the International Workshop on Matrices and Statistics. But before that, I'd been carrying around a number of his books for years. I do quite extensive work overseas, and I'll come to that in my talk. But so I used to take copies of several books because there were no PDF versions at the time. I was in Uganda at one stage, and I was going to be charged a great deal for excess baggage, so I had to leave my copies of linear statistical inference and Mitra and Rao in Uganda, hoping that they would eventually be returned, and they were. But I've been very grateful for many years about the material in the books, in C.R. Rao's books, and what I'm going to talk about today sort of leads on from that to some extent. So what I'm going to talk about is really outlined in the abstract here. Wald in 1947 looked at treating random parameters in mixed models as fixed and then testing whether they're zero. And I'm going to try and provide a context for this idea and look at whether it and when it's an approximation and to what extent it's an approximation by looking at the linear algebra that goes at the back of it. These results that Wald presented were extended by Seeley and Bazzoni in 1983, and they looked at testing whether some but not all of the random effects are zero. There's a related research strand which I'll come to, which looks at the links between linear models with parameters all fixed in one model, but some of them random in another. And more recently, there's been a paper by Hui, Muller, and Welsh in the Australian and New Zealand Journal of Statistics, which extended these results into trying to find a straightforward, easily comprehended, and computationally efficient way of conducting a test for zero random parameters. So there's some examples in that paper looking at when the approximation works best. But what's been missing to date is any explicit specification of the approximation. So I'm going to look at that approximation and using some explicit forms, which came from a paper I wrote back in 1996, which allowed deletion of the sub-equation that specifies whether some of the model parameters are random rather than fixed. So there are three strands from the literature I'm going to talk about. One's treating parameters as fixed. The other's stochastic constraints, which is really from Rao and Teutenberg. And the third is updating linear models. So the main references for treating random parameters as fixed are the ones I've outlined, which are Wald and Seeley and Bazzoni, and the paper by Hui, Muller, and Welsh, which appeared more recently. So this problem's got a long history. Wald's paper was 1947. And what the outline of what's going on here is if we consider a mixed linear model outlined by this equation here, where pi is the fixed parameters and b is the random ones, I'm not going to focus very much on normality assumptions at the moment, but look at BLUP instead. But Wald showed how to construct a confidence interval for testing whether we're looking at the correlation coefficient, or not so much correlation coefficient, but the ratio of the two variances. Again, I said it was Wald assumed full rank, but that was extended in 1983. So that's the core idea. We're going to look at that problem of, how close is using fixed parameters for B and testing whether they're zero to the problem of testing whether when B is random and testing whether those parameters are zero. Now I'm going to use a slightly different notation. I'm going to substitute beta for pi and z for B and gamma for B, small b. And I'll also consider more broadly cases where the variances of the random effects and the error are not diagonal and don't have equal diagonal elements. But I will, however, consider only linear and linear mixed models where I've got full rank, just because in a talk it's very difficult to go much further than that. And where additionally the column spaces of x and z don't intersect. I'll be looking at this model here. Y equals z beta plus z1 gamma 1 plus z2 gamma 2 plus e, with variance of e equal to r and the variance of gamma equal to this block structure equal to g. That's the case where gamma 2 is random in one model and fixed in another, but actually what I'm going to do in the focus in the end is all of gamma is going to be treated as fixed. So stochastic constraints. So when gamma is treated as fixed in one model and a random in another, the two models can be written in this way. The first one's just the case where beta and gamma are fixed. So there's only one variance, and that's for the error process. And the second one is the stochastic constraints construct, due to outlined in Rao and Teutenberg. And you'll see here that there's an additional equation at the bottom of the equation for y. And what it actually says is gamma equals minus u. And I could have put gamma equals u and put a minus I instead, but let's treat it this way. But the point is about the second equation is it cleverly incorporates the additional information that you don't usually see written down very clearly or explicitly when you're talking about random effects. It relates the first order properties to the second order properties for the random parameters. Now, this is a possible confusion I just want to cover very briefly. In the structure in 2, that random mixed effects model is denoted as random parameters as fixed, but there's a debate about whether it's a model. I happen to think it is, and Sima Punten thinks it isn't, but that's not an argument for here. But if sometimes when people use the random parameters treated as fixed, what they're actually referring to is the second equation, and they're acting as though in that second equation, despite it making no sense, they treat gamma as fixed, but computationally it works perfectly. All right. My point is that if you treat it as random, you can carry through with all the algebra and calculus and you still get the right answer without needing that assumption. But the point is that we just treat it as a computational trick at the moment. Just a small note in this here, if we let G tend to 0 in this model, we don't actually get the first model, just as a point of note to note. Updating linear models, well, in a paper in linear algebra and its applications in 1996, I outlined the explicit formula for addition and deletion of data parameters and simultaneous deletion of data and parameters from linear models. So these give changes to parameter estimates, residual sums of squares, and the variance of the difference. We'll see we're only interested in the difference now between treating parameters as random and treating them as fixed, rather than whether they're 0. And I'll explain why that's the case shortly with some diagrams. So it turns out the formula that we're interested in is for deletion of data in this context. So here's the result. We start off with the first model, numbered 3, and we update it by adding extra data and regressors and a bit more to the error term. All matrices of full rank, and what we actually want is what's the relationship between the estimates of beta 1 in this model, in the 2 models rather. And the answer is these equations 5, 6, and 7, with the various things written underneath that define the terms. Now I just want to note that this matrix CA plus CB to the -1 occurs in all of the things, and that we'll come back to this later, but in 6 and 7, the difference relates to a quadratic form, and in the first adds to the residual sum of squares, and in the second subtracts from the variance of the parameter estimates less their of the estimate of the parameter estimates less their actual value. The point about this is that there's not a lot of extra matrix inversions, given that if you fit the model, the first model, number 3 first, then sigma 1, 1 to the -1 is known, and consequently you don't need to invert any matrices of larger order than the extra y2 that you've added. All right. You can treat this as updating, adding data, or if you go look in reverse, it looks at deletion of observations. Part or all of beta 1 may be random. That's covered in the 1996 paper. But we can treat this random to fixed as a special case of the theorem. But I've got to digress a little. What does a random parameter equal to 0 mean? By construction, the unconditional expectation of the random parameters is 0. And looking at the situation where the column spaces intersect, we've got 2 possibilities, that gamma is fixed and gamma equals 0. But we need to consider what happens if you look at the expected value of gamma, given the labels that might be on these. So if you've got groups, clusters, in my case, I get to a situation where you've got small areas and small area estimation shortly. The labels are sometimes very, very important. In other words, in repeated sampling and rerunning models, what you get is that the random effects show some consistency for a given small area, and although their unconditional expectation is 0. I've used this quite often in work I do for the World Food Programme. This is an example of looking at severe stunting in children at Elika level, of which there's about 1,000 in Nepal. You can see that stunting severe prevalent in the mountains, less so in the Terai on the plains, but for different variables you get different answers. Now these models are fitted essentially using mixed models and applying a mixed model from a survey to a census. And I'm not going to go into the details of that, but the point is the labels matter. And that's exactly the situation I was talking about here, this expectation conditional on the small area. So when we're dealing with this, we need really to think about this expected value of gamma given I as one option for treating gamma equal to 0. And I'm going to provide some diagrams shortly that will link this idea. So I'm going to have 3 diagrams. One's the simple walled case plus this expectation of gamma given I equals 0. I'm going to look at a full partial deletion case, which is the one where you delete, where you essentially set part of gamma equal to 0. And then I'm going to look at a subset of those, which I'm going to focus on for the rest of the talk. The important point is there's going to be this little triangle 3 in the first diagram, because what we have is a schematic diagram. Bottom right, beta's fixed and gamma's random, but 3 moves it to beta fixed and gamma fixed. And pathways 1 and 2 go from each of those options to beta fixed gamma equals to 0, but the difference between them is the one I've got to try, number 3. So a lot of the talk is from here will focus on this pathway numbered 3, because although I'm interested in and in the other from beta fixed to gamma fixed, the difference between them is pathway 3. Now this gets a lot more complicated if you look at that diagram and start to look at situations where parts of gamma are changing and you've got the possibility that these expectations of gamma conditional on a small area or a set of small areas come in. And I'm not going to focus very much on this diagram except to say that each step in here is basically one change, and you can see there are a lot of things that connect up to one another. And it's really only part of this which has been discussed so far in the literature. I'm not going to talk at any depth at all about the expectation of gamma 1 conditional equal to 0 or gamma 2 conditional equal to 0. I just want to point out the situation is not perhaps quite as straightforward as it may first appear. So what I'm going to focus on is part of that diagram, and you can see that in fact the ones that I will focus on almost entirely are the ones that are in the brighter green color, which is the original diagram that we had, the first diagram I showed. And the other ones indicate the situation where you move to part going to random or part going to 0. And those are the ones dealt with in the 1983 paper. So I'm going to focus on the ones that are in the sort of lime green color and talk more about that. Sorry, I just noticed that in that diagram, top left, gamma 2 minus 0 is meant to say gamma 2 equals 0. Okay, so this is the framework we're working in, focusing on the lime green ones. So what we're going to look at is using stochastic restrictions. As I say, I'm going to put aside some of these ones with E gamma equals I and E gamma given I equals 0. And then it's pathway 3, as I commented on, that corresponds to the one that we're going to need to focus on. And pathway 3 corresponds to deletion of data. So the connection between stochastic constraints and deletion and observations or addition of them will now be the focus. So we go back to what we had for addition or deletion of observations. Addition, if you go from 3 to 4, 4 to 3 gives deletion. And we now put into the formula that we had the arrangement for stochastic constraints, and we end up with this structure here. There are quite a number of terms in here, and I'm not expecting you to absorb them all, but the same thing applies as before. No large matrix inversions, and in fact for GB, we can actually get an explicit form that doesn't involve a block inverse. And no surprise, the beta 1 in the model now consists of the fixed parameters and the random ones. You can do a similar substitution if only gamma 2 is going to be treated as fixed, but I'm not going to do that, as I said, because the algebra gets more complicated. You've got to invert a 3 by 3 block matrix, and it's going to make the exposition more difficult to explain. So I'm going to put these structures in here. You recall that X is the part that was fixed all along, R is the covariance of the errors in the process, and S is defined in the way above, or rather S minus 1. And I've got a few other terms there that basically look like the sorts of things you get in regression generally. The first one, the PXR, is just the regression of y on x, and the second one relates to rather more to what could be random or could be the fixed part of the model. And if we do that and use the linear statistical inference material in Rao, 1973, what we get is the following things here, and you'll see, at least in this format, they're not terribly complicated. So we've now got explicit results for changing fixed parameters as fixed, and hence vice versa from 5, 6, and 7. And these are them here. And we'll see that, we've again got the change in beta. There's a change in the beta parameter, even though it's the fixed one. And there's certainly a change in the gamma parameter, which I've made explicit at the bottom. And that's the change from moving from fixed, from random to fixed, or fixed to random. Now, I think that the signs of these things are rather dependent on y, as you'll see. I mean, it's not simply a case of one being smaller than the other, etc. It's very much a question of what your data y is. But for when you get onto the residual sums of squares, that's not true. You'll see here that the residual sum of squares for the first model has added to it something when you go to the second. And what that's saying is when you go from fixed to random, the residual sum of squares increases. And this is because this term here is a quadratic form. So the fixed parameter model necessarily has a smaller residual sums of squares than the one in which gamma is random. Now, you are basically applying constraints. Gamma random forces a distributional structure on gamma tilde that's not part of gamma hat. In other words, onto the random structure rather than the fixed one. And you could use all sorts of other distributions, and Alan Welsh is looking into that at the moment. But an indication of which distribution might best be used may be available through looking at the pattern of the corresponding fixed effects if you were to fit the model with gamma fixed. But in contrast, the variance of the difference of the parameter estimates from or predictions from the actual parameter does the opposite. So treating gamma as fixed increases the variance of the parameter estimates relative to treating gamma as random. And this is actually a strong argument in favor of fitting models that include random parameters when it's practical to do so. So the two things operate in different from random to fixed, the variance increases. But if you go from random to fixed, the residual sum of squares decreases. Again, no further inversion of large matrices is required. It's really only the dimension of gamma that requires an inversion. And it's a core advantage of using updating equations rather than completely refitting the model. That's especially so if the model's of high dimension. So, an example, one of the simplest cases is when Z, the matrix of zeros and ones that multiplies gamma, is columns containing group membership and hence zeros and ones, all columns orthogonal. I'm going to look at the equal numbers of observations per group example, R diagonal, and so is G. The Hui paper simulates this and notes that this and in other situations, the Wald approximation works well when there are many groups with few members in each, but not so well when there are a few groups each with many members. I've reparameterized the usual model to ensure the column space intersection 0. But the model you get is still linearly sufficient, so this isn't an issue. There's a paper that I was one of the co-authors for that deals with this linear sufficiency. So the change from random effects to fixed effects, RSS reduces. It reduces by this linear form. It leads to similar. Using the formula here, we get to a very similar conclusion to Hui et al. With increasing numbers of observations per group, this function Ca plus Cb to the -1 approximately equals the inverse of the variance of the random effects, provided the variance is not too small relative to the variance for the model error. But what happens is, due to the order of the various effects, the conclusion that we came to, and Hui et al. Came to, is pretty much the conclusion that comes out of this, or directly out of this. And in fact, there's now an explicit form for the accuracy of the approximation. I haven't provided all the formula in this talk. That's really, this slide just summarizes all of that, talks about the quadratic forms, talks about the terms in those quadratic forms, talks about the order of them, and looks at when the Wald approximation is likely to work best. In other words, the Wald approximation is treat your random parameters as fixed and test whether they're 0, rather than treating them as random and testing whether they're 0, because that's computationally rather more intensive. Conclusions. So firstly, covariance matrices have been assumed known or estimated for one model and then reused for another. In practice, the mixed model software re-estimates these for each fitted model. So there'll be actually an R hat and a G hat for the two models. Well, G hat will be 0 when you're treating parameters as fixed, the random parameters as fixed, but there's an element to which these are first approximations. However, any difference between adjacent models should be comparatively small, and they can be checked through the relevant computer output. So we've now got an explicit method for checking whether the approximation of Wald is sufficiently accurate. The method can be extended to the case where only some of the random parameters change. Those extensive schemata I've provided that link the various models will allow models that include conditional means of random effects, in other words, terms of the expected value of gamma given the labels. They can be considered using the formula for additional parameters, which I haven't covered here, that are in Hazlitt 1996. And finally, there are cases where these conditions of not of full rank, or where the intersection of the column spaces isn't 0, that remain to be explored. Thank you very much.
Thank you, Dr. Hasley. It's a very interesting presentation. I have much interest in linear models and fixed, mixed, and random effects models. I have closely followed the work by Simo Puntanen, sitting in Tampere. It's good that you have also collaborated with him. It's very nice presentation. Thank you. If there are any questions or comments, let's take up.
Thank you, Professor Steve.
Is there any question or comment? Dr. Hasley, I have a small point to make. Towards the end, you mentioned about the number of groups and the number of observations per group. Because we are dealing with a random effects model, to be able to estimate the variance component attached to the random effects, we need more number of groups than fewer groups with more observations. So what you have said is just right. We need more number of groups to be able to estimate consistently the variance component. That was your observation. Okay. Now, any further questions or comments? So we are at the right time. Let me thank both the speakers, Dr. Hunter and Dr. Hasley, for making interesting and very relevant presentations relating to the life and work of Professor C.R. Rao. So to conclude, let us hope that Professor Rao will have a peaceful life in the years to come. Thanks for your participation. Back to the organizers.
Professor Steve and Hunter will meet again tomorrow.
Yes, I'll be there. I will try and log in later on your evening. It'll be early hours of the morning, but I'll set my alarm.
Yes, I think it's something like 4 or 5 a.m. So it's, don't expect, if Jeff and I are here, don't expect eyes open all of the time. Yeah.
Okay.
Thank you.
Okay.
Thank you.
Thank you very much, Professor, for chairing the session. In this session, we have contributory talks from Anjan Gautam, Sikkim Manipal Institute of Technology, Sikkim, India; Divya Devi T, National Institute of Technology, Tiruchirappalli, India; Jyoti Shetty, Manipal Institute of Technology, Mahe, Manipal, India; Krishna Chandra Panigre, National Institute of Technology, Raipur, India. I request Professor Pradeep G. Bhatt, Department of Mathematics, Manipal Institute of Technology, Mahe, Manipal, to chair this session. Over to you, sir.
No problem.
Hello everyone. Hello everyone. My name is Anjan Gautam. I am research scholar under the guidance of Dr. Biswajit Dev, Department of Mathematics, Sikkim Manipal Institute of Technology, Majda, Sikkim. So I am going to give a talk on graphs with k-regular dominating set. Before starting, I would like to show you my outline, which are as follows. So I am going to give a talk. Starting with the introduction, I would like to start with the definition of graph. A graph G is a pair VG where VG is a finite non-empty set whose members are called vertices, and EG is a set of unordered pair of distinct elements of VG. Those elements we call it as edges. Now for a vertex V, the open neighborhood of V is defined as it is the set of all U in V such that UV is an edge of a graph G. Similarly, the closed neighborhood of V is defined as it is the union of an open neighborhood of V union V itself. Now, a subset S of a VG is called a dominating set of graph G if every vertex in V naught S has a neighbor in S. Now, the dominating number gamma G is the minimum cardinality of all the dominating set of graph G. Now, I would like to show you the example for a dominating set. If this is a graph G with 7 vertices, here the dominating set is 2, 6. As we can see that for all the vertices outside the dominating set 2, 6, they have neighbor in D. That is 3 as a neighbor 2, 1 as a neighbor 2, 5 as neighbor 6, 4 as 6, and 7 as 6. So this is the dominating graph. This is a graph whose dominating set is 2, 6, and domination number is 2. Showing more examples on dominating set. This is a graph G with domination set D as 2, 5. Here we can see that 2 and 5, there is some relation between them. That is, they are adjacent. Now, when we draw induced subgraph of a dominating set D, we are going to get an edge connecting between 2 and 5 in an induced subgraph. So we can say that its dominating set is 1 regular. That is, they are connected to with one edge. Similarly, for the same graph, we can see we can have another domination number, that is 2, 6. Dominating set, that is 2, 6. So the induced subgraph of this dominating set is going to be 0 regular. Why? Because 2 and 6 are not adjacent in the induced subgraph, as you can see that they are distance 2 apart. So this motivates us to define a regular dominating set. So the definition of K-regular dominating set is as follows. A dominating set D of a graph G with induced subgraph D is K-regular. Now, if the induced subgraph D of a graph G is K-regular, then we call that set as a K-regular dominating set. As we can see that that set is dominating as well as it is K-regular. Now, we will see this example. Now, this is a 3 regular dominating set. This is a graph with 3 regular dominating set D is equal to 1, 2, 3, 4. Now we can see that as this 1, 2, 3, 4 vertex comprise of a complete graph with 4 vertices, where 2 vertex, each vertex has 2 pendant vertices. Now we can see that the minimal dominating set is going to be 1, 2, 3, 4 only. Otherwise, if there can be other dominating set also as 1, 2, 3 and 5 and 6, but that is going to increase the domination number. So the minimality will lose. So the minimum dominating number is only 1, 2, 3, 4. Now when we draw in this subgraph of this dominating set, it is going to be 3 regular. Now this seems interesting because we can see this is the only dominating set in this graph, and minimal dominating set with the domination number 4, which is 3 regular. Now this motivates us to define a strongly K-regular dominating graph, which is defined as a graph G is said to be a strongly K-regular dominating graph if each dominating set of size gamma G is K-regular. That is, for every dominating set of the size gamma G, of a domination number gamma G, that is K-regular. Now we will see strongly 0 regular dominating graph and results for them. Now for the path Pn with n vertices, the path Pn with n vertices, then Pn is a strongly 0 regular dominating graph if and only if n is congruent to 0 or 2 mod 3. So we will not prove this proposition because that's easy to prove it, but we will illustrate it with the help of example. Now we can see in this figure that it is a path P7 with dominating set 2, 5, 7. As we can easily say that two vertices are not sufficient to dominate this graph, as 2 has covered 1 and 3, 5 has covered 4 and 6, and 7 remains still. So we have to include one more vertex. So here we have included 7. Now with this inclusion, the dominating set is 2, 5, 7. Though the induced subgraph of this dominating set is going to be zero regular, but we can see for the same graph we can have another dominating set, that is 2, 5, 6. This is also a dominating set for the same graph. Now we can see there are two different dominating sets, but one is zero regular, other is not. So what does this definition of a strongly k-regular dominating graph says? That every dominating set with the domination number should have k-regular, and induced subgraph should be k-regular. But as we can see in figure 6, the dominating set 2, 5, 6 is not going to be the zero regular dominating set. So that's why for n congruent to 1 mod 3, this result Pn is not strongly zero regular dominating set. So it is strongly zero regular dominating set if and only if n is congruent to 0 or 2 mod 3. Similar result with the cycle. If let Cn be a cycle with n vertices, then Cn is a strongly zero regular dominating graph if and only if n is congruent to 0 or 2 mod 3. Here also we can see that 1, 4 and 7 is going to be the dominating set for this cycle C7. Now as we see that 1 and 7 are adjacent and 4 is not adjacent to 1 and 7. So the induced subgraph is not going to be zero regular. We can get the dominating set as 1, 4 and 6 also, which is going to be zero regular, but for this to be the strongly zero regular dominating, it should have that at this dominating set should be strongly zero regular. So here it is not strong because there exists a dominating set whose induced subgraph is not zero regular. Moving further, we will see the examples of strongly one regular dominating graphs. Before that, we will a tree containing exactly two non-pendant vertices is called a double star. A double star is strongly one regular dominating graph if and only if each of the non-pendant vertices has degree 3 or more. We will see the example for this also. Families of double star are strongly one regular dominating graph. Now I would like to show you some examples. Now, as the preposition says that for every non-pendant vertex, that is vertex is 3 or more. So double star is one regular, as the dominating set contains this vertex and this vertex. So this set is going, this graph is going to be strongly one regular. Now if we keep increasing this type of graphs so many times, that is families of double star, then that family is also going to be one regular, because the dominating set will contain the middle vertex, this. Even if we draw edge between these pendant vertices randomly, this way, then also it is going to be one regular only. It is not affecting the regularness, as it is one regular of these families. So this is one example of one regular dominating graph, strongly one regular dominating graph. Okay. Now we will show the construction of strongly k-regular dominating graph. Now given a graph, how can we construct a strongly k-regular dominating graph for a given every graph? So given a graph G, we can construct a strongly k-regular dominating graph. For that, we will first take a complete graph with k plus 1 vertices. Now put at least 2 pendant vertices to each of the vertex of k plus 1, complete graph with k plus 1 vertices. Now we will select two vertices U and B of the complete graph and add one more vertex to both of them. That is, those vertex U and B are going to have degree at least 3 because two pendant vertices are already added. Now we are adding one more to each of them for U and B. Next, what we are going to do is we are going to take an edge xy from the graph G and we are replacing x with U and y with V. That is, we are going to replace that particular edge with this constructed graph. Now we are going to take the size easy number of copies of that constructed graph, that is complete graph with pendant vertices, and repeat this step with each edge of G. That is, we are going to replace each edge with this graph. Then, since this is a complete graph with k plus 1 vertices, so complete graph with k plus 1 vertices is k regular. And dominating set for this graph is going to contain all the vertices from those complete graph, which is k regular. So we will illustrate this with the help of example. Here we can see if this is, suppose this is a graph, then what we are going to do is we are going to take one complete graph. It is a complete graph with 5 vertices. Now what we are doing is we are giving at least 2 pendant vertices to each edges. That is 2, 2. Here it is 4, here 3, 3. So what we are going to do is we are going to determine 2 vertices with at least 3 pendant vertices. That is U and V. Excuse me. With U and V. Now what we are going to do is we are going to replace this edge with this graph. That is, x will be replaced by any of these vertices, this or this. Suppose we are replacing x with this vertex and y with this vertex. Then our new graph is going to be like this way. Now what we are going to do is we are going to replace each such edges with this type of graphs. Each such edges with this type of graphs. So we are going to get new graph where the dominating set is going to be, as we can see, the dominating set for this particular this graph is going to be these vertices only, vertices of the complete graph. This 1, 2, 3, 4, 5. So for each edges, this is going to be the dominating set. So for the other edge, the same thing is going to be the dominating set. For the next edge, it is going to be the same. So when we collect all the dominating set of this constructed graph from graph G, we are going to get the k regular. That is, if it is complete graph with 5 vertices, then we are going to get a dominating set with 4 regular vertices. Now moving forward, so I would like to conclude my talk with the conclusion saying that the theory of domination is fastest growing as well as an important area in graph theory. So here we have characterized some classes of graph that are strongly 0 regular and 1 regular. We have also constructed the classes of graph which are strongly k regular dominating graph. For a given graph, we are constructing a strongly k regular dominating graph. Now, our main aim is to characterize all the graphs that are strongly k regular dominating. So, thank you everyone for listening to my talk. Thank you.
Good, Anjan. Good presentation you have done. Have you any questions from the audience? Hello. Any questions?
Yes, sir. I have a question. So you have considered a double star, right?
If there is no questions, I will ask one.
No, I have a question, sir. Yeah.
Okay.
In the example, you have considered a double star. So can you consider a star with many centers and not many centers, one center and many vertices of the same kind, which have their own pendant vertices and pendant edges.
Hello.
So yeah,
I'm not.
can you consider?
I'm not getting your problem. No.
What happens if you consider instead of a double star, you have one central vertex and several vertices adjacent to it with their own pendant vertices. So it's still a tree, but you have one vertex in the center which has degree, say, k, and each of the k vertices adjacent to it have their own some m pendant vertices adjacent to them.
Okay, you mean actually taking a star graph and putting one pendant edge to each of those pendant vertices.
Yes, so
okay.
You can say it's a star corona with km complement.
No, actually, that graph is not going to be strongly k regular dominating, because we can see that there is a dominating state which we can take a center vertex and the vertices which are at the outermost region. That means the added vertex which we have added new vertex. Which we add new vertices. So those state collection of those state is going to be my new dominating state for this graph, constructed graph. So, and that is not strongly one regular, because I have and in example I have shown that those classes of double star are going to be my strongly one regular dominating graph. So whereas that constructed the new graph, as you have mentioned, that is not going to be strongly one regular, because I can get some dominating state which is not strong, which induced subgraph is not going to be strongly one regular.
Oh, right. Okay? Yeah, I see. Yeah, I see. Thank you. Thank you.
Thank you.
Pradeep, are you online?
Hello.
Anyway, thank you,
I'm
Anjan.
online.
We'll move on
Thank
to
you,
another
Anjan.
talk.
Okay, thank you, sir.
We discuss bounds for the spectral radius of the eccentricity matrix of graphs. This is the outline of the talk. First, we discuss what is eccentricity matrix and some of its properties. Then we investigate the eccentric spectrum of some graphs. Finally, we give some short lower and upper bounds for the eccentric spectral radius. Given a graph G, we can associate a matrix related to G. Such well-studied matrices are adjacency matrix, distance matrix, Laplacian matrix, etc. These matrices have been studied and applied widely. Similar to this notion, the eccentricity matrix was introduced. Let us begin with the definition. What is eccentricity matrix? Consider a simple connected graph G on n vertices. Then the eccentricity matrix is an n by n matrix, which is denoted by E of G, whose ijth entry is defined by distance between the vertices Vi and Vj, if this condition is satisfied. Otherwise, it is 0. Where that notation E of Vi denotes the eccentricity of a vertex Vi, which is maximum distance from Vi to all the vertices in a graph G. The maximum eccentricity of a vertex is known as diameter of a graph G. Let us see the simple example. Yeah, you consider this graph G. The corresponding distance matrix is given here. These red color entries denotes the eccentricity of a vertex. Then the eccentricity matrix is given here. When you look at the 1/3 entry, eccentricity of V1 is 2, eccentricity of V3 is 3, so minimum is 2, which is not equal to distance between V1 and V3. So 1/3 entry in the eccentricity matrix is 0, and you whereas look at the 1/4 entry. Eccentricity of V1 is 2, eccentricity of V4 is 3, minimum is 2, which is distance between V1 and V4, which is equal to distance between V1 and V4. So 1/4 entry is retained. Like that, we can obtain the eccentricity matrix. Yes, let us list the sum of its property. And this matrix was introduced namely as a Dmax matrix by M. Randick in 2013. Why it has the name Dmax means it has some peculiar property. It retains the maximum distance in each row and each column of the distance matrix. By that you consider the distance matrix of a before discussed example. In the first row and first column, largest entry is 2. So just retain the corresponding entry. And in the second row and second column, maximum entry is 3, which occurs at 2 fourth and 4 2th place. You just retain that entry. In the same way, the fourth matrix was obtained. Now you set the remaining entries as 0. So the fifth matrix is indeed a eccentricity matrix of G. So the eccentricity matrix can be obtained from the distance matrix by retaining the largest distance in each row and each column of the distance matrix. Right. Whereas the adjacency matrix can also be obtained from the distance matrix by retaining the smallest non-zero distance in each row and each column, which is 1. In this point of view, eccentricity matrix and the adjacency matrix are opposite. So it has another name, anti-adjacency matrix. Yes. From the definition, it is clear that the eccentricity matrix is non-negative and real symmetric. So by Schur's theorem, all its eigenvalues are real. The set of all eigenvalues of the eccentricity matrix is known as eccentric spectrum of a graph G, and the largest eigenvalue of the eccentricity matrix is known as eccentric spectral radius of the graph G. One of the most important property for connected graphs are the distance matrix, adjacency matrix, all are irreducible. Whereas this property does not hold for the eccentricity matrix. For that, you consider the eccentricity matrix of a complete graph, which is irreducible. Whereas eccentricity matrix of a complete bipartite graph with at least one partition has more than 2 vertices. And in that case, the eccentricity matrix is reducible. So, by natural to ask the question, at least for which class of graphs the eccentricity matrix is irreducible. This question was proposed by J. Wang et al. In 2018, and the same authors proved that the eccentricity matrix of a tree is irreducible. Alright. So, and people have studied the correlation between the eccentric spectral radius and some boiling point of the some chemical components, and observed that the eccentric spectral radii is a better predictor of some topological indices than the spectral radius of the adjacency matrix. Right. And Randick observed that the eccentricity matrix can be different even for structurally related molecules. So it can be used to testing the graphs for isomorphism. Recent results related to eccentricity matrix are computation of the eccentric spectrum. That is, the eccentric spectrum of some classical graphs like complete graph, complete bipartite graph, star, path, cycle, etc. These have been computed. One such result is given here. This is the eccentric spectrum of cycle. These are all the results, bounds available for the eccentric spectral radius. The bounds are given in terms of entries of the eccentricity matrix, first and second eccentric degree sequence, and Wiener index. So motivated by these results, we are adding some more bounds to the eccentric spectral radius in terms of average eccentric degree sequence. Now we can go for the computation of eccentric spectrum of some graphs. For that, we need the notion of diametrical graph. We call a graph G as diametrical graph of diameter D if given any vertex U, there exists unique vertex V such that the distance between U and V is D. Some cycle of length 4 is one such simple example. Yes. Here, the maximum distance is 2, which is for x1, it attains at x4, for x2, it attains at x3. The corresponding distance matrix is given here. In each row and each column, 2 occurs exactly once. So, this gives the existence and uniqueness. So, this is an example for diametrical graph of diameter 2. And the next result gives the eccentric spectrum of composition of a diametrical graph and some connected graph. Right. The proof is quite simple. When you compute the eccentric spectrum of eccentricity matrix of G composition H, then it will look like some tensor product of 2 matrices. By using some properties of the tensor product, we can deduce this result. The next theorem is obtained from the previous one by raising the question what happens if the diameter is less than or equal to 2. In fact, this result gives the relation between the eccentric spectrum and the adjacency spectrum. Now we can go for the bounds. For studying bounds, we need the notion of pseudo-eccentric regular. The ith row sum of the vertex Vi, and the ith row sum of the eccentricity matrix is known as eccentric degree of the vertex Vi. If the eccentric degree is a constant sequence K, then we call the graph G as eccentric K regular graph. The second eccentric degree and average eccentric degrees are defined like this. If the average eccentric degree is a constant sequence, then we call the graph G as pseudo-eccentric regular graph. From the definition, it is clear that eccentric regular implies pseudo-eccentric regular, but the converse need not be true. For that, you consider this example. Join of complete graph on 5 vertices and complete complement of the complete graph on 3 vertices. And the corresponding eccentricity matrix is given here. Here the average eccentric degree is a constant sequence 4. So this is a pseudo 4 regular graph, whereas the eccentric degree of the vertex V1 is 4, eccentric degree of the vertex V6 is 2. So this is not a eccentric regular graph. Yes. Consider a graph G on n vertices. EI bar denote the average eccentric degree of the vertex Vi. Then the upper bound for this eccentric spectral radius is maximum of this set, and lower bound is minimum of this set. The both lower and upper bounds are attained only when G is a pseudo regular graph. Right. The next corollary can be proved by observing the fact that the spectral radius always lies between the maximum and minimum of the rows. These are all some references. Thank you.
Any questions? Any questions from the audience?
Divya, unmute yourself in case you want to answer any question.
Sure, sir.
Unmute yourself. Any questions?
No, sir. Okay.
No.
Divya.
Okay, then.
Divya. Yeah, Divya Devi.
Pradeep.
Yes, sir.
Yeah, from the graph you have done the eccentric matrix.
Yes, sir.
Your eccentric matrix, is it gives any informations about the graph?
Yes, sir. Actually, it gives some structural properties. This matrix is used to find some boiling point of some chemical component. It has some application in chemical components. It is used to study
about the graph I am asking.
Sir, could you please repeat it?
Can you, from your eccentric matrix, can you able to get any properties of the graph? No, okay, you can think it.
Sure, sir.
Okay, good.
Thank you, sir.
Good luck for you.
It's Vishwajit must be having a question. Please bring him in. Okay, if it is difficult, let us go to next talk. Pradeep, please proceed.
Yeah. Okay, okay.
I'm here. Hello.
Yeah, the next.
Can you hear me, Divya?
Yes, sir.
Actually, I just wanted to know, is there any comparison of eccentric spectral radius and spectral, say, Laplacian spectral radius or adjacency spectral radius?
Actually,
Means graphs for which this say Laplacian spectral radius and eccentric spectral radius matches, or say distance spectral radius and eccentric spectral radius matches.
Sir, this
Any
eccentricity
characterization?
matrix has started to study in 2018. Recently, mostly 2 or 3 papers are published, but the relation between the spectral radius of distance matrix, Laplacian matrix, and these relations till now not found, sir.
Okay. Any characterization of graphs, those having same spectral and radius and eccentric spectral radius?
No, sir.
No. Okay, thank you.
Thank you, sir.
Okay, go to next.
We can call next participant.
Hello everyone, I am Jyoti Shetty. Today I am going to talk about my work in semigraph with BIBD and PBD with lambda equal to 1. The lambda is called the index of the block designs. Since semigraph is not such a familiar structure, I would like to show how a semigraph is. So this is the semigraph I have taken. Semigraph is basically a generalization of graph with multiple vertices on edges. So this is a semigraph that you can see I have labeled it as E1 is an edge with 5 vertices, whereas E2 and E3 are 2 edges with respectively 3 vertices, and E4 is an edge with 2 vertices. There is a definition for incidence matrix of a semigraph. In the incidence matrix of the semigraph, rows are indexed with the vertices of the semigraph and columns are indexed with the edges of the semigraph. And entry is 1 if the vertex ui and edge ej are incident and 0 otherwise. And one more thing we would like to note is the definition of edge-complete semigraph. A semigraph is edge-complete if every 2 of its edges have a vertex in common. So in the previous semigraph, you can see this edge E and edge E2 are adjacent, E1 and E4 are adjacent, whereas E1 and E4 are non-adjacent because they don't have a vertex in common. I would like to brief about combinatorial design. Combinatorial design theory concerns question about whether is it possible to arrange elements of finite set into subsets so that certain properties are satisfied. In particular, the definition says a design is a pair XA such that the following properties are satisfied. First one, X is a set of elements called points, and A is a collection of non-empty subsets of X called blocks. In particular, in this work, we are talking about BIBD and PBD. So let us see what is a BIBD in a block design and a PBD in the block design. A balanced incomplete block design is termed as BIBD. Is an arrangement of n points in B blocks of k distinct points each, where k is less than n, satisfying the condition that any 2 distinct points occur together in exactly lambda blocks. So n points in B block such that each block contains k distinct element and any 2 distinct points occur together in exactly lambda blocks, where lambda is the index of the block design, and this property is called the balance property. It satisfies these 2 given equations, and a BIBD with parameter n, b, r, k, lambda, which we have already discussed, is called the nk lambda BIBD. And a PBD is a pairwise balanced design. It's an arrangement of n points again, B subsets called blocks, such that any 2 distinct points occur together in exactly lambda blocks, and blocks of sizes from a set K. So here in BIBD, all blocks of same size K, whereas here The block size may differ, but rest of the conditions remain same. And one more thing we would like to notice, when a BIBD is called a symmetric BIBD, when B equal to N, that is number of points equal to number of blocks. Some of the results from the literature about block designs. One thing is a definition of incidence matrix of block design. Here the rows are indexed with the points and columns are indexed with the blocks, and 1 when a point belongs to a block and 0 when a point doesn't belong to a block. And the theorem, this theorem is about the incidence matrix, how it is related to the parameters R and lambda in particular. So if it's a NBRK lambda BIBD, then MM transpose, that is the incidence matrix of the block design at BIBD, is equal to lambda times Gn plus R minus lambda Im, and vector M is equal to K times the other vector U. It's a vector. And there is one more definition, that is, suppose X is a symmetric BIBD, that means B equal to M is, then if you take intersection of any two blocks, the number of elements in that intersection is equals to lambda. Main result. Here, before we start with the results, we would like to note a simple thing, that is, a semi-graph is edge complete if and only if its line graph is complete. Edge complete, we have already taught any two edges have a vertex in common, and it is complete, edge complete, a semi-graph is edge complete if and only its line graph. Line graph of a semi-graph is defined on similar lines as in case of graphs. And we have a result, the first one, lemma, that is, if M be an incidence matrix of NK1, 1 means lambda is 1 M, BIBD, then M transpose M minus KIB is A of L of G, where A is the adjacency matrix of line graph of semigraph G, where G is not a usual semigraph, it's a NK1 BIBD semigraph. Next is for a symmetric NK1 BIBD, M transpose equal to M transpose M. And we term a symmetric BIBD semigraph if the edge set of G forms a symmetric BIBD. A symmetric NK1 BIBD corresponds to an edge complete semigraph. This is the main result. So this is from the literature. M transpose is equal to lambda. As we have said, it's a relation between the parameter R lambda with incidence matrix of the block design. In particular for BIBD semigraph, lambda equal to 1, so we get this. And this we have already discussed. This is the result we have got. It's A of L of G. And since we are talking about a symmetric BIBD, B is equals to M. And we have already discussed, if it's a symmetric BIBD, M transpose equal to M transpose M. So when we take the difference, it's equal to 0. We substitute the thing. But for any, when B equal to N, R also equal to K. And we simplify, what we get is Jn minus In is equals to A of L of G. Jn is a matrix of all ones, and this is an identity matrix of order n. So when you subtract, you get, what you see is only the diagonal elements going to be 0. That is the adjacency matrix of a complete graph. So L of G is a complete graph of order n. So when a line graph is a complete graph, what about G? We have already noted that G is an edge complete semigraph with n edges. That observation, first thing we have noted. Hence, a symmetric NK1 BIBD corresponds to an edge complete semigraph. Some of the references. Thank you.
Any questions to Jyoti Shetty? If there is no questions, thank you for nice presentation, Jyoti. Okay, proceed. Next part.
From NIT Raipur. On the 100th birth anniversary of Professor C.R. Rao, I am going to present reverse order law for tensors and its applications. To do this, I organize my presentation in this way. At first, introduction, thereafter literature and motivation, then the objective drawn from it, and thereafter the research work carried out, and then the references used in this presentation. Let's start from introduction. As we see the title of the presentation, there are two keywords, tensors and reverse order laws. Let's start from what are tensors. Tensors are the generalization of scalars, vectors, and matrices to an arbitrary number of indices. That means whenever we are writing a scalar, we are just written as numbers, that is 1, 2, 3, 4, like that. So we don't need to any indexing. And whenever we are representing a vector, then we are writing AI, like that here. The vector V is represented by AI. And while in case of a matrix, we are writing it as Aij. If we generalize this indexing, that here no indexing is there, here one indexing I is there, here two number of indices I and j are there. If we generalize this, if we extend the number of indices, then this is called a term we used to call it as a tensor. And then what is dimension of a tensor? The dimension of a tensor means if a tensor A belonging to the space f I1 cross I2 cross In, in that case we call the dimension of the tensor A is I1 cross I2 cross In, and this I1 cross I2 cross In is individual, that is I1 is called the dimension of first way, I2 is called the dimension of second way, like that In is called the dimension of nth way. Also we call the dimension of its nth mode. It's I1, I2, I3. In this way we are defined. And thereafter, what is order of a tensor? Order of a tensor means the number of indices associated with it is called order of a tensor. Suppose a tensor A is represented as A equal to A I1, I2, In. In that case, this I1, I2, In are m number of indices, so it is called a mth order tensor. So following this definition, a scalar becomes a zeroth order tensor, a vector becomes a first order since it is only one index is there, and a matrix becomes second order tensor. That means a second order tensor is nothing but a matrix. Here an example of a third order tensor is given here of dimension 2 cross 2 cross 3. And next, like in case of matrix we have rows and columns. In case of a tensor we have frontal slices, lateral slices, horizontal slices, and tube fibers. Here I am taking a 3 by 3 by 3 tensor, dimension tensor, that is third order of dimension 3 cross 3 cross 3 tensor, representing here this blue line first face represents the frontal slice. Here it represents the this one also represents the frontal slice, this one also represents the frontal slice. Let's see an example here. If we see this third order tensor, then the 0, 1, 4, 5 represents this one, represents the frontal slice. Here I am representing here, and 3, 1, 4, 6 is also another frontal slice, and 2, 1, 3, 15 is also another frontal slice. While if we see like in this way 0, 4, 3, 4, 2, 3, this if we take together these three, then this is a lateral slice, like that. In this way if you choose, this becomes a lateral slice. Also another lateral slice here is 1, minus 5, 1, 6, and 1, 15. And the horizontal slices are here 0, 1, 3, minus 3, 1, and 2, 1. This is a horizontal slice. And another horizontal slice here is 4, minus 5, 4, 6, 3, 15. Next, here tube fibers. The tube fibers are nothing but they are the singly we choose. That means if we choose 0, 4, then it becomes a type fiber. If you choose only 0, 3, 2, then it is another type fiber in this way. So next, after knowing what are tensors, let's come to define product on it. In case of matrix, we have number of product rules. Here also a number of product rules are there. But whenever we generalize this product rule, we need to keep in mind that if it reduces to second order tensor, then it must coincide with the rule of matrix multiplication. It must satisfy the matrix multiplication, because a second order tensor is nothing but a matrix. So here in this research work we are using Einstein product. So let's know how Einstein product is defined. Einstein product is defined for two tensors if a tensors A and B, between A and B, if the last n indices of last n dimensions of tensor A is coincide with first n indices of tensor B, then we define A star and B. And the rule, the entries of this A star and B is defined in this way. And the dimension of the resultant tensor A star and B lies in A I1 cross I2 cross IM2, K1 cross K2 cross KL. Here the simplified notation I1 dot dot and so on M, it represents I1 cross I2 cross IM. Here is one example for the Einstein product. If we consider the two tensors A and B from dimension 2 by 3 by 3 and 3 by 2 by 2 respectively, and defined like this way, then we see that the last two dimensions 3 cross 2 and here the first two dimensions 3 by 2 coincides. So we can define here star 2 product. So and after using this rule, Einstein product rule, we get the resultant answer like this. This 4 is multiplied with 4 minus 5 is multiplied with 0, 4 is multiplied with 4. In this way we can calculate this tensor. Next, once we define the product rule, we are now ready to define ordinary inverse of a tensor. Brazel and his collaborators in the year 2013 gave the defined ordinary inverse of a tensor and ordinary inverse of a tensor for even order square tensor. A tensor X is called inverse of the tensor A if it satisfies Ax is equal to identity and X star n equal to identity tensor. And this tensor is the inverse of the tensor X is denoted by A inverse, and they used this inverse of a tensor to solve the multilinear system of equations Ax is equal to B, and they find that this solution is unique and the required solution is X equal to A star inverse star n B. And also they verified that the ordinary, also one can easily verify that reverse order law for A B inverse, the inverse, if A invertible, B is invertible, then A B inverse becomes B inverse star n A inverse. After that, in the year 2017, Son and his collaborators defined Moore-Penrose inverse for even order tensors. For a even order tensor A, in the field I1 to IN cross J1 to J1 J2 cross J2 cross Jn, there exists a tensor X from J1 cross J2 cross Jn to I1 cross I2 cross In, satisfying these four conditions: Ax A equal to A, X star n A star n X equal to A X, and A star n X is Hermitian as well as X star n A is Hermitian. In this case, we call the tensor X is Moore-Penrose inverse of A, and they also verified that such tensor exists for every even order tensors and it is unique. After that, in the year 2017, Behra and Misra find that if the tensors, if we consider the tensor A and B, then A, B Morippendo's inverse does not satisfy reverse order law. That is, A star and B Morippendo's inverse does not equal to B Morippendo's inverse, A Morippendo's inverse. For this, they are considering this example. I am collecting the example from this paper by the paper Behra and Misra. One can find this example, exactly this example from example 2.4 from their paper. And the literature. In the year 2019 and 20, Panigrahi Misra, Liang Zhang and Stanhovic independently defined Morippendo's inverse for arbitrary order tensor. Earlier we see that Son and his collaborators defined this only for even order tensors. So here in this paper, in these three papers, we found the definition for Morippendo's inverse of arbitrary order tensors. So after from these literatures, we are interested to work on reverse order laws for Morippendo's inverse of arbitrary tensor and what are its applications. And this is our objective, that to demonstrate reverse order law of arbitrary tensor and find what are its applications. And my main result of the research work are this. We find that whenever the tensor A and B satisfies these two conditions, that A dagger A is observed by the tensor B star L B H star N A, its conjugate transpose A, observed by if A dagger star N A is observed by the tensor B star L conjugate transpose of B star N conjugate transpose of A, and A star N B star L B dagger star N A dagger is Hermitian. In that case, A and B satisfies reverse order law. Also, we find that if if A dagger A dagger star N B whole satisfies reverse order law, as well as A star N B Morippendo's inverse equal to A Morippendo's inverse star M A star N B whole Morippendo's inverse star N A Morippendo's inverse. In that case, also reverse order law satisfies. These are the two results of my article. Whereas we also find more results. One can go through my paper to get another results. Also, we applied this reverse order law to find additive Morippendo's inverse. That is, it is an important task to find what becomes Morippendo's inverse of A plus B. And here we find that if the tensor A and B, if the tensor A and B satisfies I identity tensor plus A dagger star M B is invertible, and A star M A dagger is observed by B on pre-multiplication and on post-multiplication. In that case, A B Morippendo's inverse is exactly equal to identity tensor inverse of identity tensor plus A Morippendo's inverse star M B star N A Morippendo's inverse. And here is another result. We are finding this inequality, that B Morippendo's difference of B Morippendo's inverse A Morippendo's inverse, where B is a tensor obtained by a small addition of small changes in elements of A, then this inequality satisfies. Here this norm is Frobenius norm, and 2 is second norm. And also we propose one subproper splittings, which may be helpful to find the solution of multilinear system using iteration process. And we defined it as A equal to U minus B, and satisfying the U and B, A satisfies by U star N U dagger star N A equal to A, and A is u dagger u is both observed by A on pre-multiplication as well as on post-multiplication, then A equal to u minus B is called a soft-proper splitting, and we verified it that if A equal to u minus B is a soft-proper splitting, then we can express A equal to u star n I minus u dagger B. Also, if 1 is not an eigenvalue of u dagger B, in that case, A dagger, more percentage inverse of A equal to I minus u dagger B inverse star n u dagger. And if the system Ax equal to B is consistent, then every solution x satisfying u dagger ux is equal to x also satisfies x is equal to u dagger b x plus u dagger b. And this is the content of this presentation is published in the article on reverse order law of tensors and its application to additive results on Morphin inverse.
Thank you,
One can
Bani.
this article to
In
find
fact, we're going to have some questions which I'm not in a position to take up right now because of time constraints.
Yeah, any questions?
Pradeep,
Or Manjunath.
We'll say thanks to speakers.
Yeah.
And
Okay.
move on to the next session.
Yeah. Thank you very much for the nice presentation. Anyone new one is there, or is it over?
Yeah,
Manjunath?
Panigrahi, all the best.
Yeah.
I'll ask you the question to.
Okay.
Quickly.
Thank you very much, sir. Now we have another contributory talk. The speakers of these sessions are Chepuri Rajita, Kakatiya University, Warangal, India; Habibur Rahman, Pondicherry University, Puducherry, India; Harika Balledla, TSWRD, CW, Warangal, Telangana, India; Himanshu Pokhriyal, Department of Data Science, PSPH, Mahe, Manipal. I now request Dr. Vasudeva Guddettu, Department of Data Science, Prasanna School of Public Health, Mahe, Manipal, to chair this contributory session. Over to you, sir.
Thank you for the introduction. So now I request Chepuri Rajita to present her presentation. And okay, so
the system won't work that fast.
Hello. Hello.
Yes, sir. We are about to play. Yes, just a minute.
Yeah. Now I request Chepuri Rajita to present her paper.
I am thankful to the organizers for accepting my paper for the International Conference on Algebra 2020 in the memory of Professor C.R. Rao on his centenary birth year, organized by Center for Advanced Research in Applied Mathematics and Statistics, Manipal Academy of Higher Education. I am C.H. Rajita, purchasing my PhD in the area of performance study and time-dependent queuing system with a server on vacation under the supervisor Dr. L.P. Rajkumar, Kakatiya University, Warangal. Here I am to present my research paper titled An Approach in Finding Optimum Solution for a Perturbation Fuzzy Transportation Problem with the permission of the chairs, and I presented my work. My title name is An Approach in Finding Optimum Solution for a Perturbation Fuzzy Transportation Problem. Contents: Introduction, definition, numerical example, perturbated optimum solutions. Conclusion. Introduction. Decision makers play an important role and are responsible in taking strategic decisions in the expansion of an organization. Evaluation and alternative decision may sometimes turn to have a hug impact in the organization's failure. Fuzzy analysis is a study in which are related to uncertainty and vagueness and aiming at selecting the best alternative by using a step-by-step decision-making process can help to make more deliberations. In this study, we can consider a transportation problem wherein the cost, availability, and requirements are fuzzy numbers and they attributed with the alternative decisions. It is proposed to evaluate an optimum cost with an existing methods and find the shortcoming in decision making definitions. A fuzzy set of a basis set or reference set is specified by its membership function mu, assigning to each x in a degree to which x belongs to a triangular fuzzy number. If a and b two triangular fuzzy numbers, then the arithmetic operations on a and b are addition and subtractions. Differentiation. Differentiation is the process of finding singleton value which represents the average value of triangular fuzzy numbers. Here, use the August ranking to diversify the triangular fuzzy numbers because of its simplicity and accuracy. August ranking technique. The August ranking technique, which satisfies compensation, linearity, additivity properties, and provides which results consisting of human intuition. F of R represents the set of all triangular fuzzy numbers. The robust ranking function f of R integral 0 to 1 0.5 a alpha power l a alpha power u into d alpha, where alpha is the alpha level cut of the fuzzy number. Trapezoidal fuzzy number. A trapezoidal fuzzy number f a of x, it can be represented by a membership function mu of x. Robust ranking technique. If a bar is a fuzzy number, then the robust ranking technique is defined by R of a bar equal to integral 0 to 1 0.5 into a alpha power l a alpha power u d alpha, where alpha is the alpha level cut of the fuzzy number. Numerical examples. In this paper, we can take a numerical example given by reference 11 and take the numerical example. A company has 4 sources and 4 the fuzzy transportation cost for unit quantity of the product from ith source to jth destination is Cij, where Cij is 3 by 4 matrix and fuzzy availability of product at source or and the fuzzy demand of the product at destinations respectively. Then the problem become as table 1 source and destinations. We are applying supply and demands. Now solve the solution. The fuzzy transportation problem can be formulated in the following mathematical programming form. The robust ranking techniques applying these table 1 and simplifying these values and trapezoidal these are trapezoidal fuzzy numbers and solving a singleton value and robust ranking technique is applying this value and after the integrations or robust ranking of 1 comma 2 comma 3 comma 4 equal to 2.5. Now similarly we can solve this all values, rank of all supply and rank of all demands after the ranking table 2. Now after applying Vogel's approximation method from the table 3 FD1, FD2, FD3, FD4 supply and demands. These are balanced transportation problem. The transportation cost is 123.5. Now using mode method, we optimum solution as given. The optimum solutions basic cells allocated in the cell, and U1, U2, U3. Now the destinations V1, V2, V3, V4, the optimum solution is 122. Now with epsilon equal to 1.0, add basic cell, then calculate basic cell and non-basic cell. At least one non-basic cell is positive value, then the loop is involved in a basic cells. Now we assign plus theta, interchange the and theta values. We can solve this table. Then after the calculations, all delta ij is less than or equal to 0. The current solution is optimum. Therefore, the optimum solution is 1. Therefore, the optimum solution is 163. Now, with epsilon equal to minus 1.0, same as the sources and destinations, we can apply this some small epsilon minus 1.0. Now we add these basic cells and the after the calculations non-basic cells, and the optimum solution is 18.425. Now with epsilon equal to 0.5, add the basic cells, and after the calculations, the optimum solution is 125.5. With epsilon equal to minus 0.5, add the basic cells and the calculations of the transportation table. We can solve this optimum solution. These optimal solution is 100. And now add the epsilon equal to 0. From the optimum table. Now we can add the basic cells. Now consider these non-basic cells and add this. The loop is interchange the theta. U1 equal to 3, U2 equal to minus 9, U3 equal to 0, and V1, V2, V3, V4 values of the optimum solution is 119.7 with epsilon equal to minus 0.1. Sources and destinations are these loops is contained, and assign the loop involving the basic cell. Now we assign the interchange the theta values. Now the optimum solution is 116.8. Conclusions. Studying fuzzy transportation problems is considered to be of great importance due to its close connection with human life. A linear programming problem of specific structure is a fuzzy transportation problem. If in a transportation problem all parameters and variables are fuzzy, we will have a fuzzy transportation problem with the values obtained by its weighted function of model. New cost coefficients are achieved, and using Ogle's approximation method and Modi method, optimum solution is obtained. And later sensitivity analysis varying cost matrix, availabilities and requirements, optimum solution are studied. These are references. These are 9 references. Any
So thank you, Rajita, for the presentation. So quickly, can anyone have one question for the presenter? So if no question, I'll request second speaker, Dr. Habibur Rahman, to present his work.
Good morning, everyone. Today I am here to present my research work. The title of the presentation is Modeling of Computing Survival Data through Cumulative Incidence Function in the Presence of Middle Censoring. The outline of the presentation are on screen. The situation of competence arises when an individual can experience mutually exclusive type of event. For example, in liver transplantation, Individual may receive the transplant and experience the death in waiting queue. The analysis of lifetime data in the pertinence of computing is based on two approaches: first is latent value time approach and second is cause specific quantities. The following two cause specific quantities gets considerable attention in lifetime modeling. First is cause specific Hazard function, which is nothing but the instantaneous failure to a particular cause in the presence of all other risk, which is given by equation 1. Cumulative incidence function is the cumulative probability of failure to a particular cause in the presence of all other risk, which is given by equation 2. Since the all events are mutually exclusive, therefore the overall hazard function and distribution function is given by HT and FT. To represent the heterogeneity in computing setting, the Cox proportional hazard model can be plugged through equation 3. Commonly used methods for analyzing the computing survival data based on cause specific hazard function are non-parametric and semi-parametric. Advantage of non-parametric and semi-parametric inferences are they are easy to implement and free from the assumption of underlying distribution. However, parametric models are another available approach of modeling of cause-specific hazard function. If the parametric models select correctly, then they provide more robust and efficient estimate. Parameterization of cause-specific hazard function can be done by specifying some well-known distribution form for baseline hazard function in equation 3. When Choi and Gale estimate the absolute cause-specific risk by assuming that cause-specific hazard function follow piecewise exponential as well as exponential distribution. Bertrand and Dignam consider the constant cause-specific hazard function for the primary event of interest and other modes of hazard estimated non-parametrically. Jeong and Finn compared the viable cause-specific hazard likelihood estimation with direct likelihood approach by assuming improper complex distribution. Anjana and Sankaran assumed inverse viable reverse cause-specific hazard model under left censoring. Lee considered the parametric quantile inference for cause-specific hazard function with covariates. In this study, we consider the viable distribution as a baseline model through equation 4. Using equation 1 and 4, the CIF turn out in the following form given by equation 5, and it is observed that the expression in 5 is not in closed form. So to make it in closed form, we assume that all the shape parameter due to particular cause, different causes are equal. Therefore, the CIF have the following form given by equation 6. Censoring play a vital role in lifetime modeling. The computing analysis has been developed under various censoring schemes like right censoring, current status censoring, and interval censoring. In this study, we consider the middle censoring scheme, which was introduced by Jama Maladaka and Mangalam. With parameter omega 2. Let lifetime TIs and censoring intervals are independent, then the observed lifetime TI is given by yi, which is TI when actual observation is observed and random interval when censored observation is observed. Objective of the study: parametric formulation of cumulative incidence function using viable distribution in the presence of middle censoring. Obtain the point estimate by using maximum likelihood, midpoint approximation, and Bayesian methods. Obtain the interval estimates. The Bayes estimates are obtained based on informative and non-informative priors with two loss functions. Comparison of estimates based on simulation study and real-life data. Formulation likelihood function in the presence of middle censoring is given by equation 7, where delta j is the indicator function for the jth cause and theta is the all cause specific parameter set of all specific cause specific parameter. In this study, we assumed that n individuals where n1 and n2 in uncensored and censored observation respectively. It is also noticed that sum of all delta ij equals to nqj corresponding to failure due to cause in uncensored and censored observation. The log likelihood function based on assumed model is given by equation 8. Midpoint approximation estimation. In MPA method, when the actual observation is marked by the random interval, then Ti is approximated by Ti star, that is the mean of the two endpoints, and the corresponding likelihood function is given by equation 9, and the log likelihood function based on MPA method is given by equation 10. From 8 and 10, it is observed that the estimates of the parameter cannot be obtained analytically. Therefore, we obtain the estimate using numerical technique. However, the normal equation under MPM method looks simpler than the MLE. Hence, the estimator of the parameter are turned out to be more easily. For obtaining the Bayes estimate MLE for CIF, we use the invariance property of the MLE. Bayes estimation. Batch estimation. In the batch estimate, we assumed gamma prior for baseline parameter and normal non-uniform standard normal non-uniform prior for regression parameter, where Q1, R1, Q2J and R2J are the hyperparameters. We also consider the case of non-informative prior as a special case of equation 11 in a simulation study. The joint prior distribution of the non-parameters is given by equation 12. To obtain the joint posterior distribution, we use the Bayes theorem through equation 13, and it is observed that the expression of the joint posterior densities are not in the explicit form, so we use the MCMC method to generate the posterior sample. To obtain the Bayes estimate, we consider two types of loss function. First is asymmetric loss function, which is the squared error loss function and given by L1, and the Bayes estimate under squared error loss function are the posterior mean given by equation 14. Second is the asymmetric loss function, which is the line x loss function given by L2, and the Bayes estimate under LLF are given by equation 15, where phi is the hyperparameter of the line x loss function. When phi tends to 0, then the LLF is approximately equal to self. Otherwise, sign of the phi represents the degree of asymmetry. For interval estimation, we use asymptotic confidence interval, percentile bootstrap confidence interval, and Bayes credible interval. To observe the finite sample behavior of the proposed estimation, we consider a Monte Carlo simulation study. For simplicity, we consider two causes of failure and one single covariate x is generated from the standard normal distribution, and we assume three types of censoring proportion: 10%, 20%, and 31%, by assuming different values for omega 1 and omega 2. In order to compute the hyperparameter, we use the likelihood estimate, and for non-informative prior, we assume the hyperparameter are close to 0, and for regression parameter, we assume normal non-informative prior. The hyperparameter of line x loss function is fixed at plus minus 1.5. We consider for sample size 20, 50, 100, and 200. The whole process is repeated 500 times. The comparison of the estimates is made based on MSE, average length, and coverage probability. These are the simulation results of my study. For fixed censoring proportion, as the sample size increases, MSE decreases for MLE, MP, and Bayes estimate under both the brackets, which verify the consistency property of all the estimator. As expected for small sample size, Bayes estimates performs better as compared to MLE and MP estimate. It is observed that for fixed censoring proportion, average length for all the confidence interval are decreases as sample size increases, and most of the cases CP are very close to the nominal level. For fixed sample size, the average length of all the confidence interval is increases as censoring proportion increases except for some values. Moreover, we observed that the credible interval based on informative prior are better than among the interval estimate in terms of average length and coverage probability. Real life application. We analyzed liver transplant data from between 1974 to 1984. In this 10-year study period, a total of 424 patients are enrolled in the study, in which 312 patients were randomized to receive depenicillamine and placebo treatment. In the end of the study, 161 patients died, another 25 patients were received the liver transplant, and 232 patients were lost to follow-up. For the analysis purpose, one single covariate treatment is considered, which verifies the proportionality of the hazard in figure 2. For checking the goodness of it, we use the Kolmogorov distance formula for fitted model and empirical, which is the distance is 0.0331 and the corresponding p-value is 0.737, and which indicates that the model cannot be rejected for this data set. Figure 1 shows the graphical fitting of the viable distribution for this data set, and figure 2 is the Anderson plot for checking the proportionality assumption of the treatment for both the transplant and death. Next, we have created an artificial dataset by material censoring, whose left end points as the observed time itself. The width of interval is generated from exponential distribution with mean 10. Then all the censored individuals are considered as the middle censored observation. The computing outcome variable for middle censored observation are randomly assigned from the death and transplant. We applied the proposed method of estimation to obtain the point and interval estimates of the known parameters and CIF. The result of point and interval estimates of unknown parameter are presented in table 1, and the result of CIF for is given by figure 1 for transplant and death. Conclusion. In this study, we consider the modeling of cumulative incidence function using viable cause-specific proportional hazard model in the presence of middle censoring scheme. Both classical and Bayesian approach are utilized for obtaining the estimates of the unknown parameter and CIF. The simulation study shows that the Bayes estimates based on informative type perform well as compared to other estimates in terms of MSE and average length and coverage probability. All the estimator verified the consistency property in simulation study. For compared dataset goodness of fit criteria provided the viable model good fit to the data. Covariate treatment hazard assumption of the model. These are some references. Thanking you.
Thank you, Dr. Rahman, for the presentation. Quickly, can we have one question? Yeah. So if no questions, then I request next speaker, Ms. Harika Balleda, for her presentation. I think audio is muted. Hello. Audio ಬರ್ತಾ ಇಲ್ಲ ನಯನ್.
Yes, sir. We are trying to do it.
Okay. Sorry, there was a technical error. They are trying to sort it out.
Vasudev,
Sir.
can you hear me?
Yes, sir.
What we do is entire next session shared by Srimati Maya will be adjourned to tomorrow. Now this will complete it properly. Okay, after correcting this error.
Yes, sir. Yes, sir. Yes, sir.
Okay.
Yeah, thank you, sir. Yeah.
Vasudev, can you hear me?
Yeah, yes, sir. Yes, sir. I can hear you, sir.
Okay, my speaker was mute. Okay, we'll sort it out and we'll complete the session in this particular day itself right now. Okay.
Yes.
We'll make appropriate announcement on rescheduling the next 1 hour session, whichever is has been chaired by Professor Maya.
Dr. Maya.
Good morning. Myself, B. Harika. I am doing.
Dear all, there was some technical glitches. So we are replaying the current presentation once again, with the permission of the chairperson. Sir, Vasudev sir, can we do the?
Yes. Yeah, we can continue. Yes.
Yes, sir. Thank you. The presentation is continuing.
Research under the supervision of Dr. L.P. Rajkumar sir. Today I am going to give a talk on generalized triangular and symmetric splitting method for steady state probability vector of stochastic matrices. Contents: Introduction, fundamentals of stochastic matrices, generalized triangular symmetric splitting method for steady state probability vector of stochastic matrices, and finally references. Motivation. Nowadays, internet traffic is rusty in behavior. One of the major challenges for traffic engineers is internet traffic. Based on the performance measures, one can conclude the quality of services and stability criteria. Research philosophy. The switch or router is modeled as queuing system, and we can find out the steady state probability vector by using the matrix geometry techniques. And after finding the steady state probability vector, we can find out the performance measures, and based on the performance measures we will conclude the quality of services. And after finding the quality of services, one can dimension the switch or router. Fundamentals of stochastic matrices. Markov modulated Poisson process has been used for modeling of aggregate voice sources and video sources. This model is a doubly stochastic Poisson process where the rate process is determined by the state of a continuous time Markov chain. The Markov modulated Poisson process is characterized by infinitesimal generator Q of the underlying Markov process and the vector lambda of the arrival state. The matrices Q and big lambda are given as follows. The mean arrival later lambda of Markov modulated Poisson process is given by lambda equals to pi big lambda E, where pi is the steady state probability vector of Q. The steady state probability vector pi of Q satisfies the equations pi into Q equals to 0 and pi E equals to 1. This diagram represents the transition diagram of an end state Markov modulated Poisson process. Coming to our problem, the generalized triangular and symmetric splitting method for steady state probability vector of stochastic matrices. In most of the cases, when the network nodes are modeled as queuing systems, the problem of computation of performance measures is reduced to that of steady state probability distribution vector of transition rate matrix or transition probability matrix. Therefore, it is a key importance to investigate the pertinent linear systems. The significant improvements in convergence rates can be achieved from the Krylov subspace methods, two-splitting and multi-splitting iterative methods. The alternative methods, namely Hermitian and skew Hermitian and positive definite skew symmetric methods, which converge unconditionally to the unique solution of the system of equations. Moreover, the triangular and symmetric iteration method has been developed and discussed for solving the positive definite linear system of stochastic matrices. Here, P is the stochastic probability matrix. If sum of each row in P and sum of each column in P is 1, then this matrix is also called as doubly stochastic matrix. The steady state probability, the steady state distribution vector pi satisfies the equation pi into p equals to pi. That implies pi q equals to 0, where q is the matrix. In this matrix, if each row sum and each column sum is 0, then q is doubly stochastic rate matrix. Some of the definition related to our talk. Any matrix A belongs to R power n cross n of the form A equals to Si minus B, S greater than 0, B greater than or equals to 0 is called an M matrix if S is greater than or equals to spectral radius of B. If S greater than spectral radius of B, then A is non-singular M matrix, otherwise A is singular M matrix. A non-symmetric matrix A belongs to R power n cross n is M matrix if its symmetric part A plus A transpose by 2 is M matrix. A non-symmetric matrix A belongs to R power n cross n is positive definite if its symmetric part is positive definite. The coefficient Q of the equation 3.2 has one-dimensional null space. Thus, triangular symmetric iteration method cannot be directly applied to solve the linear system. So we go for a regularized linear system, which is in the form of A bar x equals to 0, where A bar is Q transpose and x is pi transpose. Then there exists a non-negative constant epsilon greater than 0 such that the above equation can be converted to the preconditioned linear system Ax equals to En, where En is the unit vector. Lemma. A stochastic rate matrix Q belongs to R power n cross n is a matrix for any non-symmetric stochastic rate matrix Q belongs to R power n cross n where there exists a constant epsilon greater than 0 such that A equals to Q transpose plus epsilon In is positive definite if all its real eigenvalues are non-negative. This theorem is very useful in finding the convergence criteria of the triangular symmetric iteration method. Consider the coefficient matrix A equals to D plus L plus U. This is the schema which we were used to solve the problem, where D is the diagonal matrix with the diagonal entries and L is lower triangular matrix and U is the upper triangular matrix, where D is defined like this and L is defined like this and U is the defined like this. The triangular and symmetric splitting method is generalized on the regularized stochastic matrix as follows. That means A is splitting as triangular and sum of triangular and symmetric matrices. That means we can also written as A equals to T plus S, where T is the triangular matrix with the non-negative diagonal elements and S is the positive symmetric matrix with the positive diagonal elements and negative off diagonal elements. To find the solution of the regularized linear system, we can use the iterative method described. We will guess the initial value x0 and we will calculate the next approximations by the following scheme. We will continue this process until x power k converges to for any positive constant alpha. The above iterative scheme can also be written as in this format. This is the iteration matrix of the triangular symmetric iteration method. M of alpha is the iteration matrix of the triangular symmetric iteration method and n alpha equals to like this. If the spectral radius of m of alpha is less than 1, then the iteration method is convergent. We assume the lemmas 3.3 and 3.4 from the paper. This paper is a reference list. Let W of alpha equals to alpha I minus T into alpha I plus T whole inverse. If T belongs to R power n cross n is a positive definite matrix, then we have 2 norm of W of alpha less than 1 for our alpha greater than 0. If the matrix S is a symmetric part of the coefficient matrix A of the regularized linear system 4, then there exists epsilon greater than 0 such that the matrix S is positive definite. We prove the following lemma 3.5. Let H of alpha equals to alpha I minus S into alpha I plus whole inverse. If S belongs to R power n cross n is a positive definite matrix, then we have 2 norm of H of alpha is less than 1 for all alpha greater than 0. 3.3 and 3.4 are previously proved in some other paper. Here we will prove lemma 3.5. The numerical results also not discussed here, but we will find out the numerical solution for steady state vector using the triangular symmetric method, and after calculating that we will compare with the other existing methods. Therefore, the convergence rate of triangular symmetric method is very fast when compared to other previous existing iterative methods. Finally, my conclusion is, in this problem, we present generalized triangular symmetric splitting iterative method for the regularized matrix of the system of stochastic matrix. We proved that the regularized matrix is positive definite under specific condition. We conclude that this method unconditionally converges to a unique solution and the convergence rate is rapid when compared to other existing methods. And these are my references. Any queries or suggestions? Thank you.
So thank you, Harika, for the presentation. So can we have quickly one question for the speaker? So if no questions, then I'll invite next speaker, Dr. Himanshu Pokhriyal, for presenting his presentation.
Good morning, everyone. My name is Himanshu Pokhriyal. I am Assistant Professor in Department of Data Science, Prasanna School of Public Health, Manipal Academy of Higher Education, Manipal. Today I'm going to present my work on testing for measurement error in regression with autoregressive innovations. This is a joint work with Professor N. Balakrishna from Cochin University of Science and Technology. This is the outline of my presentation. We will start with the introduction to the problem setup. Then we see how the test was obtained, which is followed by some simulation study and conclusions. So first of all, let's consider the multiple linear regression model with k independent variables given by equation number 1. The error sequence ET is assumed to follow a stationary autoregressive process of order P given as ARP and given in equation number 2, such that the roots of the polynomial phi b lie outside the unit circle, and the sequence AT is IID with mean 0 and variance sigma square A. We analyze the regression models given in equation number 1 and 2 when there are measurement errors in the response as well as in the regressor variables. So suppose that we observe the surrogate instead of the true variable or the true regressor variable xjt. So we are observing wjt instead of the regressor xjt, and we are observing surrogate rt instead of the true response variable yt for all j equals to 1 to k and t equals to 1 to n. So assuming the additive structure, we can write the forms of these wjt and rt as equation number 3 for all j equals to 1 to k and t equals to 1 to n. So here the sequence uj, t and the sequence vt are the measurement errors such that ujt's are IID with mean 0 and variance rho j sigma square a, and vt's are IID with mean 0 and variance rho naught sigma square a. So note that rho naught and rho j's for all j are strictly greater than 0. When they are equals to 0, that means the model has no measurement error in the scenario, and then further for all UJTs and VTs are independent of XT, ET and AT sequence. So in this paper we consider the testing problem. We test the null hypothesis rho naught equals to rho 1 equals to and so on till rho k equals to 0 against the alternative rho j greater than 0 for at least one j equals to 0, 1, so on till k. So if you see here under h naught, there exists no measurement error either in response or regressor variable, whereas h1 indicates the presence of measurement error. Now using equation number 3, the model given in equation number 1 becomes equation number 4, and bt is given in equation number 5, also known as the composite disturbance term. And if you see carefully, this bt is the sum of an ARP process ET and the linear combination of white noise given in equation number 6. Granger and Morris and Hamilton have already shown that the sum of an ARP process and a linear combination of white noise error series results in an ARMA PV process. Using the same result, equation number 5 can be written as equation number 7, So if you see, BT here is now an ARMA BP process given as phi b BT equals to theta b epsilon t. Phi b and theta b are both pth order polynomials given as such, where epsilon t is a sequence of IID random variables with mean 0 and variance sigma square epsilon. Here the parameters theta1, theta2, theta3 and so on till theta p and sigma square epsilon can be determined by solving for the variance equations of both sides in equation number 7. So we have equation number 7 and we solve for the variance of this equation and then we get equation number 8. And then comparing the coefficients of the Bakshchev operator B on both sides, we can get the estimates of, or we can determine the parameters theta1, theta2 till theta p and sigma square epsilon. So in order to proceed with the estimation and then the testing of hypothesis problem, we make the following assumptions. The first assumption is about the stationarity and invertibility of the ARMA PP process, and the roots of polynomial phi b and theta b should lie outside the unit circle and they should not have any common roots. The sequence AT are assumed to be normally distributed with mean 0 and variance sigma square a. The sequence UJT are assumed to be normally distributed with mean 0 and variance rho j sigma square a. The sequence VT are assumed to be normally distributed with mean 0 and variance rho naught sigma square a. UJT for all j and VTs are independent of each other and are also independent of AT for all t. So from assumptions 2 to 5, it follows that epsilon t is a sequence of IID normal random variables with mean 0 and variance sigma square epsilon. So finally, we can write our model as equation number 9. If you see, equation number 9 is now in terms of the surrogates instead of the true values, which can further be written as ARMA PP representation given in equation number 10. So the log likelihood of the parameter theta for the model 10 is given in equation number 11, and the partial differentiation of this log likelihood value with respect to the rho j's under h naught can be computed as summation I equals to 1 to p. So if we first differentiate the log likelihood with respect to theta i's and then we multiply it with the differentiation of theta ith with respect to the rho j's under h naught. It's given in equation number 12. So hence under h naught, del L by del rho naught under h naught is given in equation number 13, and for all j equals to 1 to k, del L by del rho j under h naught is given in equation number 14. So the LM test statistics takes the form under h naught as equation number 17. So we have the test statistics T naught. So under h naught, T naught converges in distribution to standard normal variable as n tends to infinity, and it rejects h naught for large values of T naught at alpha level of significance. Note that the LM test statistics obtained in equation number 17 is free of the estimates of regression coefficients of the original model. It depends on the autoregressive parameters of the error sequence given in equation number 2 and the variance of the measurement errors in both response as well as regressive variables. Now we come on to the simulation study. We investigate the performance of the test by simulations for various parameterizations of the model. For illustration purposes, we consider a simple linear regression, y2 equals to 1.5 xt plus et, where the innovation sequence takes one of the following forms. Model 1 is a AR1 representation where the AR coefficient can take any one of the three values 0.9, 0.5 and 0.1. Model 2 is an AR2 representation where the combination of phi1 and phi2 can take any one of these three forms, and AT is taken to be a standard normal random variable. Now if you see, the AR coefficients are taken as such that the AR process is stationary in both model 1 as well as model 2. So here the regressor xt is fixed and generated from a normal distribution with mean 550 and variance 0.5. For every combination of models, we study the power performance of the proposed test for sample sizes 50, 100, 250 and 500. We repeated the simulations 5,000 times for different sample sizes. All the computations were carried out in RStudio Cloud platform. Now table 1 presents the power performance of model 1 for different values of autoregressive parameters phi1. It is seen that as rho 1 increases, the power increases for fixed sample size n. For higher values of phi1, the power performance of the test is much better than when phi1 takes smaller values. So when phi1 equals to 0.9 or 0.5, the power increases as n takes larger values, although the power decreases when phi1 is equals to 0.1. Similarly, for model 2, table 3 represents the power performance of the LM test. Here again, as rho 1 increases, the number of rejection increases for fixed n. For fixed rho 1 and varying n, the power increases as n takes the larger values. Table 2 and table 4 represent the power performance when the measurement error is present in both response and regressor in model 1 and 2 respectively. As rho 0 and rho 1 increase, the proportion of rejections increases. The power performance of the test was reasonably good and promising in detecting any presence of measurement errors. So these are the conclusions. These are some of the references. Thank you. Thank you for listening.
Sir, was it sir? Sir, because of the technical issues, the next session has been postponed to tomorrow. We will be announcing the time in no time. One contributory talk from the next session would be happen now. Will be played right now. That is a contributory talk by Dario Ferraria from University of Beira Interior, Portugal. I request Dario Ferraria to switch on the video and ready for question and session. Now we'd like to play the video. We request Vasudev sir for permission.
Yeah, I can continue. Yeah.
Thank you. Yes. It's okay. It's okay. Thank you. Hello, my name is Dario Ferreira, and the title of my presentation is Sums of Squares and Prime Factorial Designs. This is a joint work with Professors Sandra Ferreira, Célia Nunes, and João Tiago Mexia. We are all from Portugal. This is the outline. So, prime factorial designs are P up to n designs where P is a prime or a power of a prime. This kind of models are very common in industrial experimentation. The most of such experiments use two-level factors, but experiments with a larger number of factors are also quite common. The advantage is that these models allow the simultaneous study of a larger number of interactions compared to classical approaches. A disadvantage is that the procedures for obtaining the sums of squares can be a bit cumbersome. So, the goal of this presentation is to present a recurrence way for obtaining the sums of squares in order to alleviate these difficulties. The method may be applied to cases with any number of factors and levels, even when it's neither a prime or a power of a prime. We illustrate the method with an example. So, in what follows, we will use mode R arithmetic, where the numbers wrap around when reaching R, and we denote A plus B in mode R arithmetic by this way. So, consider a model with U factors, P prime levels, then we will have P up to U treatments. With XH, the level of the H factor, the treatments may be represented as we have here. So, we have the linear function represented in 1. Note that there are P up to U of these functions, of which QU are reduced. We say that a function is reduced if the first non-null coefficient is 1. Let Li be a reduced linear function, Ai be the vector of coefficients of the ith reduced linear function, and Jx be the index of treatments x. The functions in Li are ordered, coming first x1, then x2, then x1 plus x2, and so on until we have this. These functions constitute the LIP square functions. Going forward, we will have LP plus 1x, which is x3, and then the other functions of LIP up to 3. The indexes of these functions are obtained by adding this to the index of this function. We'll now consider recurrence relations. So we'll associate PU with a KU times PU matrix whose row vectors are associated with the functions of LIPU. Let's say that it's BU. So B1 will be this function. BU plus 1 may be written as we have here, where all the sub-matrices are KU times PU, except this second, which will have one single row. It may be seen that the first matrices in the first row will be equal to BU, and that the one in the second row, which will be that matrix with only a single row, will be equal to this product. So we may write BU as we have here. Now let's define delta B VR, which will be a vector with all components null except the ones with value V in the rth row of a certain matrix B, which will be 1. So to exemplify, let's consider matrix B as we have here, and so delta B01 will be 1, 0, 0. Why? Because we have to look for 0 in the first row, where 0 is here, so we'll have here 1, and the remaining positions will be 0. In the same way, we'll have delta B12 is 0, 0, 1, because we'll have to look for the 1 in the second row. So whereas the 1 is here, so we have here 1, and the remaining positions are 0. Now we can associate this kind of matrices to the functions. So we'll have these matrices. It may also be shown that the sum of squares associated to that functions are given by this product, where AI is this product and CP is obtained by deleting the first row of a J times P orthogonal matrix. We have an example where we consider a T up to 3 model. The data is presented here in this table. So in this case, we'll have 13 reduced linear functions. Matrices BU will be, well, for B1, we'll have 0, 1, 2, and then for B2, we will have here 0, 1, 2, it's B1, B1, B1. This the row or the matrices with a single row, and here this matrix is obtained by summing. For example, here we have 1 plus 1 is 2, and 2 plus 1 is 0 in mode 3, of course. Finally, B3 is represented here. So here, this is B2, B2, B2. This is that matrix with a single row, 0, 1, 2. And here, for example, we have 1 because we are summing 1 plus 0 is 1. Or here we sum 1 plus 1 is 2, and so on. So from 12, one may obtain, for example, that delta B matrices. For example, here for the first row, for Bx1, we'll look here in the first row of this matrix. So for the first row here, we look for 0. Then here we look for 1, and here we look for 2. So where's the 0? It's in this position, in this. The 1 is in the second position. The 2 is in the third position. So here we have 1, 0, 0, 1, 0, 1, 0, 0, 1, and 0, 0, 1, and so on. Now, if we consider these matrices, we may write the matrices B as we have here. Now, considering this orthogonal matrix, we obtain C3 by deleting this first row. And then, using 13, we may obtain the sum of squares. So here we have the table with the decisions, with the 13 linear functions. X1 is for factor 1, X3 for factor 3, and here we have interaction between factor 1 and factor 3, and here another part of the interaction of factor 1 and factor 3. So we do not reject, we reject. If you want to obtain the sum of squares obtained by the ANOVA, by the usual techniques, we just have to consider, well, for the single factors, they are the same. If we have the interactions, we just have to sum, for example, interaction and between factor 1 and factor 3. We sum these two. Here it is. And here we have the table using ANOVA just to confirm that the sum of squares may be obtained this way. So note that if we use ANOVA, we reject the null hypothesis for interaction 1, 3 between factor 1 and factor 3, here reject, but using the prime basis factorial method, the null hypothesis corresponding to function x1 plus 2x3 is rejected, as we saw, but the null hypothesis corresponding to function x1 plus x3 is not rejected. So, as final comments, I can say that prime factorial designs allow the simultaneous study of a larger number of interactions compared to ANOVA, but if wanted, the classical sum of squares can be easily obtained. The procedures for obtaining the sum of squares can be a bit cumbersome, and we presented a recurrence way for obtaining the sum of squares for cases with any number of factors and levels in order to lighten the calculations. So here are some references, and thank you very much.
Vasudev.
Yeah, I'm audible, sir?
Yes, sir.
Yeah. So I'll thank all the speakers of the session, and I'll thank all the organizers for giving me opportunity for chairing the session. So over to you, sir. Yeah.
Thank you, sir.
Vasudev?
Yes, sir.
Can you see my screen now?
Yes, sir, I can see.
Okay, I like to describe the audience how I have changed the schedule. Today, we are not able to continue with the next schedule properly. We are changing it. So this is revised tomorrow. The morning session starts as it was planned earlier, but here one particular session will be shifted, and we inserted today's whatever in this particular Professor Srimati remains to be chair of that particular session, and Azade Cesare Ford, Pandam Ravindra Reddy, Lintu MK. Those three will be delivering their contributed talks in this particular session at 16:55 to 17:35. Vasudev?
Yes, sir.
Vasudev?
Yes, sir. Yes.
Am I with you?
Yes, sir. You're audible, sir.
But he could see it earlier. Also, you could see the screen earlier?
Yes, sir. Yes, sir. I can see.
So,
It is visible.
Yes, sir. It is visible, sir. Yeah.
Schedule is visible.
Yes.
Vasudev, am I audible?
Yes, sir. You are audible, sir. Yeah.
Okay, this is a change I made. Today's session which we couldn't has been rescheduled for 16:55 to 17:35, and rest have been accordingly. Okay. I request those three tomorrow's speakers to make note of this, and will also mail the same thing to all. Thank you.
Dear all, we'll be resuming back exactly by 3 o'clock. We just have only 1 minute left. We'll be back in a minute.
Now, there will be an invited talk from Professor Dietrich Rosen and Professor Arup Bose. Professor Dietrich von Rosen is visiting professor at Swedish University of Agricultural Sciences, University in Uppsala, Sweden. He will be deliver a talk on discrimination of growth curves. He is one among the people who greatly inspired by Professor C.R. Rao's book on linear statistical inference and by his talk at Tampere University, Finland. Another speaker, Dr. Arup Bose, is a professor from Indian Statistical Institute, Kolkata. His topic of presentation is Modeling COVID-19, a dynamic SIRD with application to Indian data. He is a Shanti Swarup Bhatnagar awardee in Mathematical Sciences, CSIR Government of India in 2004, the most well-known yearly scientific honor for Indian scientists below 45 years. We are happy to have you with us, sir. I request Professor Agustin Markewicz, Professor of Poznan University of Life Sciences, Poland, to chair the session. Over to you, sir.
So let me open the session, and as you talk at the beginning, the first speaker is Professor Dietrich von Rosen from Swedish University of Agricultural Sciences in Uppsala, Sweden. And his research interest is covering mathematical statistics, regression analysis, probability and statistics, but first of all, multivariate analysis. I met first Dietrich 36 years probably ago in 1984 at the conference on linear statistical inference held in Poznan. And from this time we have a lot of collaboration, and recently Professor Dietrich von Rosen is a very active member of research group on mixed and multivariate linear model, and the meetings are held twice per year, and last meeting was held in the beginning of November, and also in this so-called hybrid form. And Professor Dietrich von Rosen will present a topic on his favorite, probably problem, I mean multivariate analysis. And as you thought, the title of his topic is on discrimination of growth curve. So Dietrich, screen is yours.
Okay, ladies and gentlemen, I'm very proud to participate in this conference in honor of Professor C.R. Rao. And C.R. Rao has in fact been an old hero to me, and he was very important for my why I entered this or the research. I became a scientist, because in Sweden we have a lot of coursework which we have to do as a PhD student. And there was an occasion where I was studying his book on linear statistical inference, and this became a very important book to me, and I really enjoyed the topic. I started at that time from chapter 4 and went up to chapter 8. And another thing, connection in my background as a PhD student was a conference in Tampere in Finland, where Professor Rao and George Steyan were the main speakers. And it gave a very interesting impression of what science is. And I remember the talk by C.R. Rao, it was about generalized inverses, and in particular geometry, I remember he was talking about. So today I will talk about a very classical topic. It's about classification, and I will discuss the classification of growth curves. It has been on, I think, a very old topic by Professor C.R. Rao. He has a lot of contributions to it on various levels over 50 years. So I'm happy to share my results now here in this forum. So this is a joint work also with a colleague and friend, Martin Singel from Linköping University in Sweden. So if you look at background a bit on discrimination, classification, it's one of the earlier topics in statistics. And there are three names, I would say, this from the beginning. It's Carl Pearson, Mahalanobis, and Fisher. And definitely Mahalanobis and Fisher had good connections with CRO. So more than 100 years ago, Carl Pearson discussed about sexing bonds. And so they have, say, two populations, and you want to see if the bonds come from either one or the second population. And it's in some ways about the mixed populations, and then you have to classify new observations. So after a while, he also introduced the so-called coefficient of racial likeness, and CRL. And this was in practice for a long time, but it was also criticized. In particular, there was the coefficient depended on the number of observations collected. And I think this was the reason why Mahalanobis introduced the distance between populations. And Mahalanobis' work had a great impact, I would say. And one can read about it in a paper by Mahalanobis by himself, 49. But there's also a nice summary of Mahalanobis' work by Dasgupta, 93 in Sankhya. And in particular, I saw that he was referring to an old conference in London, 1911, where Mahalanobis participated. About discrimination in populations, which was a fashion in the beginning of the statistical era, then the idea about testing, the significance test came up, and Hotelling started to discuss it when you had dependent variables, or you can say you can have it repeated measurements on individuals, and then you have samples from two populations, and you want to compare these samples, and then you can do it in a formal way by statistical testing. The discriminant function and distances, it's a bit different because we don't have a null hypothesis there. We have two alternative hypotheses, usually. And Fisher, 1936, constructed a so-called linear discriminant function. And this has been in use for a long time and has inspired enormous amount of others to continue the work. And today we're going to talk about the classification of growth curves. And growth curves means that you have repeated measurements and you have observations on individuals from the same time points, for example, age 0, 2, 4, and 6 here. So there will be 4 repeated measurements, and then the population follows some kind of mean structure. And here we have two populations, denoted pi 1 and pi 2. And then we have a new observation, X, which we want to classify as coming from either pi 1 or pi 2. And the problem started, it was discussed already in the 30s, and in particular Barnard and used some kind of regression to discuss this problem. And what is important also, why I highlight this 1 and 2 here, is that regression and growth curves are connected. But there was also by Professor Rao a discussion that when you discriminate or classify observations, it can happen that the observations come from some kind of unknown population. And this we will focus on a bit today. And later multivariate analysis became really fashion in the 50s, and then you mostly was focused on testing. But this is a testing between groups or mean levels. Then in the 60s, growth curve returned a bit more, and there is a so-called growth curve model which was introduced by Potthoff and Roy, 64, but there were many authors, or several authors at least, who had discussed the growth curves before in particular Professor Rao here in some papers, where also the classification problem was mentioned. If we, from the classification of growth curves, there is or not of growth curves, but connected to growth curves, there's an interesting paper by Burnaby, 66, who in some way discussed some kind of geometrical approach to the classification, maybe very inspired of Fisher's early works. But the point here was to adjust for the growth. So he didn't want to classify the growth curves by himself, but he wanted to classify some kind of treatment, or not treatment, but effect when you reduce the growth curves effects. And very close in age, and Professor Rao was also involved in, say, classification of growth curves. And in fact, also, if you look in the paper by Burnaby, he's referring to some communication with Professor Rao. Later, you can see there was it's Shirsagar and with colleagues who has been studying classification of growth curves for many years. But there's usually some kind of testing going on. So he relates it to canonical correlations, and this is also classical work where he, say, turns the testing problems into a classification problem. We have a Bayesian approach, and I would, if I should mention one, it's Jack Lee, who has several papers on classifications, and where you can see really that you use a posterior distribution when classifying. But otherwise, there's also a huge literature on classification, and in particular a book by McLaughlin here from 2004 can be recommended. But very little is one can find about the growth curve classification. And if you go into these bigger or classical multivariate books, oh sorry, misspelled here, should be Srivastava. These books here, they include all classification, but not the classification problem of growth curves. And is there anything new in classification of growth curve? Yeah, maybe. We'll see how one can think. And then there is a modern literature in, say, connected to so-called data mining, etc., and artificial intelligence, maybe also. I'm a pretty orthodox person. I think most of that literature is not about statistics. So I haven't considered and I haven't followed up it very careful what's going on. But of course, there are ideas how to classify data. But the connection to distributions is pretty vague, I would say. So now we're going to talk about the classification of growth curve, and I'm going to introduce you here some notation and the growth curve model. So the growth curve model is given here. And what does it stand here? Now we have an X of our matrix of observations, or the random variables corresponding to observations. We have a mean structure given by 3 matrices, and we have an error matrix. And the error matrix is matrix normally distributed with parameter sigma and a constant identity matrix. And this means the identity refers to that the columns in X are independently distributed. And the dispersion matrix sigma, which we suppose is positive and definite, describes the dependence among the objects in one column. So independent p-dimensional columns with the covariance matrix sigma we have. And we suppose that everything is normally distributed. So this is a usual error term in MANOVA or in many linear models. If you look at the mean structure, we have these 3 matrices. And there's A is a design matrix, and you usually call within individual structure individual structure and this design matrix. And it models the repeated measurements within an individual. And then we have C, which is a between individuals design matrix. And here you model treatment groups and in particular treatment groups. And it models the independent observation and if there's some kind of design behind it. This model belongs to the curved exponential family, which is interesting. But the interesting thing is that you can find explicit maximum likelihood estimators. And here the maximum likelihood estimator for B is given. Also we write ABC because I don't assume any full rank conditions here. So this is the mean, but this is a maximum likelihood estimate of the mean structure. And then as you can see, here you have X, here is a linear function, and you can say that this is the averages, if you want. And here you have an S weight matrix, which also is a random matrix, so which are distributed in fact. And this is used as a weight here. And then we see that this estimator, which is an explicit maximum likelihood estimator, is nonlinear. And also its distribution is complicated to handle. And then we have the estimator, the maximum likelihood estimator of the dispersion matrix. And this is given here. And you see this is S's which are distributed, but this is a very complicated expression, what is given here. Because you have S inverse here, and you have X here. So if you look at the model here, just for the growth curve, is that you have 4 repeated measurements here at age 0, 2, 4, and 6. And then you have a mean, which is indicated with the red. And then there will be some variation around it here also. More important here is the classification of our growth curve. So we have our 2 populations, we have a new observation, and we want to decide where to put that observation or where to classify it. So then we go over to some technical, and we want to apply a maximum likelihood approach. And what we want to do is we have 2 likelihood ratios or likelihood, and we will put them into a likelihood ratio. One is when X belongs to the first population, and another is when X belongs to the second population. If X belongs to the first population, we have the models described in this way here. And that means that we have X1, it was the sample from the first population, and then we have added the new observation which will be classified. And then we have a model. We suppose that they have the same mean structure given by A, but you can see here this one vector is one for each independent observation, and since we have n1 plus 1, we have added 1 observation, and we suppose here that n1 we have n1 observations from population 1 and n2 observations from population 2, and then we see that the means are different from the populations. So this model here describes the situation when X equals population 1. If X equals population 2, we have this model here, where instead of X1, we have X2, we have beta 2 here, was here, and then we have beta 1 here, and then we have this the same error matrices as here. But we have 1 more observation. We can put all things together, and then we create the matrix X, which consists of the X1 from population 1, the new observation which will be classified and X2. And then depending on which situation we are in, we have 2 design matrices. And we'll get 2 weight matrices, S and S under tilde here. So under the assumption that X belongs to population 1, we have a maximum likelihood estimator of this form. For sigma, and then we have this S is here, whereas if X becomes from population 2, we have an estimator of this form, where an S under tilde is given here with C2 here instead of C1, which was here. So the classification goes on that we take the likelihood ratio of these two estimators and have the determinant. It comes from the normal density, and then we just inserted it. Of course, it's not exactly likelihood ratio because we have removed this minus n½ here and something more. But it turns out to be like this here, equivalent. And then one can manipulate the ratio here so that we get a ratio which ends up in two ratios. And we see that we have S and S under tilde here, and we have something AO times S, AO transpose S AO. And AO is any matrix which generates the orthogonal complement to the column space generated by A. Now to do the derivation, probably need to manipulate a bit. And then one can see that we will define two sums of squares matrices in this way. And this is just based on for the first observation, the usual sums of squares matrix. And this is for the second samples. And here are not, or X, which is to be classified, is not involved. And then we have the total sum of squares without X, and this is given here. And we call it S1, 2. Which are distributed as here. And the important thing is that our sums of squares matrix, S and S tilde, are function of this S1, 2. And in fact, they have this structure. So they require some manipulations, but where we explicitly see how these C matrices are, but it comes out like this. And then we can see, if you look at the first ratio, or in the likelihood ratio, is between the determinant of S and the determinant of S under tilde, that will end up in a relation of this form. So what we have done is just to take out S1, 2 here in a nominator and in a denominator, and then we flip around a bit and come to this ratio. And the same we can do for the second ratio, which is given here. And it's a bit more complicated, and I will not go into details, but you can see you have one part here, and then you have another part here, and this part is in particular involved in the with the structure through A. But it comes out that if you look at them, and this part here, for example, the under part, it can be written, it has the same structure. So it means that this here will cancel out towards this field. So what we end up in is the likelihood ratio, which is H1 divided by H2. It's given here and here, but we are not going to work directly. Of course, we are interested if this ratio is smaller than 1 or greater than 1. But we are, this is still pretty much complicated. The information is relatively complicated here to see. So we simplify it a bit. And then we form a ratio. We know, for example, if lambda should be less than 1, then H1 should be less than H2. And then we can form this quantity instead of the quantity here. And here we can see that L1 divided by L2 is a function involving the structure A here. And here is and the function is just a comparison of the means. So the averages in each time point is compared with the observation for the in X, which is to be classified. And then you can view this here as some kind of distance, or we can call it even an empirical version of Mahalanobis distance on a certain condition. And the different samples here, which you can see N1 over N1 plus 1 and N2 and is exactly what we want to do, because if you take the square root here of this here times this here, the dispersion will equal sigma. And here also, because you're waiting with this here, the dispersion will equal sigma. So the ratio in sum does not depend on the number of observations here. And then and something similar here also for L1 and L2. We can manipulate this L1 over L2 a bit, and then we can see that the estimated mean structure will be compared to a projection on the A matrix with this weight, and we look at the difference here from the MLE with what happened to this particular observation, which is to be classified, and then we have created a distance. So our proposition is here now that if you want to classify an observation X into pi1, there should be two conditions satisfied. The first condition is that the observations should be close to each other from an average without any model, some kind of fitting, goodness of fit, we can say we have here. And then we look at the second point on the structure. What is a bit special here is that when we want to classify, because we want to have the ratio less than 1, we can have a constant CO, which depends on on these observations here. So to summarize here, we classify X into pi1 if 1 and 2 are satisfied, and X is classified into pi2 if no one of 1 and 2 are satisfied. And then we classify X to belong to an unknown population if only one condition is satisfied. And we can see we have some scenarios here. We have these growth curves, we have this observation, and then we have to decide where to classify. The same here, if you would have an X here, which should be classified, it's in somewhere pretty close to the first population, but the growth here is very similar to the second population. So we really don't know, I think, where to put it. And the same, here we can see, this has a growth which is very similar to the second population, but it seems to be pretty far away still. Also, here it's closer to that population than this population here. So if we just would compare averages, this would be classified here, but it's still maybe not so that it belongs to this population. And here we have that nothing is pretty clear that this X doesn't belong to either pi1 or pi2. So now we saw here that there was a problem, and even if we have a strategy that two conditions should be satisfied, one can show that this is in some way not enough. So we have to look at this individual parameters. And this is done in a technical way with some kind of selection criteria. And the selection criteria or the selection matrix is given here by TK. I will not talk about this more. I will just show you plots, and then we can, with help of these criteria for individual parameters, we can construct a number of criteria, in fact. And here we motivate it, but I want to finish with the following plots to see what can be done. So we have here two populations, and here we have an X which belongs to population 2. And here we have something a bit farther away from population 2, even further away, and then we have something which belongs to population 1. If we look at X belongs to population 2, we have the first two criteria was what we discussed, and then we have 4 other criteria, and all are positive, and this is what we want to have. And today we haven't talked anything about misclassification errors, which is some kind of, I think, very important to statisticians. Yeah. So thank you very much for listening, and you're welcome to come with questions today, tomorrow, or anytime. Thank you very much again.
Thank you very much, Dietrich, for your very nice presentation. Unfortunately, we have no so much time for discussion, and I would like to thank you.
Yeah, thank you. Thank you.
And probably now it's time for next speaker. And the next speaker, it is Professor Arab Bose from Indian Statistical Institute from Kolkata. And his research interest is covering economics, econometrics, probabilities, and statistics. And all this interest is based on some stochastic, let's say, problems. And what is interesting, I'm finding it is high-dimensional data that we both, with Dietrich, we are interested in also partially. And Professor Bose will present us very hot topic on COVID-19 90. Sorry, 19. And his talk will be about modeling of this virus development. And as we can see, he will propose us an epidemiological model using adaptive dynamics three-compartment model. And I would like to ask Dr. Bose to start his presentation. Professor Bose, screen is yours. Please start.
So today I want to talk on COVID, which has been in our lives for last 9 months or so. And this is joint work with Professor Madhuchanda Bhattacharjee from University of Hyderabad. And here's a quick outline of my talk. I'll briefly describe for some of you in the audience, you have heard the terms SIR models or reproduction number, but some of you may not be quite aware of exactly what these are. So I'll spend some brief amount of time on these two ideas, which are already known, very well known in the epidemiology literature. Then I'll talk about how you fit these models. For example, we have some novel ways of doing that. We use aggregated residual sum of squares. We use a geometric smoother, dynamic robust estimates. And then I'll show you how we do long-term interval predictions. So these methods are applicable in general, but I will be a little bit more specific when applying, and we'll see what happens to it when we apply these to Indian COVID data for the period March 14th when it hit India and November 30th. So on the SIR stands for susceptible, infected, and removed. And removed can include recovered or deceased. In the original models, it was only recovered, but now we have counts for the deceased also. And this was a model that was initiated by Carmack and McKendrick almost a century ago. And it's a very important model in epidemiology. And so along with several variations, it has been reprinted as Carmack and McKendrick 1991 with additional material by other authors. So it's a three-part paper, so it's a very important landmark paper in this area. So the assumptions for the SIRD model, the basic assumptions are that the epidemic propagates in a closed, completely susceptible, well-mixed population of a constant size. There is no demographic change, so we assume that there is no net births or deaths during the course of the propagation. And then the propagation happens at constant rates of infection, recovery, and fatalities. So the following parameters are held constant in the regular SIR model. For us, they are constant only for each data window under modeling, where the windows shift by a day, keeping the length fixed, and the parameters are re-estimated. So that's the variation that we are going to use. So the effective contact rate will be beta, the recovery rate will be nu, and the fatality rate will be mu. So these are the three basic parameters of the SIRD model. SIRD will be the cumulative counts for the susceptible, infected, and recoveries. And D will be the fatalities. N is the total number of individuals. Usually it is normalized to 1 by dividing by the total. So that's how it's formulated. And the SIRD model assumes that these sequences or these functions, they satisfy the following simultaneous differential equations. And of course, there is no randomness in this model. As you can see, it's a deterministic model. And of course, there are many variations in the context of COVID-19. And there are a couple of references that we have listed at the end of the lecture. The progression condition, which means that the epidemic will not stall, will not stop, but will continue to progress if and only if the rate of infections is positive. And one can check by using the equations given in this previous slide that this happens if and only if this beta over nu plus mu is greater than 0. So that is the condition on the three parameters for the infection to progress. Now this is related to what is known as the reproduction number. So let me show you how this number is related to the reproduction number. Now, in general, for any epidemic, there are three essential parameters that drive that epidemic. Whereas tau, C, and D. Tau is the transmissibility parameter. That's the probability of infection. Given contact between a susceptible and an infected individual, what is the probability that this individual would be infected? And then there is the average rate of contact, C, between susceptible and infected individuals. So the more the infected individuals move around, there's more chance of getting other people infected. And then the duration of the infectiousness. So as long as the person who is infected, he or she can infect other people. So that's the duration D. The basic reproduction number R0, that's a standard notation in this literature, is the expected number of secondary cases produced by a single infection in a completely susceptible population. So this number is a dimensionless quantity and is proportional to tau times C times D. So these are the three parameters which determine what is known as the reproduction number in an epidemic. So this is a general framework. This is a general kind of definition. And for different models, this R0 takes different meanings or different shapes. In the SIRD model, tau times C is equal to beta, and D is 1 over nu plus mu, and hence the R0 is beta over nu plus mu. So the constant that we had encountered earlier in this slide, where we say this is the condition for the epidemic to progress, that number turns out to be nothing but the reproduction number in the SIRD model. And hence, this is the importance of the reproduction number, which you can see in many different public documents or discussions. Everybody talks about the reproduction number. So this reproduction number in the SIRD model is related to beta over nu plus mu. Is exactly equal to that. And hence, there is always concern if the reproduction number is greater than 1, then the epidemic actually progresses. And the intensity of the progress depends on the higher the value of R0 from compared to 1, the progression is more and more intense. So its estimation is related to the estimation of beta, mu, and nu because of equation 3. So if I can estimate these three parameters, I can estimate the reproduction number. For other models, the definition and interpretation and estimates of R0 is necessarily much more involved. I've given you a very simple setup where we have related the reproduction number to the SIRD model, how it behaves, what it is for this particular model. For other models, these definitions are much more involved. There are actually more than one definition of the reproduction number. And there's a very nice article by Van Risch in 2017 who explains there's many other models and many other definitions of reproduction number and their interpretations. Now, there will be different factors influencing the model in general. So as for example, the time. So if the model parameters should evolve over time. So for us, it's not a deterministic model. And also, the more people get infected, things change. So the time has an important aspect, and the parameters should also evolve over time. So that's our basic message, that it should depend on time. And it also depends on the regions. For example, India is made up of several states and union territories. And for different regions, the data plots show significant regional variation. And then there is this issue of national versus local. So an SIRD model, dynamic or otherwise, for the national data is not appropriate for local prediction. So if I look at the national data and try to predict or estimate parameters and then try to implement those predictions or those estimates in the local level, that's not going to work. So one has to do a regional kind of analysis. Data at the level of even smaller administrative regions will be more informative, but these are not easily available. And then finally, there is a spatio-temporal dependence. So different regions could influence each other. And so we may be able to borrow strength from connected regions for an improved analysis. So in this case, connected does not necessarily mean geographically connected. Connected, for example, could be that the metro cities are more connected than the other cities among themselves because of migration of people from, or because of the airline travel or train travel among the metro cities. So here, spatial temporal dependence takes a very different meaning than from being geographically connected. And there are, of course, there are further factors which influence this an epidemic like COVID. For example, we have locks, unlocks, and zoning and travel restrictions. We have all encountered these things in India, and there is migration. There has been a lot of talk about what happened, how the spread of the epidemic, whether it was affected by the migration that happened in mid-June, July, around that time. And then the level of compliance with the guidelines. So different states, different regions have tried to implement to their best possible ability these locks or zoning or travel restrictions, but the compliance from the public and other authorities has not been uniform. So these also affect the progression of the epidemic. And then there is also this issue about what kind of reporting is done. For example, it's believed that there is a significant underreporting of cases, number of infected people, or of deaths. There is a delayed reporting, and then there is change in the methodology of reporting. So what constitutes a death by COVID and what it does not. So there was a lot of controversy about that. You must have read some of these in the newspapers. And then there are clinical issues, and so that changes over time in the methods of case identification and the method of sample collection and the laboratory testing procedures. So there are so many different kinds of COVID tests now, for example, available. So these are also add to the variations in the data over time. So there has been attempts to incorporate at least some of these factors, but even though we have not done that in this particular work. So you can see, for example, the paper by Anshumali and Meher and Kotwal. So the list of references is given at the end. We, on the other hand, take a parsimonious approach. We do not try to model all of these factors that could influence the progression of the epidemic. There will be simply too many parameters. So what we do is we continue with the SIRD model that I have explained or given a very brief account of earlier. But instead of having these parameters beta, mu, and nu being fixed over time, we let the model or the epidemic model evolve adaptively with the temporal data in each region. So first of all, we do the modeling region-wise. And secondly, these parameters are not going to be fixed for us. They are going to evolve adaptively over time. And due to estimation based on shifting of windows, the parameters are able to adapt to changes in the underlying observable as well as latent factors. So in a broad sense, our approach is akin to non-parametric curve fitting. So we have these curves for our daily data on infections and deaths and recoveries. And we would like to fit a non-parametric curve to that. And in the process, we will also estimate the parameters beta, mu, nu, and also the reproduction number. The data source has been the volunteer-driven crowdsourced database, which is more or less standard now, especially for Indian data. This data is updated daily. And as you pointed out earlier, there are issues with this data. For example, there could be missing values, negative counts, delay in updating, and change in the reporting format. So we did some preliminary consistency checks and cleaning. And one has to note that the data is obtained only at discrete points, even though that's the original model is a differential equation model. So it's a continuous time model, and of course one has to match these two issues up. So for any choice of the values of beta, nu, and mu, the SIRD differential equation can be solved numerically because we have data only at discrete time points, and there are softwares or programs available to do this. So here is the distribution of daily infection for the 12 first hit regions. So March 14 was the first, the day when COVID was identified in India, and these are the first 12 states which were hit by COVID, and this is where they stand now. And you can see there is significant regional variation in the counts. So we should mention something about the software and the hardware in which we had implemented all this, the method that I'm going to mention. So the implementation was done on the software R. The library dsolve was used to solve the differential equations numerically. The entire program takes a few minutes, and you can refer to all the details of the analysis in our archive paper, which comes with a supplementary file where all the detailed plots and figures are given until August 31, 2020. And further updates beyond this time point are available in this link to Professor Bhattacharya's website. All right, so one important novel or variation that we have done is that we have implemented the SIRD model and its variation by all those that we came across in the literature. They used what is known as the residual sum of squares of the number of infections. However, for COVID-19, we have information on recoveries and fatalities also. And so what we did was, instead of using only the residual sum of squares for the infections, we used the aggregated residual sum of squares for infections, recoveries, and fatalities. And that changes drastically the quality of the fit and the quality of the estimates that we have seen from our experience. So the temporal estimates of beta, mu, nu, note that now, because we are going to allow evolution over time, these three parameters are going to be estimated over time. So they are going to be time-varying estimates. So only the most recent past 7 days data is used to estimate the parameters, with the obvious updation of the initial condition as time progresses. These estimates are then smooth, leading to robust final estimates. Thus, at time point t, these are obtained by minimizing the sum of squares given in equation 4, where where the hats are the observed values of infections, recoveries, and fatalities. And then we devise a grid, and the values of IT, RT, and DT for given parameter choices over a grid are obtained by numerically solving the differential equations. So there is an optimization procedure over the grid, which eventually gives us the best parameter values of beta, mu, and nu. Once you obtain those, then we choose a weighted average over the last 7 days estimates with geometrically decreasing weights. Other smoothness could also be used. By trial and error, we arrived at these estimates, which seem to be doing a reasonably good job. So we thus arrive at a robust final estimates, so beta t, nu t, and mu t at the time point t. It's important to realize that these set of estimates will keep on changing. So it's like because it's happening over a moving window of 7 past days. So at any time point t, these are the estimates of the current estimates of the three parameters. Now recall the relation between beta, mu, nu, and R0, the reproduction number. So our initial estimate for R0, once we have derived beta, mu, and nu, is simply beta by mu plus nu at the time point t. Now, once you do this, and this turns out to be a spiky estimate, and we robustify this estimate by, for example, taking a median of moving window of 7 past values to obtain a model for the epidemic, and hence this equation is really not sacrosanct. Now, once you obtain these estimates, then the point estimates are obtained by solving this SIRD model numerically, and that's how we do it. So we can also calculate the k-step ahead predicted values. And while solving this, we found it extremely useful to add the obvious but crucial constraint R plus D is less than or equal to IT. Recall there is no random component. At any time point t, we can consider the past values and also consider the corresponding accumulated predicted values. And we can consider the empirical distribution of the error values IT minus I hat t, and then use this empirical distribution to come up with our predictive interval by taking the quantiles of this empirical distribution at the lower and the upper quantiles. And the same idea could be used for other variables also. Note that the width of the band remains same for the k-step ahead predicted values, as there is no updated empirical distribution. So a quick view, this is what was happened to the last 4 months of reproduction number, and you can see that this was in August, and then September, and then October, and then November, and you can see there's a shrinking of the range of values of R0, and there's also the change in the order of the with respect to the highest and the lowest, and so on, and this is how the changing the reproduction number distribution changes over the last over time, and this is one sample plot from our paper, and predictive bands for daily count for Delhi, which is a very worrisome state as far as the number of infections is concerned. And this is the predicted counts up to 1 year starting from November 30th. And you can see, for example, the curve for West Bengal is sharply increasing. So that's a really worry for that's a real serious concern. And then, for example, Kerala is also sharply increasing. Delhi, which was not doing too well, which is increasing recently, but it seems to be still increasing significantly. Some of the other states are look to be flattening the curve. So for different regions, the progression has been quite different. All right, so here is a quick list of references. And one can always go to our article for all the other details. Thank you very much.
Thank you very much, Professor Bode, for your interesting talk. And we have few seconds for questions. If somebody has a question or comments, so please ask. If not, I am pretty sure that you can expect many.
Please raise the hand in case.
Yes. Okay. So please. Oh, no. So if not, I would like to thank Professor Bode once more. And as I told you, you can expect many contacts with people, because this topic is extremely hot and very interesting from also mathematical point of view. And these models are the subject of big discussion. So thank you very much for your presentation, and I'm closing this session. And thank you very much.
Thank you.
Thank you very much, all participants for coming.
Thank you.
Please.
Thank you. Thank you. Thank you. Thanks.
Yeah. Will.
Thank you, Professor Augustine, for being the chairperson for the session. Moving on, we have invited talks from Professor Augustine Marquez and Professor T.S.S.R.K. Rao. Augustine Marquez is a professor at the Department of Mathematical and Statistical Methods, Poznan University of Life Sciences, Poznan, Poland. He will be talking on linear admissible estimation revisited. He is one of our invited speakers, having research collaboration with Professor C.R. Rao. We are happy to have you here, sir. Second speaker, T.S.S.R.K. Rao, is the adjunct professor, Mahe Manipal, and visiting professor, Ashoka University, Sonipat, India. He is going to present on the topic operators, Birkhoff's James orthogonal to spaces of operators. I request Professor Ramesha C., MIT Mahe Manipal, to chair the session. Over to you, sir.
Thank you very much. Yeah, it's my pleasure to chair the session.
I would like to thank Professor Prasad and the organizer for the invitation and to give me the opportunity to give a talk at ALAPS 2020. But first of all, I would like to send my best wishes for a happy birthday to Professor Rao and wish him many more anniversaries to come. And in fact, I would like to dedicate my talk to Professor Rao, whose work has greatly influenced my research. And the main topic of my research was linear admissible estimation, and it is of my presentation. First, I would like to show some pictures from the last visit of Professor Rao in Poznań. It was in 1991 when Professor Rao was getting honorary degree from Adam Mickiewicz University. It is the main university in Poznań. And it was very nice ceremony. And now I would like to go to present the problem I would like to talk about. And first, I would like to present it, to make some preliminaries. I would like to present the model. I will consider general Gauss-Markov model. I will use the notation by the triple y x beta sigma square v, where y is the vector and dimensional vector observation, with expectation x beta and dispersion matrix sigma square v. Matrices x and non-negative definite matrix v are known, while beta and sigma square, vector beta and sigma square positive number are unknown parameters. And the problem I would like to present it is estimation of arbitrary vector of linear parametric functions, k beta, defined by k by p matrix k. And I will consider estimation of k beta among the set of linear estimators of the following form: fy plus f, defined by matrix f and vector capital F and vector f. And the criterion of estimation is quadratic risk function that has the following form, and it consists of two parts. First, it is trace of covariance matrix of the estimator, and the second term is the sum of squares of bias of the estimator. And the admissibility with respect to the quadratic risk function is defined as follows, namely, estimators Ay plus f is said to be admissible for k beta in the class of linear estimators under the model M, and with respect to the quadratic risk, if there does not exist another linear estimator, fy plus f, such that the difference of quadratic risk of estimator Ay plus a and f plus f is non-negative for all beta and sigma square, and it is non-zero for at least one such pair. And now I would like to present the main motivation, inspiration for this work. Namely, it was the characterization of admissible linear estimators for k beta given by Rao in 1976. And this characterization is the following: under non-singular model M, it means model with dispersion matrix V positive definite, and for any estimable k beta, it means defined by matrix K that can be represented as the product Cx. This condition can be expressed in a bit different form, namely that linear space generated by rows of matrix K is linear subspace of linear space generated by rows of matrix X. And now estimators Ay plus a is admissible if and only if the following four condition holds. The first condition is very important. I will mention about it later on again, and it's telling that the range of matrix VA prime range, it means the linear space generated by columns of the matrix, is linear subspace of the range of X. The second condition is telling that the product AVC prime is symmetric matrix, and the third one, that the product AVC minus A prime, I'm using prime for transpose, it is non-negative definite matrix. And the last one is concerned to the vector A defining estimator, namely A belongs to the range of matrix A minus C multiplied by X. Now I was putting star here in the second condition. Maybe when I will assume later on that that metric is non-negative definite, I will assume that such a metric is symmetric. So this condition can be cancelled, assuming such definition of non-negative definiteness. That is quite common, and it is a bit simplified the condition. So Rao work stimulated further research in this area, and Rao results were later on generalized to other linear models, namely restricted models and models and multivariate models and so on. First result generalizing Rao result was given by Hoffman in 1977, who gave characterization of admissible linear estimators for parameters vector beta in non-singular model and with matrix Sx of full column rank, and in the model with so-called elliptical restriction of the form beta prime and beta less or equal sigma square, where n is known positive definite matrix. Another result concern linear model with linear restriction, and these results were given in two papers by Paxelar and Markiewicz in 1985 and 1986. To get this result, we were using the following characterization of admissible linear estimators for parameters vector beta in the model with full column with the X of full column rank and with V non-singular. It has the following form, and it is telling that the XAV is symmetric matrix, and the eigenvalues of the product AX, the eigenvalues belongs to the interval from 0 to 1, and that vector F belongs to the space, to the range of I identity matrix minus AX. And I will present one of this characterization. It is telling that such estimator is A y plus A is admissible for beta in a restricted model with restriction of the form R beta equal small r, and in the non-singular model and with the matrix X of full column rank. So such estimator is admissible in restricted model, even only if it is admissible in unrestricted model, and it is fulfilling the restriction. So estimator itself is fulfilling restrictions. And another characterization is telling that AY plus F is admissible in non-restricted model, and expectation of estimator is fulfilling the restriction. So it is quite nice characterization. Now, I would like to say something about generalization of Rao result to a singular model. First, let me mention the paper by Matthew, Rao, and Sinha from 1984, in which they were showing that in a weakly singular model, it means in the model when in V is possibly singular, but the range of matrix X is subspace of range of matrix V. And for K beta estimate Rao's conditions are unchanged. So we can use exactly the same conditions. Let me say that this condition is quite, we can obtain such condition, for example, but using some transformation, we are getting dispersion matrix of transform vectoral observation can be singular. Now the general results concerning general models, it means the model in we have when matrix V is possibly singular, but it's not necessary such a condition, such a range condition. And for any estimate vector K beta, the characterization we obtained is the following. It is what we can see, we have three the same condition from a raw result, and with some additional one condition telling that the range of the matrix A minus C multiplied by X is equal to the range of matrix A minus C multiplied by S. And what is S? S is any matrix such that the range of matrix X is equal to the common part of the ranges of matrix X and matrix V. And now it is very easy to see that when the model is weakly singular, so we can put as matrix S, we can take as matrix S, we can take matrix X. So here this condition, of course, is trivially holds and can be cancelled. So it is confirmation that another way to showing that in weakly singular model we can use only raw conditions. And now a bit inspired by the paper by Professor Mitra about probably the title was about estimation of non-estimate functionals, and we are considering the fully general setup. It means that the model is general, but also we have any restriction of on the vector k beta. And this characterization was given in 1990. And let's say the most general results was given by Baxellare, Markiewicz, and Rao in 1995. And this paper was given a characterization of admissible linear estimators of k beta and with respect to the weighted quadratic risk. This risk is defined as follows: when W is any is matrix of weight, that it can be any non-negative matrix. And of course, it is assumed that k beta is arbitrary and model is general. So next, I am presenting this problem here, namely a matrix risk function denoted by capital Rho f of y plus f k beta is defined as follows. And it is very easy to see that the quadratic risk is equal to the trace of matrix risk. So it is the following relation between these two risks. And the definition of admissibility with respect to matrix risk is the following: AY plus F is said to be admissible for k beta among the class of linear estimators and the model M. And with respect to the matrix risk function, if there does not exist another linear estimator Fy plus F such that the difference of matrix risks of estimator AY plus F and Fy plus AY plus F and Fy plus F is non-negative definite matrix for every pair of parameters beta and sigma square, and it is not a zero matrix for at least one pair beta sigma square. And the set of admissible estimators, of course, contain estimators admissible with respect to the quadratic risk function, and the motivation, the inspiration to study this problem was the very important necessary condition for admissibility with respect to the matrix risk function is the following. I was telling about this condition already, that the range of Vf prime is linear subspace of range of X. So it is necessary condition for admissibility with respect to the matrix risk, but as well as with respect to the quadratic risk. And we obtained in 1989, the paper Baxellare and Markiewicz, we obtained general characterization of the class of admissible linear estimators for beta, for any k beta, with respect to the quadratic risk function in a general model. And later on, with the paper Gross and Markiewicz in 1999, we obtained a bit more general characterization of such a class in mixed linear model. And I was using this matrix risk function in the problem of admissible linear estimation in multivariate linear model. In fact, I was introducing another matrix risk function in the case of the setup of multivariate linear model, but also I was considering usual quadratic risk function. And this characterization are given in my 2002 paper. So this end of story of matrix risk function, but now I would like to mention some problems connected with singular model. When the model is so-called strongly singular, it means when the matrix V is singular and the range condition, the following range condition doesn't hold, or we can say that the range of X is not a linear subspace of range of V. Then beta satisfied so-called natural restriction when Q sub V, it is orthogonal projector into orthocomplement of the range of matrix V. And the use of this restriction is very hard because of the vector of option Y. We can know it only after when experiment is done. So it was quite a big discussion about what to do in such a problem, and we obtained some. We were giving some recommendation what to do. Oh, sorry, so it is something up. Oh no, maybe it's okay. Yeah, not. Oh. In the paper by Baxellari, Rao, and Markiewicz, 1992, we were recommended that natural restriction can be ignored in the case of linear unbiased estimation, minimum dispersion linear unbiased estimation, admissible linear estimation with the static, and as well as with respect to the matrix risk function. That this restriction can be ignored, and we showed that when we are considering both class of admissible, let's say admissible linear estimators, in the first case we are considering this restriction. In the second one, this restriction are ignored. So in this second class, we can always find estimate for an estimator from the first class. We can find an estimator in the second class that is equal, such that both estimators are equal with probability 1. So they are stochastically equivalent. And now I would like to say something about another problem. It means the class of admissible linear estimators is quite, let's say, big class. It's containing some not so much reason-like estimators. So it is such idea to impose some additional condition to the estimator. And such condition I was studying, it is linear sufficiency. Linear sufficiency was, this name was given by Drigas, who also was giving the following definition of such linear sufficiency of statistic Ty for estimation of K beta. But the first such statistics was studied by Baxellari and Kala, and I will use the title of their paper as characterization of such statistics. Namely, the title was telling something like that it is transformation, T, it is transformation of observation vector Y, preserving the blue. It means that it was possible to derive best linear unbiased estimator of K beta by linear transformation of statistics Ty. So it is much, let's say, simpler description of this property. And I was studying this problem in my paper 1996 in the case of estimation of parameter vector beta in the model with matrix X of full column rank, and I was showing that the class of linearly sufficient and admissible estimators are exactly the class of general ridge estimators, and this class was presented in raw papers on one of the class estimators that are admissible. And later on, we were, in the same year with Heidegger's, and we are obtaining the characterization of linearly sufficient and admissible estimator in a restricted linear model with elliptical restriction. So we were following Hoffman paper. And further later on, I was studying the problem of linear sufficiency and admissibility in misspecified model. It means it is the problem started with the famous paper by Mitra and Moore in the of best linear unbiased estimation, and it is the problem is the following, that we are characterizing the linearly sufficient admissible estimators in the model in which covariance matrix V is possibly incorrect, and we have now studied the problem whether the sum of these estimators, and we are characterizing such estimators that are linearly sufficient and admissible in correct model. And continuation of this study of admissibility and linear sufficiency in the model with nuisance parameters was presented in the paper Markiewicz and Puntanen 2009. And at the end, I would like to say something about the study of the admissibility problems. There are quite a lot of papers published recently, and these authors were using so-called balance risk function. And when we see this, it is R of a y beta, so it is the problem of estimation of the parameters vector beta, and this risk function has the following form. It is the sum of two terms. First, it is V multiplied by expectation of the following product. When we are looking at this product and we replace a y by beta, so and we are minimizing it, so we are getting so-called ordinary least square. So it is this form used to get ordinary squares, but the beta now is replaced by estimators of beta a y. And the second term, it is nothing more than possibly weighted quadratic risk function of such estimator, but multiplied by 1 minus w. And w is a number from the interval from 0 to 1, a closed interval, and the matrix of weight is known positive definite matrix. So now we can see that putting small w equal to 0, so we are getting one of such balance risk function is usual quadratic risk function. And this result was recently given, for example, in a series of papers by Kong, He and Wu, and Kao and Xu, probably. My pronunciation is correct. So I would like to thank for the it is the almost end of my presentation, but at the end, I would like to present the list of references. And so you can see the story, the paper on linear sufficiency, admissibility problems, and here we have the paper on natural restrictions, and the paper on in which characterization of admissible linear estimators with respect to the arbitrary quadratic risk function is given. And later on, there are two papers on admissibility with respect to balanced risk function, and and here is a paper by Drigas when he was using the name of linear sufficiency, and he was showing that the linearly sufficient statistics under normality is sufficient in usual sense. And so these papers I was giving, and here are the papers still about admissibility and partially linear sufficiency. It is a paper when the characterization of general rich estimators was given using the term of linear sufficiency admissibility, and at the end we have this
raw papers. The title is Estimation of Parameters in a Linear Model. It was published in Annals in 1976. And at the end, we have some additional references. I would like to say at the end about one of them, of these references, namely, it is in this paper, the authors were considering continuous time Gauss Markov model. So it is another way of generalization of linear sufficiency and linear admissibility problem. So thank you very much for giving me opportunity for presenting my talk. And this is the end of my talk. Thank you very much.
Augustine, I had several questions.
Yes, yes.
I'll write to you through mail. And I invite you to participate in this felicitation function at 9 o'clock Indian time.
Okay.
Please join us.
Yes, yes. Thank you very much. Sima was reminding me. Okay, so we'll have opportunity to discuss maybe a bit more. Okay, I will.
Okay, bye.
Thank you, Professor. Now let me invite Dr. T.S. R.K. Rao from
Thank you, Professor Ramesha, and thanks Mahe and CRAM for this kind invitation to give a talk at this conference. Before I request for the recorded lecture to be played, I would like to briefly say that even though my affiliation now shows as Ashoka University, I retired in 2019 as the head of the Indian Statistical Institute at the Bangalore Center, and I also did my PhD from Indian Statistical Institute at Kolkata during late 70s and early 80s. Professor Rao by then already left ISI Kolkata or other places, but even as a very young PhD student, I could see his influence on this entire institute. Subsequently, in my career, I met him several times and had occasions to listen to him. So it's a great pleasure for me to be able to give a talk in this conference. So now I would request the organizing person to turn my lecture on. There seems to be some connectivity issues at my end, so the lecture would play on, but I would also be here to interact and take questions. So my talk is about operators that what are called Birkhoff-James orthogonal to spaces of operators. Okay, so I will mute my phone. So are there any technical issues? I'm on talk screen or audio. So thanks the organizing committee and Mahe for arranging this conference and for asking me to give a talk in this. And I am glad that in spite of all the difficulties caused by the pandemic, we have been able to continue to share mathematics by efforts of various colleagues and through online platforms. So this talk is a combination of linear analysis, functional analysis, that is geometry of Banach spaces, and approximation theory. In fact, we are going to get to some new minimax principles and apply them to solve problems in operator theory. So this title is the operators, Birkhoff-James orthogonal to spaces of operators. And for real Banach spaces X and Y, I will only be talking about real Banach spaces. And L of xy denotes the space of all bounded linear operators. Then, if you take a closed subspace Z contained in Y, you can look at the space of all operators from X taking values in Z, that is L of xz. That is a subspace of the space of all operators L of xy. And on the space of all operators, one has the usual operator norm, which is the supremum of t values of the vectors over the unit wall. So one of the questions of interest that one can ask is I will just define this formally in a minute. If one could look at the Birkhoff-James orthogonality in the space of all operators and relate the orthogonality to a subspace. So not orthogonal to a vector, but like in the case of the usual Hilbert space orthogonality, you can look at set of all vectors which are orthogonal to a given vector and look at that set now. And you can ask if one can actually describe such a set and of course relate it in the spaces of operators, not just in an arbitrary vector space, but in your vector spaces of operators. So now I'm going to just read the abstract before I simply explain the terminology using my electronic board. So here is the abstract. So the important question is that if you have a P that is orthogonal to this space L of xz, then can you find a vector, unit vector x0, such that the norm of t is attained at that vector x0, and the value, the vector t of x0 is orthogonal to y. So this is somehow tries to relate orthogonality of an operator to a collection of operators to orthogonality of a vector to the corresponding subspace. So that is the challenge. You have only information globally, then can you actually get local information? The orthogonality here should imply for some vector x0 where the norm is attained, t of x0 is orthogonal to this. So in order to achieve this, so as you can see somehow, since this is supremum, and when you reinterpret orthogonality, you will see that it's actually an infimum problem. So in order to achieve that, you have to develop a compact optimization for the space of all. Well, I tried to do this problem initially in the spaces of compact operators, and I would need to then develop a minimax formula which would allow me to estimate the distance between an operator to the subspace of operators, distance between t from L of xz in terms of point-wise best approximations, so that this approach links what is called a local optimization to a global optimization problem. So this independently, somehow these ideas are of interest to people working in optimization theory. One of the things when we look at the problem, you realize that most often this kind of problems involve what are called selection theorems. And selection theorems are the kind of a thing which would allow you somehow to choose what is called a selector having certain properties. But it has been well understood in linear analysis that getting a linear selection is very difficult. Somehow you can get a point-wise selection, but to make this map linear is something quite difficult. There are very few linear selection theorems, and only in case of very good spaces like Hilbert spaces and things like that. So in general, these questions are difficult to answer. So what I would do in my approach is to bring in techniques from geometry of Banach spaces to solve this problem. So here is then our background is the space of all real Banach spaces. So X is a real Banach space. If you look at a vector X belonging to X, you would say that X is orthogonal to Y. So this is a notion due to Birkhoff and James. So we used to continue to use the perpendicularity to denote the orthogonality. Here, if provided, if you look at, so X is a Banach space, there is a notion of a norm there. So if you look at norm of X plus lambda Y, that would be bigger than or equal to norm of X for all scalars lambda. So for all scalars lambda, if you know that the length of the vector norm of X plus lambda Y is bigger than or equal to norm of X, then you would say that X is orthogonal to Y. And it turns out that in case of a Hilbert space, this notion of orthogonality coincides with the usual notion of X is with the notion of inner product of X with Y being 0. That is the notion of orthogonality in the Hilbert spaces. And unlike the case of a Hilbert space, the Birkhoff-James orthogonality is not symmetric, nor is it additive. So X is orthogonal to Y need not imply Y is orthogonal to X, or if X is orthogonal to Y and X is orthogonal to Z need not imply X is orthogonal to the sum vector Y plus Z. So this is somehow more restrictive notion, but it turns out over the years this has been a well-studied notion, and it does give a lot of information even in the case of a general Banach space about the structure of the Banach space. So this is the basic notion, and the thing that we want to understand is this notion in the space of bounded operators L of x, y. So if you have an operator T and if you have another operator S, and you want to look at the notion of when is T orthogonal to S, is it some way related to, for some points, the corresponding vectors T of x being orthogonal to S of x? So that is the basic question. Can you relate or understand the orthogonality, Birkhoff-James orthogonality in the space of L of x, y in terms of orthogonality of the corresponding vectors in the range space for a suitable vector, appropriately chosen vector x or chosen set of vectors x? So that is the question that one wants to answer. And the reason, of course, why these things need to be studied in the general context is that even when you start with a Hilbert space H, then the minute you look at the space of all bounded linear operators, that is only a Banach space. So no longer you have any inner product structure here. This is just a Banach space, and the orthogonality then you can study here is the Birkhoff-James orthogonality. And this talk in part is motivated by a well-known theorem of my colleague Rajendra Bhatia from Ashoka University, also at ISI. So this and a well-known linear analyst and also colleague to several of us, friend to several of us, Peter Semrel. So this Bhatia-Semrel theorem would say that when H is a finite dimensional Hilbert space, I will write it in the next page. So for a finite dimensional Hilbert space, this would say that if you know that T is orthogonal to S, then there is a vector x0 of length 1 such that T attains its norm at this vector x0. So remember, let me recall what is the norm of the T per U. This is holds for any space, Hilbert space or general space. This is supreme over all vectors of length less than or equal to 1, norm of T of x. So in finite dimensions, of course, because of the compactness, Heine-Borel theorem, compactness of the unit ball, a transformation would attain its norm. So this is saying that there is when it is attains its norm, it will be at a unit vector. So there is a unit vector where the norm is attained and such that T of x0 is then Birkhoff-James orthogonal to, or orthogonal in the Hilbert space sense to S of x0. So this is a very beautiful theorem which would say that orthogonality with the operators would actually mean that there is a point where the norm of the operator is attained and the corresponding vectors are orthogonal to each other. So this has generated in the past 2 decades a lot of interest, and one of the things it turns out is that this is no longer true in infinite dimensional spaces, and also even in finite dimensions no longer true if you don't take a Hilbert space. So this is something which is special to Hilbert spaces. So what one would then like to understand, the research that has been generated by this is somehow to understand the notion of Birkhoff-James orthogonality when you have general Banach spaces of x and y, and try and see if you can relate this kind of a point-wise relation you can get out of the general orthogonality. So one of the things then you can talk about is that you take any subspace Z contained in a space Y, a closed subspace for me always, and you are looking at the space of all operators from a Banach space X into Z as a subspace of space of all operators from X into Y, and then you take an operator T which is such that T is orthogonal to all the operators in L of xz. So this I will write it as T of orthogonal to L of xz. Means that for each S, T is orthogonal to L of xz. So instead of looking at a single operator, as in the case of Bhatia-Semrel theorem, I want to look at this subspace of operators, and I want to look at T orthogonal to space of all operators, and ask a similar question, namely, when can you get a unit vector T such x0 such that norm of T of x0 is equal to norm of T, and this vector T of x0 is now orthogonal to this subspace Z. In other words, it is orthogonal to all the vectors in Z. So instead of looking for one vector situation like the way I illustrated Bhatia-Semrel theorem, the more general problem in the context of Banach spaces can be formulated like this. For a closed subspace Z, if you have an operator T such that T is orthogonal to all of L of xz, then is there a point x0 such that norm of T of x0 is equal to norm of T, and T of x0 is orthogonal to Z. So then one of the things which is also true in case of Bhatia-Semrel theorem also here is that the converse is always true. In other words, if you can find a unit vector x0 such that norm T of x0 is equal to norm of T and T of x0 is orthogonal to Z, then T is orthogonal to L of xz. So this is easy to see. Take any S in L of xz and then look at norm of T plus lambda S to show the orthogonality. That is bigger than or equal to its value at the unit vector x0. So I write it as now T of x0 plus lambda times S of x0. Okay, but I know that T of x naught is orthogonal to Z, and S of x naught, since S is an operator from x to Z, S of x naught belongs to Z. So by hypothesis of pointwise orthogonality at the vector level, this is bigger than or equal to norm of T of x naught. And of course, norm of T of x naught we said is norm of T. So we have proved that for any S belonging to L of xz, norm of T plus lambda S is bigger than or equal to norm of T for all scale S lambda. So that means T is orthogonal to the operator yes. So that this is clearly a necessary condition, and what we want to look at is to see that when under what conditions is this a sufficient condition. So this is the minimax formula that I want to develop, and somehow these kind of things have been looked at by well-known approximation theory people. This is William Light and E.W. Cheney. This is a monograph by them called Approximation in Tensor Product Spaces, and one somehow knows that there is a close relationship between tensor product spaces, particularly injective tensor product spaces, and compact operators. So this is somehow the kind of setup one would like to know. So for example, if you look at the space of all continuous functions on a compact set K, which are valued in a Banach space Y, and look at the space of all vector valued continuous functions, you can again put the supremum norm of this. So norm of F is supremum of K belonging to K, norm of F of K, where F is a continuous function. Then for any closed subspace Z of Y, you can now look at continuous functions which takes values in Z as the space of subspace of continuous functions which take values in Y. And so this classical formula due to Light and Cheney would say that if you look at the distance, so the distance means this is infimum of norm of F minus G, where G belongs to CKZ. So this infimum is same as supremum of, look at the distances for each K, for each point K of K, F of K is a vector in Y. So look at its distance of this vector F of K to Z. Look at those distances and take the supremum. So this is somehow a very famous minimax situation. Here you are looking at an infimum. So this is infimum of norm of F minus G, but norm itself is a supremum formula. So this is in sup is same as sup, and distance is again infimum, supremum. So this is a very beautiful minimax formula. And so I have realized that one of the things you would like to do is to really ask if such a minimax formula is can be formulated and proved in some special cases in the case of spaces of operators and generally compact operators. So this is what we would do. So it is quite easy to see that, so let us get back to our setup of operators. So Z is a subspace of Y. We are looking at L of xg as a subspace of L of xy. So you take an operator S in L of xg, then it's easy to check that if you look at any unit vector, the length of T of x minus S of x is always bigger than or equal to the distance between T of x to the subspace Z. So now you take a supremum on both sides over the unit wall and take infimum on overall S belonging to L of xz, you realize that distance between T and the subspace of operators L of xz is really bigger than or equal to supremum over the unit wall distance between the vector T of x to the subspace Z. So the analog of Light and Cheney then can be formulated in a context of operators on Banach spaces as to ask, when is this formula valid? When can you have equality in this inequality? When can you say the distance between T and the space of all operators is really looking at pointwise this thing? So this is what I call as a local optimization, and this is what I call as a global optimization. You are looking at a global infimum, and here these are local infimums, and then you are taking the supremum over the local. So this is what I would call as the minimax formula, and one would like to know when is such a minimax formula valid. So the kind of domains that I want to solve this problem is that I look at, because the light and genius problem is situated for continuous functions, I would like to look at a kind of a class which is more general than continuous functions. These are Banach spaces which have the property that when you take the dual, then the dual is isometric to the space of all measures, space of all integrable functions with respect to some positive measure mu. So this is somehow a very natural class. When you look at LP space theory, you realize that it is possible that you have Banach spaces X such that their dual is isometric to L1 of mu, and these are such spaces were essentially studied by a well-known functional analyst, and of course a great functional analyst, Zoran Lindenstrass. And Lindenstrass has studied it, and his monograph is called Extensions of Compact Operators. So it is clear that somehow these are the kind of setup where you would like to solve the kind of optimization problems that I am looking at. So I look at these class of Banach spaces to solve this problem. So then there is associated with this subspace L of xz, you can look at the quotient space L of xy divided quotiented by L of xz, and then you map it into operators from X taking values in the quotient space Y over Z. So that is a subspace of Y. So I have the quotient space Y over Z, whereas L of xz is a subspace of L of xy closed to some space. So I have this quotient space of operators and send it to the space of operators. And this is the map. So pi denotes the quotient map on all spaces. So you look at phi of pi of t. This is any element here is looks like a pi of t, where pi is the map from L of xy to this quotient space. So phi of pi of t is look at the corresponding quotient map here and take the composition. Now one can easily check that the minimax formula I am asking is to say that when is this map phi is an isometry. So what we started out as a minimax formula is turns out to say that when is this map is an isometry. And philosophically, this is also a very important problem in Banach space theory. Namely, most often you have, these are spaces you have pointed out by another space of operators. And then you want to say, when can this be realized as space of operators in some other sense, from X into, of course, different range, Y over Z. So this is again a very classic problem in Banach space theory, and one is actually attempting to solve that problem also here. And somehow this turns out that you would need a little more extra geometric information in order to do this. And then if you do that, then the main result will be the following. For a separable and reflexive Banach space, my domain is like Hilbert space, for example, is a reflexive space, and most often it is enough to consider separable Hilbert spaces. So similar to that, I take my domain as a separable reflexive Banach space, and Y is a Z is a subspace, closed subspace of Y, and now I put some geometric conditions on Z. Z is an L1 pre-dual space like the one we I have defined before, and it also sits in Y in a very nice way, that is called, it sits like a M ideal in Y. Then for any compact operator T from X to Y, this distance T of T to space upon bounded operators X to Z is actually attained. There is a point x0 of length 1 such that the distance of T of x0 to Z is really equal to this supremum taken over all unit vectors of the corresponding point-wise distances. So this is the minimax formula. So this minimax formula validity very clearly is equivalent to that if T is orthogonal, if this compact operator is orthogonal to L of xz, then this at this point x0, T of x0 is actually orthogonal to the corresponding subspace Z. So this is then one special instance in the theory of Banach space theory where one can do an analog of Gattier-Semrel theorem on Hilbert spaces and much more, because somehow Bhatia-Semrel theorem is about only two operators being orthogonal to each other, whereas I am solving this problem for an operator T, which is orthogonal to the space of operators from L of xz. Then my conclusion is that there is a vector x0 where the norm is attained such that the corresponding vector T of x0 is orthogonal to this closed subspace Z contained in Y. Of course, G has to be a special subspace of Y. Then this problem is solvable. So I hope I have sort of communicated to you a lot of interesting thing in geometry of Banach spaces, things somehow which work quite neatly in case of finite dimensional or infinite dimensional Hilbert spaces are enormously more difficult to solve when you formulate and try to solve the same problem in the context of general Banach spaces. So I would like to stop here and take questions in a subsequent few minutes, but let me finally show you my references. So these are my references. So this is the paper of Bhatia and Semrel that I'm talking about. This is from linear algebra and applications in 1999. And this is the monograph of Light and Schinig, which is about approximation theory in tensor product spaces, where they have somehow attempted to solve some minimax problems in long time ago in tensor products. So when I wanted to do the same in spaces of all operators, so that would be my starting point. But then since these things involve selection theorems, I had to apply tricks from geometry of Banach spaces to overcome the difficulty of choosing a linear selection. And there has been a lot of interest in Indian colleagues also and others in this area of Birkhoff-James orthogonality. There is a nice survey article written by two colleagues from Jadavpur University, Kallol Paul and Dev Malya Sen, Birkhoff-James orthogonality and its applications in study of geometry of Banach spaces. It appeared in 2019 in this proceedings. So that is a very good point to start the study. And I think the general theory of tensor products is the monograph by Ryan is introduction to tensor products of Banach spaces is a good place to learn tensor product theory. So thanks once again for arranging this meeting and giving me this opportunity. Thank you.
Thank you, sir. Any questions? Manjana, shall we wind up? Yeah.
So thank you very much for patiently listening to me, and I'm glad very well without a hitch.
Yes, join us. So thank you, sir, Dr. Professor TSS R.K. Rao, and also Augustine Marguerite for their excellent lectures. Thank you, sir.
Please join us for evening function, presentation function. Thank you.
Thank you.
Yes, somebody muted. ಅಲ್ಲ ಇದೆಲ್ಲ ಸಿಗುತ್ತೆ
It looks as though my video froze.
Thank you, Professor. Moving on to the next session, we have Professor S.K. Niyagi and Professor T.E.S. Raghavan. S.K. Niyagi is a professor and head of Indian Statistical Institute, Delhi Center, India. He will be delivering talk on characterization of special matrix classes using degree theory. One more speaker, T.E.S. Raghavan, is an emeritus professor at Department of Mathematics, Statistics and Computer Science, University of Illinois, Chicago. He will be speaking on linear complementarity via zero-sum matrix games. May I now request Professor T.S.S. R.K. Rao to chair this session. Over to you, sir.
Thank you very much. It's my pleasure to invite these distinguished colleagues to give talks in this session. So may I request Professor S.K. Niyagi, who is also head of the Indian Statistical Institute at Delhi, to give his presentation. I'm not getting the audio.
So I'm glad that so I'm able to give a talk in the honor of Professor C.R. Rao. The title of my talk is Characterization of Special Matrix Classes Using Degree Theory. So I'm from Indian Statistical Institute, Delhi. So let me give first outline of the talk. So I start with give some preliminaries, and then I'll introduce some concept degree of a LCP map, linear complementarity problem map. And then I'll talk about Stewart extension formula of degree, and then I'll talk about different matrices of degree plus minus 1, and then I'll talk about superclass matrices. So let me start with the preliminaries. The linear complementarity problem, it started with a paper of Duhal, and that time that name was different. It came with the name as a problem of linear inequalities, and subsequently that with the thesis of Cottle, this particular subject took off, and over 5 decades, host of researchers have worked on this problem, and so that I am going to elaborate and what are the developments, and something that finally that I want to say that degree theory plays a big role of characterizing the matrix classes associated with linear complementarity problem, and what are the other developments has happened with respect to these classes and degree theory that I am going to explain. So let me tell you that linear complementarity problem, it is basically to find x such that given a vector a and q, ax plus q greater than or equal to 0, and x transpose ax plus q is equal to 0. X transpose ax plus q is equal to 0. This is the complementarity constant. Other one is the feasibility condition that which is given by the linear inequalities. I'll make use of the term pos A, that is the convex cone generated by the matrix A. So that is basically that set of all x such that y greater than or equal to 0 and x is equal to ay. K is the set for all q for which SQA is not equal to 5, that is the solution set is non-empty. And CA is the union of strongly degenerate complementary cones of A, and K, the set of all vectors in Rn which are non-degenerate with respect to A. And in this connection, the two matrix classes Q and Q naught arises. The class Q is basically that for all Q, if solution set QA is not equal to pi, that is, if it is non-empty, then we say that it is a Q matrix, and a matrix is said to be a Q naught matrix if a feasible solution implies, and it will be the solution of the LCP. That is, FQA not equal to phi implies SQA not equal to phi. So in this context, I'll make use of the complementary cones. Given a matrix A and a set alpha, which is a subset of 1 to n, will denote CA alpha as complementary matrix with respect to A. Complementary of A with respect to alpha, and we will denote CA alpha dot j is minus A dot j if j belongs to alpha, or CA alpha dot j is equal to I dot j if j doesn't belong to alpha. And the associated cone, cos of CA alpha, is called the complementary cone relative to A. So these concepts we need it. Subsequently, if determinant of CA alpha not equal to 0, then it is set to a complementary basis, and the cone, complementary cone with respect to alpha is said to be non-degenerate if delta alpha is not equal to 0. Otherwise, it is said to be a degenerate complementary cone. A degenerate cone post CA alpha is said to be strongly degenerate if there exists 0 not equal to x belonging to Rn plus such that Ca alpha x is equal to 0. Now, given a matrix A and alpha, the matrix A is said to be non-degenerate if data A alpha alpha is not equal to 0 for all alpha belong a subset of 1 to n. And any solution of LCB QA is said to be non-degenerate if W plus Z is greater than 0. Otherwise, we will say it is a degenerate solution. And when that every solution is non-degenerate, then a vector Q is said to be non-degenerate with respect to A. We'll also need this terminology. A set is connected if there do not exist disjoint open sets U and V, such that U intersection C is not equal to phi and V intersection C is not equal to phi and C is contained in U union V. Now, for any set S contained in Rn and any x belonging to S, the connected component of a set S containing S is defined as the union of all connected sets C such that x belongs to C containing S. As I said, that so what are the problems that associated with the linear complementarity problem? As it is known that linear complementarity problem, it unifies a large number of optimization problems like linear programming, convex quadratic programming, linear fractional programming, bimetric games, etc. So definitely a large number of researchers was interested to study linear complementarity problem. And so the basic question which arises, what is the class of matrices M for which LCB QM has a unique solution for all vectors Q? So you might have seen that this question is very much relevant, and so that answer is known, partially known about this, and about the next question, what is the class of matrices for which LCB QM has a solution for all vectors Q? This class is denoted by Q, and its elements are Q matrices. Now, an ideal answer will be to provide a set of necessary and sufficient conditions which could be used to check in finite time. And if any, given matrix M belongs to that class. Okay. So that is about the first one. And in case of question 2, that some partial but not entirely satisfactory answers are available. Now we are going to talk about these classes, and so before that, I would like to say some more open problems which are there. That if we ask in terms of complementary cone, question 2 is asking the class of matrices for which the complementary range of M equals to Rn. Okay. Now note that for an arbitrary matrix M, the cone Km is generally not even convex and much less equal to Rn. Okay, so we can at least ask for the class of matrices M for which Km is convex. Now this matter is closely related to what is the class of matrices M for which LCB QM is solvable whenever it is feasible. I have mentioned this class is known as Q0, and the matrices which has this which belongs to those class, that those are called Q0 matrices. Now the open problem associated with this that provide a set of necessary and sufficient conditions which could be used to check in finite time if any matrix M belongs to class Q and Q0. So therefore, so we have two problems in hand, that that uniqueness of the solutions and the existence of the solutions. So these are the two problems in hand, and so here one more concept in the literature which plays an important role, that is called principal pivot transform. Now principal pivot transform of A with respect to some set alpha is defined as follows. So here M is defined like this, that if M is the principal pivot transform of A, we can write M alpha alpha and M alpha alpha bar, M alpha bar alpha like this. And when you take a PPT, the principal pivot transform of A with respect to alpha, that obtaining the pivot on A alpha alpha, then you get a LCB, that as Q prime M, and where Q alpha alpha is like this, you will have this one. And here, interesting thing is that cardinality of the solution set will remain same. Okay. Note that PPT is defined with respect to dose alpha for which state alpha alpha is not equal to 0. Now we try to characterize some of the matrices that using degree theory. Now let me tell you that what is the degree of an LCB map. Suppose f is a piecewise affine function of the form fj given by this, and where this denotes that component-wise minimum, and fa which is from Rn to Rn, be a piecewise linear map, and which I write it down as fax, which is equal to x plus minus ax minus, where xi plus will denote max of 0 xi, and xi minus is 0 minus xi. And note that we can write for any x belonging to Rn, x is equal to x plus minus x minus. Now, if you see that an LCB QA is equivalent to finding x belonging to Rn such that this fax is equal to Q. And if x belongs to the interior of an orthent Rn and data alpha alpha is not equal to 0, so here alpha is set of all I for which xi less than 0. So the index of alpha, you can write it like this. Okay. Say this is equal to sine of a data alpha alpha, data alpha alpha is this. Now so if Q and Q belong to Rn minus Ka and lie in the same connected component, then degree of a Q is equal to degree of a Q prime. And when Rn minus Ca is made of a single connected component, so what will happen? Then we can say that the degree of A at Q is defined and equal at the same constant for every Q belonging to R. And such a scalar, we will call it as degree of A, and we will denote it by degree of A, DEG in the bracket A. And local and global degrees of an LCB map are quite useful in identifying the subclass of Q and Q0. As I mentioned that we want to get a characterization of Q and Q0 matrices using degree theory, and we're going to talk about that some of the well-known characterizations are given a newer perspective in terms of degree theory. Now, let us compute that suppose we have a 2 by 2 matrix, A is like this, and you can draw the complementary cones. In the beginning, I have discussed what are these complementary cones, and we can easily see that R square is made of a single connected component. Okay, and if you draw the complementary cones, you will see that it is a single connected component, and so therefore, in view of the discussion done earlier, that the degree of A is well defined, and it is easy to check. For every vector Q greater than 0, we have exactly 3 solutions. Okay. And as we mentioned that if we add the respective determinantal signs and then we can get the degree, it will be -1. Now, when we talk about degree of an LCB map, that there obviously that one matrix class comes into picture, that is the R0 class. So R0 class, a matrix is said to be in R0 class if LCB 0A has a unique solution W is equal to 0, Z is equal to 0. It has a unique solution. Z is equal, so it has only trivial solution. Okay. So if A belongs to R0 and Rn is a single connected component, and degree is well defined, and if degree of A is not equal to 0, then A belongs to Q. So this is a known result. An interesting property is that it is carried over principal pivot transform. Okay, so if let A belongs to R0 and degree of A is R, then all its PPT degree remains same. Okay. Degree of M belongs to R. The degree of M is equal to plus minus R. It is same. So here, that let us consider a matrix that you can see that A has two principal minors, which is equal to 0. These are the principal minors, which is equal to 0. And so one can check that LCP 0A has a unique solution Z equal to 0. So you can see here that 0A has a unique solution. And so therefore A is an R0 matrix. And for a Q greater than 0, you will see that LCP QA has a unique solution. Okay. So therefore, degree of A is equal to 1 and A is a Q matrix. Okay. So this is a nice characterization that in the previous page which I mentioned, that if A belongs to R0 and Rn is a single connected component, then I can say that degree A not equal to 0 and A belongs to Q. So otherwise it is very difficult to figure out whether a matrix is Q matrix or not. There's no satisfactory way to check whether a matrix is a Q matrix or not. So for a vector K, non-degenerate with respect to A, we define the number degree A as sign of date A alpha alpha. So where the summation is defined over all index set alpha such that Q belongs to pos of C alpha. So sign of X is 1 if X is a positive real number, minus 1 if X is a negative real number, and 0 if X is equal to 0. And this expression star is same for all Q non-degenerate with respect to A and is called the degree of A. And the term inside the summation sign in star are known as indices of A. So Stewart extension, now I'm going to discuss that Stewart extension formula of degree. So in our definition of degree of an LCP map, we made use Q belongs to Rn, which is non-degenerate. The new formula of Stewart extend this definition to vectors that are semi-non-degenerate with respect to. And Goda stated a neater form of this formula and made use of the following result. The number of solutions for certain class of linear complementary problems. So we'll now define, we mean by a vector being semi-non-degenerate. Let Z be a solution of LCP QM. And for this Z, let us define the following index set. And so this is the Sood complement. And so when alpha is empty, then MSS alpha is equal to M gamma gamma when gamma is empty. And MS alpha alpha is the identity matrix of an appropriate order. The solution Z is called semi-non-degenerate if the corresponding principal submatrix M alpha is non-singular, where alpha is defined as above is non-singular. So a vector Q belongs to Rn is non-degenerate with respect to M if every solution of LCP QM is semi-non-degenerate. And for a non-degenerate matrix, every Q belonging to Rn is semi-non-degenerate with respect to M. Now Stewart's extension formula of degree M for any Q, any Q belonging to Rn semi-non-degenerate with respect to M can be stated as that this is the formula degree of M is summation of sign, date, determinant of M alpha alpha, and degree of MS alpha alpha. Where the summation is defined over all index set alpha, and Q belongs to pos C alpha. And indeed, if M is a non-degenerate matrix, then the above definition of degree is valid for any Q belonging to Rn, and sign of X is 1, that if X is a positive real number, and -1 if X is a negative real number, and 0 if X is equal to 0. So this two-word formula, that extension formula, this is very useful to figure out the degree. So that is illustrated in this example. So yeah, let us consider this matrix, and it is easily seen that no principal minor it has no principal minor 0 and LCP either to 1, that is 1 0 0. This has that A and the given matrix A. This has the unique solution W is equal to either to 1, Z is equal to 0. Now, if you make use of the Stewart extension formula for Q is equal to either to 1, then degree of A may be found as the same as that principal submatrix of A, leaving the first row and first column. And you can see that if you look at the first row and first column. So this is -1, 2, and 1, -1. And you have seen in the previous example, no, that so here degree of A is -1. So it follows that degree of A is -1. Now we are going to discuss the matrices of degree plus minus 1. As all of you know that a P matrix in the context of LCP, that is very important, because that if A is a P matrix, then LCP QA has a unique solution for all Q belonging to Rn. And it is defined as that a matrix is said to be P or P naught matrix if all its principal minors are positive or non-negative. And even, as I said, that even the definition, if you look at the definition, that this is just for checking the principal minus positive or non-negative, but there's no satisfactory way that you can find out how to check a matrix is P or P naught. It is still unsolved. There's no satisfactory algorithm for this. In fact, that in the beginning, that maybe that 20-25 years back, Murthy tried to look at this problem. So he tried to give a some characterizations which ultimately can lead to a problem of checking the matrix, the 2n plus 1 vectors, the checking that to conclude that whether matrix is P or P naught, but it doesn't work for the higher degree, and there are some counter examples out there. Then after that, not much work has been done in this direction. So it's still that open, and if the degree of A1, whenever A is a P matrix, then degree of A is always 1, and a P matrix is also a Q matrix. A is called the N or N naught matrix if all its principal minors are negative, or N naught if it is non-positive. The N and N naught matrix, this is also a well-studied matrix in the literature over the years, and a lot of researchers have worked on this class of matrices. In fact, if you look at LCP, there are more than 50 matrix classes out there in a paper by Cottle, and all these matrix classes are of great importance in the sense they have nice structures, and that with respect to solution of LCP, there are nice characterizations out there, and still there are lots of problems which needs to be studied with respect to those matrix classes. That to the matrix theoretic researchers, maybe that P naught and N naught, these matrix classes are well known. But apart from that, that large number of matrix classes which arises in the context of LCP, many are not well studied. So therefore, a matrix is called N or N naught matrix. Then when A is the N matrix, then degree of A is either 0 or -1. We denote K is the set of all vectors in Rn which are non-degenerate with respect to A, and for a matrix to belongs to class Q, it suffices to observe that for any Q belonging to Rn minus QA, LCP has a solution. So in this context, that the degree that one matrix class, which is called superfluous matrices, that has come up, and A is called a superfluous matrix if LCP QA has at least K+1 solutions for every Q belong to Rn minus Ka, given that degree of A is equal to K. And for any integer K, there exists an R0 matrix of degree K, then there exists a superfluous matrix of degree K. And there's an observation that about Q matrix is that this is the Q matrix, this is given by Howe, and it is shown that A is non-degenerate, and Howe proved that degree of A is 0. And, so therefore, it was Howe who first showed that with A that there exists a 0 degree Q matrix. This particular that studying various matrix classes using degree theory, there are lots of problems which are open, and there is a lot of scope is there to study the variety of matrix classes which arises in linear complementarity problem using degree theory. Thank you. These
Thank
are
you,
the
Professor
references that one can look at. I will say that these are partial list. You can see the references there.
Thank you again. We may have time for just one or two questions.
Don't. Professor TSS, I have an announcement to make.
Please.
After Professor Raghavan's lecture, we will take a break of 5 minutes. We will have to live with the limitation of the present technology. Whatever the MS team, it cannot stream for 3 to 4 hours continuously. So we take a break of 5 minutes in between. We'll just change the system after Raghavan's talk. This is what the announcement that I want to make. Yeah, please proceed.
Okay. So now I invite Professor T.S. Raghavan, a very distinguished analyst, to give his talk.
It is with great pleasure that I am able to be part of this superb conference in honor of Professor C.R. Rao, my thesis advisor. I am deeply touched by the efforts which have been put in by Manipal University, headed under the direction of Professor Manjunath Prasad and his team of excellent students. C.R. Rao, when I joined in 1962 at the Indian Statistical Institute, C.R. Rao was so compassionate to me, and he allowed me to have my own freedom to continue with whatever area I wanted to do research in, and I chose to work in statistical decision theory and change it from there to game theory. And he said, you continue on. And I was also interested in matrix theory at that time. He said, why don't you give lectures on matrices and even write a note That's how I came to appreciate his the way he treated graduate students with freedom and compassion. When I finished my PhD, the day I submitted my thesis, there was a call from England from George Barnard, the famous statistician, who wanted somebody to join him in the department, the new department of the University of Essex. C.R. Rao suggested immediately my name, and that's how he changed my whole life. So all I can say is Guru Brahma, Guru Vishnu, Guru Devo Maheshwaraha, Guru Sakshat Parabrahma, Tasmai Sri Gurave Namaha. My respects to this great statistician, a mentor, and everything. With this, I would like to start my lecture. I am presenting my talk for the first time on a connection between matrix games and linear complementarity. This is a joint work with Deepti Dubey of Shivanada University, Professor S.K. Niyogi of the Indian Statistical Institute, and myself. It has two parts. The first part is linear complementarity problem, and the second part, it has to do with zero-sum 2% matrix games, which shows the connection. What is linear complementarity problem? Suppose you are given an n by n real matrix M, and you are also given an arbitrary real column n vector Q. When these two are given, for every arbitrary Q, can we find a solution to the system of equations W equals mz plus Q as equation 1. W and Z are vectors non-negative, all coordinates are non-negative, and W and Z are orthogonal, namely each coordinate wise Wi, Zi is 0 for each I. Any solution to 1 and 2, namely W equals mz plus Q and W non-negative, Z non-negative, is called a feasible solution. And any solution to 1, 2, and 3 is called a linear complementary solution. Namely, you should satisfy 1, 2, and also W and Z orthogonal. Now, before trying to do this one, when we look at this system of equations and inequalities, if you consider only 1 and 2, the set of solutions W and Z, if it is non-empty, is a convex set. So we are not searching for any arbitrary point of the convex set, and it is a polyhedral convex set. So we are concentrating mainly on looking for extreme points of that set, and among them looking for those which will satisfy also condition 3. Now, instead of searching for that one straight away, Lemke came with the following idea. Consider an auxiliary system where W equals mz plus Q and plus a scalar z0 times the vector with all coordinates 1, which is the vector E. And again, WZ, Z0 non-negative, and W and Z are orthogonal. No matter what M is, what Q is, you can always find a Z0 sufficiently large that will solve 4, 5, and 6 with no sweat. Incidentally, any solution to 1, 2, and 3, namely, any solution which satisfies 1, 2, and 3 will automatically satisfy 4, 5, and 6, provided you put Z0 as 0. Unfortunately, on the other hand, any solution to 4, 5, and 6, until and unless Z0 is 0, may not satisfy even 1 and 2. That means it may not even be, the original problem may not even be feasible, and yet you may find a solution which with positive Z0. So we first impose what is called a non-degeneracy assumption, which is the usual assumption in all areas like linear programming, simplex method, etc. Under the non-degeneracy, a pair of coordinates wi and zi as mate variables for each I. Any basic feasible solution to 1, 2, and 3, 1, 2 will satisfy 3 if and only if exactly one of the mate variables is basic. That means either wi is 0 or zi is 0, but not both. So in all honesty, our problem under non-degeneracy is searching for such a solution. We will motivate what we have in mind with a simple example. Consider the matrix M, 2 by 2 matrix, 5, minus 4, minus 3, 6, and Q as 1, minus 3. Suppose Q is positive, we have no sweat. Our original problem can be very easily solved. Simply, let me indicate again. The original problem can be solved if Q is positive or non-negative. All you need is put Z equals 0 and W becomes Q and you have everything satisfied. So the real difficulty is only when Q has some negative coordinates. So we start with such an example. Now we need to develop first a feasible solution that satisfies 4, 5, and 6 for a suitably large Z0. Now the moment you increase Z0, all of them will be satisfying those 1, 2, 3 conditions. And so that means these solutions form an edge of unbounded length. Now this unbounded ray will have one end at an extreme basic feasible point, and like we use the simplex tableau method to first locate such a point, satisfying 4 and 6. So what we do is you make W1 and W2 as basic variables, and what we see is we have two equations. So W1 minus 5Z1 plus 4Z2 minus Z0 equals 1. W2 plus 3Z1 minus 6Z2 minus Z0 equals minus 3. This is your initial table, but unfortunately W2 is minus 3. So we need a feasible solution. So the first thing which we do is to get rid of W2 and replace it by the auxiliary variable Z0. This is the first starting point. So initially we bring Z0 into the basis. The standard technique of row operations will help us to make Z0 as the unit vector, and it's number 1 appears at the cutting of W2 row and Z0 column. So we get the next table. So W1 and Z0 are now the basic variables, and the current solution is W1 is 4 because the solution is identified with the last column Q. W1 is 4, Z0 is 3, all the other variables are 0. Now we notice the only positive variables are in the basic variable column. This is clearly a solution to 4, 5, and 6. We reached this table first time by making W2 non-basic. Now what we notice is not only W2 is non-basic, its mate Z2 is also non-basic. Unlike W1, which is basic, its mate is non-basic. W2 is non-basic. Z2 is also non-basic. Only recently we made W2 non-basic, from basic to non-basic or non-zero to thing. Now we bring the mate of W2 into the system. That means the column corresponding to Z2 enters the basis as in the simplex method. And we use the usual ratio test to determine who leaves. Should W1 leave or Z0 leave? If Z0 leaves, we'll be back in W2. So it's actually, it is only W1 which will leave. And that is determined by the star entry which we notice in this table. Now, Z2, in the next step, because we have brought in Z2, so that's the table which we get. So the column corresponding to Z2 will be 1, 0, and the solution is Z2 is 4/10, Z0 is 6/10. But we are still not able to eliminate Z0 from the system. What we now try to do is, we look at the solution. Now, Z2 is positive, W2 is 0. Z1 is 0, W1 is also 0. Just previously, we had W1 into the system, which we dropped out. So now we made from basic to non-basic. So we try its mate to become basic. Its mate Z1 has to become basic, which means the column corresponding to Z1 enters the basis. By the ratio test, the only allowable condition is, because if you look at the Z1 column, the first entry is negative, the second entry is starred entry is positive. So we can take the ratio only on the Q column with the Z1 column, the ratio corresponding to positive entries. And that makes it necessarily that Z0 must leave and Z1 must enter. And that's what happens now. We find the only one to vacate is Z0 by the ratio test. Now we have come to the solution basically. Z1 and Z2 are positive, W1 and W2 are 0. They are complementary, and then they satisfy all the conditions. Z2 is 12/18, which is 2/3. Z1 is 1/3. W1 is 0. W2 is 0. And we have arrived at a solution. We were simply lucky. I knew that for this class of matrices, Lemke's algorithm will work. For example, our procedure has to fail when M is this matrix with all entries negative and Q also negative. What will happen is we may be able to find a positive Z0 such that Z equals 0 will satisfy the conditions. But unfortunately, by this pivoting method, you will never let Z0 leave the basis. That is you can try it with a simple example, or the same example. Now we would like to show that we can give a class of matrices with certain conditions guaranteeing the termination when they admit a feasible solution. This is what we want to study via zero-sum two-person matrix games. Now, you look at this polyhedral set. The idea is that we start from an unbounded ray to one extreme point, and we travel only along this edge, where all these edge points satisfy the complementary slackness condition. So it is some kind of an one-dimensional lines which are going. And the real thing is, if you see a thicker line now, the thicker line says that is how the path is now moving. The path movement is equivalent to saying from one tableau you move to another tableau by adjacent extreme points. But then the moment it stops, it won't move once Z0 becomes non-basic. But we are not sure whether the path will go that way, or it could also go the following way. You can see the new path. It will terminate provided Z0 is still non-basic. But if Z0 is basic, it may go and then reach another extreme point. I can call that extreme point 1 minute. other extreme point which I have noted. From there, it may go to another unbounded ray, which means we have lost our effort to solve the problem. So this is what is called, the first one is called the primary ray. The second one is called the secondary ray. If the matrix is not in the right structure, what could happen is we may end up with a secondary ray, in which case the problem is not solved. It doesn't mean that the problem has no solution. It means that my algorithm is not able to solve the problem. So we have only one algorithm right now. There is no other algorithm. That is the algorithm of Lemke, which lets you move from table to table only because the complementary path travels in such a way that you enter through a corner and you exit through its made corner. So the made is made positive and one of them is made zero, like that. So that's all we are doing now. But when are we sure that it will terminate at a solution? That's the final question. And to understand that question, initially many attempts have been made by Eves, by Garcia, and quite a few people, including Lemke. But what I realized is it is closely connected to a game theoretic problem, and that's what I now want to talk about. So we would like to show that we can give a class of matrices with certain conditions, guaranteeing the termination when they admit a feasible solution. We want to study through game theory. What is that? So I give a small, basic baby introduction. What is a matrix game? We consider our own matrix M as the matrix, which two players play. Player one is the column player whose interest is to get the maximum amount from player two, the row player. So he chooses secretly a column, and player two chooses secretly a row. But they may not necessarily choose them with exact probabilities, or with exactly one of them. They may also perform a chance experiment by which they may select a row or a column. So the chance experiment is with probabilities P1, Pn, the column player chooses the columns. And the row player chooses with probabilities Q1, Q2, Qn. And if the jth column ith row is reached with probability Pj, Qi, then the income to player one, namely the column player, is Mij, and he receives this income with probability Pj. So his expected income is at least Vm for a suitable P, where Vm is a unique number which has the following property. While column player can hope to get on the average Vm independent of what player 2 does, same way player 2 can also select his rows with probabilities Qi, guaranteeing that his loss is no more than Vm, and that Vm is called the value of the game, and von Neumann proved there exists such a Vm. And these P and Q are called good strategies for the two players. They are called optimal for 1 and optimal for 2. Now let me put the condition which I want to impose on this matrix. Condition 1, that the matrix game M has value 0. 2, if I take the transpose matrix and consider every one of its principal submatrices, they all have value non-negative, where column player is the maximizer as usual. So now we are ready to state the main theorem. The following is the main theorem which connects linear complementarity with game theory. Let Vm be 0 and Vm transpose Kk be non-negative for all principal submatrices. What do you mean by principal submatrix? If you choose the 4th, 9th, 15th row, similarly you choose the 4th, 19th, 15th column, that such submatrix is the MTMKK, where K is 4th, 9th, and 15th. So like that, every one of those submatrices if you calculate their transpose matrix value, it must be non-negative. That's not the only condition. Now, the second condition is for any optimal U mixed strategy for the column player, there should be an optimal X for the row player such that U and X share the same positive coordinates. That is, if Ui is positive, Xi must be positive. If Ui is 0, Xi is 0, and conversely. Further, we need one way condition. M of Ui, which is the expected income to the maximizer, when player 2 chooses ith row is 0, the same way in M transpose X, I must also be equal to 0. Once this is given, the theorem says the linear complementarity problem can be processed by Lemke's algorithm with a solution to 1, 2, and 3, provided 1 and 2 have a feasible solution. We can always check for feasible solutions by simple linear programming. So this way we know that when this condition is satisfied, the theorem guarantees that if you start with a feasible solution, there is no way that if you start from the primary unbounded ray, you will not hit another secondary unbounded ray. You have to stop at an extreme point or a basic feasible solution, which is complementary. The key conditions, because I'm not giving the proof is long and quite a little bit involved. With the limited time, I cannot do that. All I can give you is the feeling of it. The conditions of the above theorem guarantees the existence of two diagonal matrices, lambda, capital lambda non-negative, capital omega non-negative. Omega can also be assumed as non-negative as well as positive, such that lambda m plus m transpose omega u is 0, where u is optimal for 1 and x is optimal for 2. So the Lemke's algorithm applied to the auxiliary problem hits another unbounded ray different from the primary ray if and only if the system 1, 2 is infeasible. So that is these are the two key ideas of the proof. They are a little bit long and you need to manipulate to get them. If people are interested, I can send later the paper. This is the picture which we took. In fact, Teja, Sierra's daughter, she took when we went to visit them 3-4 years back. And Mrs. Rao was so happy. We took some mangoes and she was like a child. She was saying, I want mangoes. I want mangoes. What the ma, she was telling. No, she said, I want mangoes. And then we stood there and I prostrated 4 times before this, my great teacher, and got his blessings. And this is one of my most memorable pictures. And another one, which I also want to show, is the following. So this is a few years back, quite a few years back, when Professor Rao was honored by the University of Wisconsin-Madison. And I went all the way to Madison to see him. And we were in some GM Naidu's house. That's where we sat. And then this is a picture when I was probably much younger. These are the 2 pictures which I have of Professor Rao. And I cherish them like anything. Guru Brahma, Guru Vishnu, Guru Devo Maheshwaraha, Guru Sakshat Parabrahma, Tasmai Shri Gurave Namaha. Thank you.
Thank you, Professor Raghavan, for the lovely talk and sharing your memories. Wonderful. I think we have time for a few questions.
Professor Raghavan, I just want to say that I have used your Krishna to start the Morning, sir. Thank you.
Hello? Hello?
Hello.
Couldn't hear you properly, Manjunath.
Yeah, I'm also not able to hear the other side.
Okay, can you hear me now?
Yes.
Good sloka in the morning.
Yeah, it is.
So
Now,
when we started
4
the
a.m.
first session, we have used it. So for that, I must thank.
I don't hear you. I'm sorry, I'm not hearing you again.
Hey, computer. Yeah, they may not be able to. Here, yeah, bad network quality, it says. Okay, I'm sorry. Please continue. Hey, you tell
So
him.
let us thank Professor Raghavan again. Thank you, Professor
Sir,
Raghavan.
Professor Prasad is not able to connect from his internet connection. It seems like there is some internet glitches. He would actually like to thank that he has used your Guru Shloka in the morning inaugural function.
Oh, thank
That's what
you.
actually he would like to actually express.
Thank you. Thank
you.
Thank you, Professor,
Okay,
for chairing the
thanks, everybody.
session.
Thanks for.
Moving on to next session, we have invited talks from Sean Pallet and T. Krishna Kumar. Sean M. Follett is a professor at University of Regina, Canada. He is going to speak on almost principal minors of symmetric matrix. T. Krishna Kumar is a director, Rockwell Analytics, USA. His topic of presentation is Probabilistic Foundation of Econometrics. Dr. C.R. Rao's contribution.
We will be having this session exactly at 6 p.m. Indian Standard Time. We'll get back to you in 5 minutes. Thank you, sir.